I wish each one of them good morning, good afternoon, and as well as good evening to some parts of the world to all the participants. Meanwhile, we ask you to all the participants to keep mute of your audio while speaking. If you have any problem with your uploading your PPT, you can send to a mentioned email ID. We are sent in chat box. We'll be playing behalf of you. I'm especially thankful to Mr. John William, who hemmed his heavy duties and responsibilities to make his happen today. I would like to thank the participants, especially those who are joining from miles of distance and sharing your valuable experience and ideas. With a good number of participants, I'm sure this conference will be memorable, highly educated, and not to missed event. This webinar aims to provide to people to share analysis and results about all features of based on topic like material science and nanotechnology that is going to happen today, September 17th. Myself, Mr. Rakesh Madhu, representing Inovine Conferences, welcomes all distinct guests, dear doctors, scientists, educators, colleagues, friends, ladies and gentlemen. It is a great honor to me to welcome to join this webinar on behalf of organizers of webinar on material science and nanotechnology. I would like to express my most sincere gratitude to your presence in this opening ceremony as the gateway to initiate to our program. I am especially thankful to Mr. John William to sharing his by making this scientific program. This webinar aim to provide a different technology regarding the material science and nanotechnology. The topics we'll be covering today will be material science and engineering, nanotechnology basics applications, smart materials and techniques, electronics, optics and magnetic materials, biosensors, and so many we have more than more than 25 to 30 tracks are there. We'll be talking different topics based upon the concept. Once again, I request all the participants make sure to introduce everyone at the beginning. So now I would request the first keynote speaker of the conference will be Dr. Soshu Kirohai from Joining and Welding Research Institute from Osaka University from Japan to start the presentation. The topic will be stereolithographic additive manufacturing of ceramic components with nanoparticles based materials.
Excuse me, I don't think he is online.
Yes, sir. Yes, sir. So we'll do one thing, sir. We'll do one thing. Just you can start your presentation. Just I'll begin introducing you. You can start your presentation by uploading your PPT from your side.
Sure.
Yes, sir. Actually, we have got 3 video presentations, sir.
Okay.
Yes, that's the problem. We'll be playing behalf of them. But better we'll be playing after 1 or 2 hours because the remaining speakers will be joining.
Sure, no problem.
Yes, sir. Just so now we ask Dr. Vijay Kumar from University of Mysore from India to start the presentation. The topic will be multifarious and high refractive index glasses by levitation technology.
Yes, thank you very much. Myself, for Dr. Vijay Kumar from the University of Mysore. I am working as a Ramanujan Fellow as well as a scientist at the Department of Chemistry, University of Mysore from India. So today, I would like to thank the Inovine for giving me an opportunity to share my research experience and research topic with this webinar. So today I would like to introduce multiferroics and high refractive index glasses by levitation technique. Before going to the actual topic, just I will introduce what do you mean by levitation technique. First, I will go with the introduction. What do you mean by levitation technique and how we can get it? So levitation technique is nothing but we can obtain the same facility in space, but depending on your requirement, depending on your material preparation, you can choose the facility and you can make a material depending on your requirement. So first, this is y-axis is gravity and x-axis is the duration. So here I have mentioned, like you can see in graph, second to year, and from 10 to the power minus 2 to 10 to the power minus 6, that is in the scale of gravity. But when you go to space, there is no gravity. I mean, we are saying that reduced gravity, gravity is almost zero. But depending on your requirement, we can get a zero gravity in seconds or in a month, in a minute, hours, or in a year. So let me give you an example. Like if you want to get it in a second, we have a facility like a parabolic flight that is available even in Japan, even in Europe, even in NASA. They are giving a facility, but using this facility, we can get only 20 seconds of microgravity. That is a reduced gravity. There will be no gravity at all. I'm going to show you a video later. And if you want to get a reduced gravity in a minute, that we can use a sounding rocket. But using these, we can do some fluid science experiments and metal solidification. And if you want to get I mean, some of the experiments we cannot complete it in seconds or minutes, but we need longer time. But depending on our requirement, like hours or a day, we can choose. And for a longer period, we are choosing a International Space Station experiment. So by using an International Space Station, we are getting a longer duration of reduced gravity, as well as the gravity quality will be up to 10 to the power minus 6 G. That is called microgravity. Micro means 10 to the power minus 6 G. So by using this, yeah, I will show you a parabolic flight, how we can obtain the zero gravity like this. This is the parabolic flight that goes, I mean, that starts from this is the altitude, this is the time, y-axis is time, that is in meters, that starts from point A and it comes to point B, then gravity is going to increase. From B to C, you can see the gravity is going to increase, but from point C to D, there will be no gravity at all, that is zero gravity. So from D to E, again, it is going to increase, that is coming down, and E to, that is the rest. So this is me. I boarded this parabolic flight in Diamond Air Service in Japan, and I got an opportunity to fly in to really experience the zero. You can see this video. So my colleague, he's floating now because that flight has reached a parabolic shape. That should create a parabolic shape. So if you get a parabolic, that's why it is called a parabolic flight. So by using this flight, we can get only 20 seconds of microgravity, but we cannot do material science. I mean, most of the material science experiments in 20 seconds. Of course, some of the experiments we can complete, but yeah, you can see the left-hand picture. So flight is going up with a plus 45 degree and comes back with minus 35 or minus 45 degree. So that will create this parabolic shape. That's why it is called parabolic flight. So during that period, that is like a 20 seconds will be in zero gravity. That is like a reduced gravity. So let us see an example like how water behaves in space. One of the major problem, I mean, more difficult part is to control the water in handling water in space. So he is Dr. Mamoru Mori. He is a Japanese first astronaut who lived in on board the flight, and he conducted some of the material science experiment by using a simple technique. So this is a water droplet. You can see he is going to introduce a flower, that is a cherry flower. So you can see that water bubble is bigger than this flower. So it is going to swallow. But one of the other thing is when you take water to space, I mean, there is no gravity. So just because of the surface tension and there is no density difference at all, water will become like a jelly. It will be not in the form of liquid. So you can see it's swallowed and it's moving. So in space, there is no density difference at all. So you can see it's keep on moving. So it's keep on moving, is trying to blow it up. So that indicates that in space, water bubble or any material can move anywhere, but it is very difficult to control the movement of the material or a water droplet. So here water droplet, or if you take any material, it is very difficult to control the movement of the material. Yes. So now here in the right hand side picture, you can see the water droplet. So he's a Mr. Scott Kelly. He is an USA, I mean a NASA astronaut. He is hitting a water bubble with a pedal. So this water bubble is moving up and down. It is not going any other directions. It is only moving up and down. So that indicates that if you use some technique, you can able to control water droplet or any material in space. So in zero gravity, liquid samples can be held without any container. Since it is floating, you don't have to keep any container. That does not require any container to hold the liquid samples. That's why it is called a containerless. We don't use any container to hold the samples. So containerless condition that can be obtained by opposing gravity with an external force. Yes, in space we can get it is floating, but on Earth, what we can do? Can we create the same environment on Earth to conduct some of the material science experiment? Yes, it's possible. I'm going to introduce some of the techniques what we can use on Earth. So containerless technique is like we don't use any container to hold the liquid or any material. So this is a electromagnetic levitation. You might have heard about the magnetic maglev, that is a magnetic train. So that is the same concept. That is in this method, the material should be electrically conductive because we are using an eddy current and magnetic force will be generated and sample will be floated. That this is a copper coil. So eddy current is flowing in this coil. So magnetic field is generated. So material should be electrically conductive. So the material will be floating in between the coils. And we can also we can use the aeroacoustic levitation. That is like a speaker or a sound. So these are the speaker, that's the waves. And this is the sample is floating. So we are not holding sample with any container. That is why it is called containerless process. And one more technique is like a electrostatic. So this is like two electrodes. One is a top electrode and a bottom electrode. I'm going to explain that principle later. And the sample is floating in between these electrodes. So in this technique, I mean, in aeroacoustic levitation, you can use only oxide sample because we cannot control the atmosphere. If you use metal, that will be like a metal oxide. So we cannot get it in the form of pure metal. So that's why we use oxide sample. But here in the electrostatic levitation, we can use all kind of materials like alloys, metal, semiconductors. You can use oxides as well. And the most other suitable technique is like a aerodynamic levitation. That's why in this technique, we use the gas force to suspend the sample. So without having any container, so that we can use the laser to melt the material and that will be in the liquid state. So once we cut down the heating source, that will be like a solid. So I'm going to explain the principle in the coming slide. And other technique is like a drop tower. This is a 26-meter drop tower in JAXA. That is in Japanese Space Center in Japan. And here we can melt the sample at the top. You can see this arrow. So we can melt this and you can drop the droplet, that is like a molten liquids here. And while coming from this point to here at the bottom, that has to travel to a height of about 26 meters. While coming from this to this, from top to bottom, that liquid will become a solid. During this process, there will be a lot of phase transition. We can get a new kind of material or like a metastable phases or a stable phases, but property will be completely different. So I'm going to explain that later in the coming slides. That is like a materials are no longer in physical contact with any container. We can prevent melt contamination. That we can also minimize heterogeneous nucleation. This is a useful tools for high temperature experiments under containerless condition. So how we can get one of the other advantages, like we can cool the liquids below its melting point. For let's say an example, you can take a freezing point of water is like a 4 degree or a 0 degree, you can take it. So this is the temperature 0 and minus is like a water temperature. We are cooling the water using an ice bath. You can watch this video, and this is the one of the major advantages. We can also get it in the containerless process. We can cool the liquids about 300 to 400 degree below its melting point. So this is the water we have cooled to -7. Once you disturb, once it becomes a crystal, so you can see once it freezes, it has to come back to its freezing point. That is like a 0. You can see the -7 to 0. So that advantages can also be obtained in containerless process. And one more video you can see, this is a free surface water droplet. So outside temperature is like a -17 degree or -20 degree, but air is hitting the surface of the water droplet. It is disturbing, so that nucleation is taking place at the surface or any part of that, and bottom is touched with this ice. So nucleation can also happen at the bottom or at any side. So what is the advantages of this one? So on ground, we need some container to hold any material or any liquids. But in space, since there is no gravity, there is no density difference at all, I mean, the reduced gravity, the materials will be floating. If you take a liquid will also be floating just because of the surface tension, and we don't need any container. If we use this technique, what are the advantages? So there is no reaction with container. We can get it in the form of high purity sample, and we can prevent the heterogeneous nucleation and achieve deep undercooling. That is, like, we can get 300 to 400 degree below its melting point. And we can also reach high temperature, that is like a 3000 Kelvin. In this experiment, we have used the gas force to suspend the sample. This is called a gas levitation or aerodynamic levitation. This is the nozzle, and this is CO2 laser. We use the CO2 laser to melt the sample to become a liquid. So this is the gas flow. It is flowing upwards, and sample will be moving up. As you can see in the video, it is floating, and the sample is already melted. Once it becomes completely molten state, that is completely melted, then you can cut off the heating source. Then there will be a phase transition from liquid to solid. During this transformation, there will be a lot of phase transformation. We can get a lot of phases, so with a different kind of properties. So this is the top view of the technique what we have. This is the high-speed video camera. This is the same conical nozzle, and we flow the gas from the upwards. This is the conical nozzle. This is the pyrometer. We use this high-speed video camera to capture the surface morphology of the sample. The pyrometer is used to capture the surface temperature of the sample, and this is the CCD camera to capture video. And this is the gas outlet is going up here. The sample will be moving up so that it is nowhere contact with the any container or a nozzle. So this is like a nozzle. We flow gas upwards so that sample will be moving up. You can clearly see this in this nozzle. So how we can make a sample? So here I am going to introduce how we can use the oxide sample first. So here you can take any metal oxides. You can make a powder, and you need to make a pelletizing sample, because if you put a powder in the nozzle and if you flow gas, that powder will go out. So that's why we need to make it as a pellet. That's like a tablet, so that we can melt it. You can make a spherical shaped sample, and sample size will be up to 2.5 to 3 millimeter, and mass will be like 20 to 30 milligram. We use various kind of gases depending upon our requirement, and by using this, either you can choose to make a crystal or in the amorphous phase like a glasses. And here we use some of the multiferroic materials. That multiferroic materials is like a materials which has both ferromagnetic and ferroelectric properties. And here we use some of the nickel ferrites and cobalt ferrites and manganese and rare earth iron oxides and barium titanates and so on. So some of the other ferroelectric material like barium titanate I'm going to introduce, and also bismuth iron oxides we use by using this containerless levitation technique. So we can see how we obtain and what are the properties, how it changes. And this is the example for nickel ferrites. This is the standard commercially available sample. This is the sample process using a containerless process or the gas levitation. So we saw that most of these nickel ferrite phases are present, but along with that, nickel oxides was like a small dendritic phases were obtained in the form of nickel oxide. So once you anneal the sample at high temperature, this nickel oxide will be transferred into a nickel ferrite. So at high temperature, we can obtain the single phase of nickel ferrites. So this is the microstructure of the sample process. Initially, we can, the as prepared sample, you can see the dark, this is a brown, you can see the gray phases is like a nickel ferrites, and this dendritic, like a white patches, is like a nickel oxide. Once you anneal these at high temperature, that's like 1400 degree, and nickel oxide will be transferred into nickel ferrites. And finally, you are going to get a single phase of nickel ferrites. And along with that, we have also processed some of the ferrite sample, that is rare earth iron oxide, just by changing the effect of oxygen partial pressure. Just by changing the oxygen, we have obtained a different phases of the material, but just by changing the oxygen, we obtained the same phases for the different kind of materials. So here you can see the excited pattern matches with the hexagonal phases. And this is the crystal structure of the hexagonal rare earth iron oxide that has a non-centrosymmetric structure that shows the ferroelectric properties of the hexagonal phases. That hexagonal phase has a spin of a P63 cm. And just by changing the oxygen partial pressure, we can prepare the same ferroelectric structured materials just by changing the oxygen. We can also control the oxygen partial pressure by using this facility. Here, one of the major thing we need to keep in mind that why we have got these phases. The one idea is like iron has a tendency to change its valence state depending on the oxygen partial pressure. It can change from Fe3 plus to Fe2 plus. That is, so that's why the ionic radius is going to change, and also a tolerance factor is going to decrease by changing the valence state of iron. So that's why we obtain the same phases. If it matches with the same ionic radius, then we are going to get the same phases for the different materials, different composition of the same ferrites. So from this, we can say that we can explore a new functional materials by using this technique. And here, as I mentioned, we have observed the surface morphology by using a high-speed video camera and also CCD camera. We have, this is the temperature time profile. This is the time and this is the temperature. Initially, it will be at a molten state. And once you cut off the heating source, it cools down, cools down, cools down. At this point, nucleation starts. That is, the solid phase starts to appear at this point. You can see the S1 is indicating the solid phase and L is the liquid phase. Here, initially, you can see both the phases like that. You can clearly see the phase boundary between the liquids and solid. And once the temperature increases and it completely becomes solid. In some cases, it stops at this point and comes down. But in majority of the oxides, there will be two phases. One phase is like a metastable phases, which has a small, the lower melting point than the stable phases. The stable phase has a higher temperature, that is like a S2. That will remelt the primary phase of that is the metastable phase. And by XRD, we are not able to see the primary phase. For that, we have a different technique. I'm going to show it in the next slide. So this is the phase 1. We are saying that solid phase 1 and solid phase 2. And this is the video. You can see this dark region is like a liquid, and you can see the brighter spots. So that is a solid. This is a liquid, and because temperature is going down, so that's why you can see the darker region. And once the nucleation starts, temperature starts increasing, that intensity of the light is increasing. So that's why you can see a brighter phase, brighter spots. This is a solid primary phase. And along with that, there is one more phase, but we are not able to see that in video, but we can see it. This is the primary phase. You can see here. And this is the primary phase. This is the liquid. This is the primary phase, and this brighter is a secondary phase. So you can see it appears here. You can clearly see this is liquid. This is the solid S1 and solid 2. Here also in picture you can clearly see this is the first phase, and this is the second phase, and this is completed with a second phase. And it goes like this. This is the liquid. This is a solid and liquid. And tau is like a time taken, delay time. And this is the phase 2, and phase 2, solid phase 2 is completed. So this is delta 1, delta 2 is like undercooling. That is the recoalescence. Delta 1 is represent the solid phase 1, and delta 2 is a solid phase 2. So in some cases, we are not able to identify the primary phase. For that, we use a synchrotron radiation source in Japan. That is beamline experiment. That is a in situ observation. We used 50 kilo electron volt X-ray. So that passes to the molten state, and that passes, and we can get a X-ray out of it. We can get a XRD pattern. This is for the liquid. We are not able to get any spot. That means there is no crystal. But as the crystal phase increases, solid phase, you can see the number of spots here. If you analyze that these spots, you can see, we can get this kind of peaks, that is like a XRD peaks. If you match with the structures, whether it is a stable or a metastable phase, that completely holds good with a metastable phase with a hexagonal structure. And one more example is like a barium titanate. It has, we have taken a two composition. That's like a barium 113 and 125. You can see whether it is the peritectic point and the eutectic point. You can see the difference now. And barium titanate has a different crystal structure depending on the temperature. And it has a cubic and tetragonal phase. But if you see the ferroelectric dielectric constant of cubic and tetragonal phase, it is about 200 or 6,000. But the material processed in containerless process has about 150,000. That means it is about 15 times higher than the cubic structure, almost 150 or 500 times greater than the tetragonal structure. Why we got this result? That is like we got a hexagonal structure with an oxygen deficient sample that shows the dielectric constant of about 1,000. So that sample can be used as a capacitor, that is 1,000 times the higher electric charge to be stored, that is can also be used as a piezoelectric material. So by using another composition of barium titanate, one got a crystal, we have changed the composition, that is like eutectic point 125, but surprisingly we got the glass samples, but these glasses are having a high refractive index. Commercially available glasses have a refractive index of 1.5 to 1.8 or 2, but the sample we have processed using a containerless process has a refractive index above 2.2 or 2.3. If you prepare these balls, we can directly use these balls for your mobile phone lenses or camera lenses, endoscopy lenses, and for the other applications like a fiber coupling, endoscopy, optical disc, and so on. And if you see the commercially available sample glasses, that has a refractive index about 1.8. But the sample process in this technique has a refractive index that is close to diamond. Diamond has the highest refractive index of 2.4. And these samples will also have a refractive index close to diamond. But in future, we can clearly say that these samples may replace diamond. Whether we can also use this sample, but we are checking the safety reason, and we can also use this material as a gemstones. And other samples we have processed, and also we have got the glass sample with a high refractive index of 2.3. for the lanthanum. We can, by another way is that you can increase the refractive index by increasing the density of that sample. So we can increase the density so that we can, to increase the density, you can introduce some of the rare earth heavy metals, so that density is going to increase, so that we can also obtain the high refractive index. So as I mentioned, we have also a space experiment. On ground, we can prepare the samples by using a levitation technique, but we want to check that same sample in space to check the properties of the sample. So this is the electrostatic levitation. This is the upper electrode and bottom electrode. And this is the principle behind it. This is the minus and this is plus. And we are charging the sample with a positive charge just because of the Coulombic force. And we are opposing a gravity, and sample will be levitated and it is suspended in between, so there is no container at all. We can reach up to high temperature and there will be no contamination. So this instrument is already launched to International Space Station. We are conducting experiment, and we are probably this year also we are going to conduct some of the experiment, and we are waiting for the results. And with this idea, we are going to explore new materials like oxide, ceramic, metal, semiconductors, and so on. And main objective is like to measurement of thermophysical properties like density, viscosity, and surface tension. And also, as I mentioned, we use sounding rocket where we can get a 6 minutes of zero gravity, and we use bismuth ferrites to see the effect of reduced gravity. This is the bismuth ferrite this is the microstructure what we observed from the sample we processed using a sounding rocket. And surprisingly, we saw that this is the TM image. This particle is nanoparticles is dispersed along the edge of the specimen, and the matrix diffraction pattern shows the coexistence of a hollow and spot, that indicating that material consisting of both crystalline and amorphous structure. So this is the preliminary result. So it indicates that we can also do some of the space experiment using a longer period, so that we can get good material. So with this, I will conclude my talk with these points. Containerless condition can be obtained by using some external forces like acoustic, gas, electromagnetic, and electrostatic levitation. This study can also be expanded to chemical science, physical and material science, fluid dynamic, medical science, and biological system as well. And in this topic, we have covered a new glasses with a high refractive index that is above 2.2. And this multiferroic materials with a remarkable stable phase was prepared from the undercooled barium titanate and nickel ferrites, and also a rare earth iron oxides. And these results suggest that the containerless process is a promising method to prepare the advanced materials. Thank you for your kind attention. And this is the acknowledges for funding agencies, CERB and DST, and Japan Space Center, and also Vijnana Bhavan, University of Mysore, India. So thank you for your kind attention. If you have any questions, I am happy to answer.
Yes. Any questions? Any questions to Dr. Vijay Kumar? Just if you have any questions or comments, you can share in chat box. We'll be asking behalf of them.
Yeah, sure. We
Yes,
can
sir.
do
Yes,
that.
sir. Even after the completion of the conference, you can share your questions. We'll be asking. We will be sharing officially through mail.
Yeah, sure.
Yes. Thank you. Thank you very much, sir. I think there are no questions.
Yeah, thank you very much. Thanks for giving me an opportunity.
Yes, thank you very much, sir, for participating in this event.
Thanks a lot.
On behalf of organizing committee member of Material Science and Nanotechnology 2021, we want to thank you for instant presentation. Looking forward to you next time, sir. If in a physical event, if everything goes well in 2022.
Yeah, sure. I will be available. I'm happy to be.
Yes, we are planning in Asia Pacific region, especially in Dubai, sir. If everything goes well, we will plan in the month of April 2022.
Sure. I will be happy to be a part of that.
Yes, thank you very much, sir.
Thanks a lot.
Yeah, have a nice day. Bye. Next, we welcome Dr. Anil Ramdas Bahari from Kavetri Bahinbhai Chowdhury, North Maharashtra University from India to start the presentation. Sir.
Thank you, sir.
Yes, sir. So we have a lot of time. You can take your own time.
Okay. 1 minute. I will share my screen.
Yes.
Can screen is visible, sir?
No, sir. Just you start sharing.
Hello, I'm Professor Muhammad Safwan. What time is my presentation?
Hello.
Yeah, hello.
Just to be online, sir.
Yes, sir. The screen is visible.
No, not yet, sir. So you can find in the bottom share screen with a green color. You can start sharing, sir. Yes. So I think Dr. Mohammed Supan. So, shall we go with the other speaker, sir?
Now it's visible.
No, sir. The other speaker, Dr. Mohammed Sopan, has started presenting.
Better to go ahead with this.
My presentation is supposed to be up to 4 minutes.
Yes, sir. We do understand. Just to be online.
Can I present now or what time? Shall I wait for 4 minutes?
Actually, we have announced to Dr. Anil Kumar, sir. That's why we are waiting.
What happened?
We have announced to Dr. Anil Kumar. So he's
Oh,
going to start.
not my turn now.
Just you can start. You will be inviting after this talk. Just to be online for 30 minutes, more 30 minutes.
Oh, I think it's delay, yeah?
No, not yet, sir. Not yet, sir. We are running
No.
according to
No.
the program.
And no,
My-
according to the program, this Mohammed is he has to present at 11:40.
Yeah, now it's 11:40, right?
Yeah,
Yes,
you can
almost
go,
11:40.
I think you can go ahead with this presentation. Maybe
Yes,
we
you can start. You can start, sir. You can
Okay,
start.
thank you so much. Thank you, ladies and gentlemen.
Hello, sir.
Yeah, hello. Yes.
Problem. Hello. Can
Yeah,
I share
hello.
my presentation?
No, I thought it's my time now.
Yes, you can start your presentation, sir.
Thank you so much. Okay, very good afternoon.
Yes.
Ladies
Just
and
meanwhile,
gentlemen.
just be online. So just meanwhile, I invite you. Please
Thank you.
apologize. Yes, please apologize. There was a mistake. Now we invite Dr. SM Sapun from University of Putra, Malaysia. The title of the talk will be the preparation and characterization of arrowroot from Maranta, Arodinian Fibrio renifused biopolar composites. He is going to join this conference as one of the keynote speakers for this conference. Yes, sir. You can start your presentation.
Thank you. My name is Professor SM Sapwan. The title, as mentioned by the Mr. Chairman, on the arrowroot composite. Yeah, okay. My lecture will be focusing on introduction, arrowroot biopolymers, arrowroot biocomposite, biopackaging application, and conclusion and reference. Okay, I will introduce first my university, UPM, UC Putra, Malaysia. It was an agriculture university, a leading university in agriculture in Malaysia for undergraduate and postgraduate, particularly in agricultural science. So we are working toward excellence in agriculture. It has become the legacy for our university, to be, in forefront of agriculture. And the focus of this lecture is on biocomposite. Biocomposite in Malaysia is very important research area where we have polymers and composite from plant-based. So in the recent year, research on bio-based polymer has become very important, and work on method selection, design, and still limited. And we focused on the tropical fiber and tropical, the starch for biopolymer. Yeah. Yes, sorry.
Yes, sir, you can go ahead.
I'm working on that. I cannot move. Oh no.
Now, place your cursor on the screen. You can.
Yeah, yeah. Okay, I will do it normal. I mean, without. I don't know what to do now. I try to escape. Yeah. Okay, I will do on this mode. Okay. When we see this picture, there are that seagull with the stomach full of plastic, and also the plastic bag become the threat for the sea creatures like the turtles. That's why we have to make effort to eliminate those, to reduce the use of the plastic bag. As you can see in this whale in Thailand, it was dead because of that swallowing so many plastic bag. And we see also here, the mountain pile of plastic bag. You can see, even on land, like it cause land pollution, it's cause problem to the marine life. And this all done because of, and it's causing also depletion of fossil fuel. So that's why we need a kind of alternative. So by having green polymer and green material and green composite, basically, the biopolymer composite has a biodegradable, it's a made from biodegradable polymer, renewables, available, easily and environmentally friendly. And however, it suffers from some disadvantages like poor water sensitivity and poor mechanical strength. And to overcome this, we can use blending, chemical modification, grapho polymerization, and we can incorporate pillars such as lignin, clay, cellulose. In our case, for the purpose of this today's presentation, arrowroot fiber and multi-wall carbon nanotube. So many ways to improve the strength and the mechanical properties. And the plastic, normally from biodegradable plant-based is safe, environmentally friendly, renewable, and it is a sustainable resource. I would like to classify briefly three types of bioplastic, biopolymer. One is we get it 100% from plant, like in our case here, PLA, and also we can get from the biopolymer from biodegradable petroleum based, like PBS, and petroleum polymer from mixed source like bio and petro, biomaterial and petroleum based, like PPT, polyester, and bio-based epoxy. And one of the focus of our research today is on the starch-based biopolymer. And a native starch contains about 70 to 85% amylopectin and 30% amylose. And we use plasticizer like glycerol, water, and sorbitol to help increase the free volume. And we call it thermoplastic starch. So this is going to be the topic of our talk today. And the second part is on natural fiber, because we have natural fiber plus in a biopolymer to become 100% biopolymer composite. Fiber which grow or develop come from natural resources like plant and animals. Obviously, there are pro and con of using natural fiber and also synthetic fiber. For example, synthetic fiber, they are used a lot. However, environmental and health problem become the issue. That's why we resort for natural fiber. And see, it is more comparison, like in terms of density, cost, renewability, recyclability, distribution, disposal, and health issue. And basically, as far as these criteria are concerned, natural fiber are a lot better. Even in terms of cost, you see, when you see the comparison of the price on the right hand side, natural fiber is much cheaper than glass fiber. So this is a very good thing. And these are the traditional use, for broom, sofa, handbag, mat, shoes. But this is not the one that we at our university looking for. And we want to go for, higher end of application. As we can see, pineapple is one of the natural fiber we have. And it is, has the properties, the strength is quite comparable to flax, even higher than flax, which we can find a lot in the West. Similarly, the tensile modulus, it is 82, higher than flax. So that's why we thought the tropical fiber got a lot of potential, and they are normally used in the form of, like a different part of plant, like wood, non-wood, and from straw, bast, leaf. For example, we can get from cocoa and also from the empty fruit bunch of the oil palm, and you can get it from kenaf, and you can get it from banana, even banana stem, date palm. So various sources. Okay, in Malaysia, we have predominantly kenaf, and from kenaf plant, we can get the fiber, and we have done a lot of research and published books on kenaf, as well as oil palm. We are one of the main exporters of the world. Even India now, they're importing the oil palm palm oil from Malaysia. So we have good source. So that's why we can have good fiber from that. And similarly, with this is sugar palm, very uncommon work or plant that's producing the fiber. In India, they call it gumoti. In Malaysia, we call it ijo. It's a good source of plant. We publish the work on that as well. And similarly for the, roselle. So last month we published this book with the academic press, where we can get even from the fruits, we can make juice and we can make like a chutney, etc. But we can have a good fiber from the trunk and and we can get fiber and to become the product. So natural fiber composite is the topic of my lecture. As we know that the fiber is from natural fiber, but the polymer could be from synthetic polymer, thermoset or thermoplastic. But we can also focus on the biopolymer, like today is from the arrowroot plant. Okay, the advantage of composite from natural fiber: non-abrasive, low cost, abundantly available, sustainable, high specific properties, low density, flexible, and recyclable. And before I go into the topic proper, I want to review some work that we have done at UPM on biocomposite product. Here is a plates from kenaf, and this is a flooring from kenaf composite. And recent work of us from the frame from kenaf composite, the certificate frame, for the pictures frame. So we developed this and we commercialized this, and we can also have like chair and table. In this case, we use kenaf composite with some thermoplastic polymer, and this is we carried out manually the banana pseudo stem fiber we do in the woven form with the epoxy. This is hand laid up, and this is also one of the product that we developed from sugar palm fiber to form the tables. This is also the work that we carried out on the solar modules for the solar panels. One of the layer is made from the sugar palm fiber composite. And because I don't have time to go into detail, but it has got very good properties and then performance, in service. So we also developed, we got some grant from Sam Dhabi to develop the safety helmet for the plantation workers, from the oil palm itself, from the fiber from oil palm, because the Sam Dhabi has got a lot of oil palm fiber. So to make this kind of helmets, for the plantation workers. So the market is huge because we have so many workers here in Malaysia and in our neighboring country, Indonesia. And in the past, we also worked with the Proton, our national car, to develop the packaging tray from oil palm from kenaf composite. And this is also another product, kenaf used as a window regulator in car. And this is very recent work. We work for the automotive door handle from hybrid sugar palm and kenaf composite. So this is very recent work. And in the past, we worked with the gumoti or sugar palm fiber in the producing boats. So this is among of the product that we developed. So now, because I still have time, so I will talk about the arrowroot fiber starch biopolymer composite. So arrowroot is I think it's not very common in many countries. That's why it becomes something new, and we can easily publish and accept it in the market in the journal. So these are how the plant looks like. It is that we can find in Malaysia and Indonesia. But the one that is produced in China, they are big. They are different. The tuber is very big, huge. But this one is long, slender. This is the plant, and this is the leaf and also the plant, and you can see the root also. The source of starch and starch of fiber is taken from the bottom part that is immersed in on the soil, in the earth. And you can see on the right hand side, we have the fiber made from husk, and also from inside there is some kind of bagasse that we can use for fiber, as well as the starch we take from the tuber. Okay, similar to other starch arrowroot, but the plastic bag, like in arrowroot, the plastic bag from this product are brittle, sensitive to water, hindering their application as good packaging. This is known. That's why we have to use plasticizer, such as glycerol, sorbitols, water, so that they can, improve the mechanical as well as water barrier properties. Arrowroot starch has excellent characteristics such as digestibility, gelling ability, as well as having the highest amylose content, which is 40%. Yeah, even you compare to corn, which is what 33%. Wheat starch 32%, potato 20%, cassava 19%, which are necessary to produce film. So arrowroot the starch composite is expected to aid in addressing the environmental issue regarding the alternative material for petroleum-based polymer. One of the solution. So in our work, we carried out the work to investigate the effect of glycerol concentration on properties of the starch itself, the film made from starch, biopolymer film made from starch. So we use the glycerol as plasticizer. The second part is to characterize the fibers from bagasse and husk of the arrowroot tuber, and to explore their potential. We carried out detailed experimental work on that. And then we make composite. AF means arrowroot fiber, AS means arrowroot starch, to form a composite. At different loading, we determine the thermal, mechanical, and physical properties, as well as morphological, antimicrobial, and biodegradability properties at different loading. This is our work now. Okay, the starch. The first part is starch. The extraction of starch with a yield of 8 to 16% on dry basis. This is what we got. The high amylose content, as I mentioned, 40% of arrowroot starch could allow its application in production of film with good mechanical and barrier properties. And the packaging is playing a key role to maintain food quality and to regulate interaction between environment and food. So this is a good advantage of this plant, but I think mainly this plant obtained in Malaysia and in Indonesia and in some part of China. So our work at University Putra Malaysia is really combining bioplastic, which is a arrowroot biopolymer from starch, with natural fiber, even from arrowroot, which is from the bagasse, as well as from the peel, to form bioplastic composite, or we call it biopolymer composite. Okay, briefly on the starch fabrication. See, this is how the plant looks like. We call it Maranta arundinacea. And how to produce the starch? First, the fresh rhizome from the tuber. We grind it, we pulp it, we add water, we mix them, we filter them, and we got fibrous residue. And we can go ahead and settling the filtrate, decanting, meaning remove all the dirt, and drying and refining the starch. Finally, we got the starch. This is the flow diagram of starch extraction of the arrowroot rhizomes. And if you can see here, this is the tubers on the right hand side. Initially, we cut. Then we use normal blender to extract the starch, and then we do some kind of separation, using a filter between fiber and starch, and then the starch are allowed to settle. This is how you get the starch. Then we add, of course, the plasticizer to form the starch biopolymer. As far as the fiber is concerned, so we have the wetted. Sorry, I think this is a mistake. I placed it wrongly. I think it should be the next slide. Anyway, this is still under starch. Yeah? Wetted starch, and there is a dry starch and wetted fiber. So we can see now, we can see the separation between the starch and fiber. And then this is the real fiber. Okay, we got the fiber from arrowroots, and then from arrowroot bagasse, and also from arrowroot husk, the field in the chilna. And then we pulverize it, and then we can have bagasse fiber as well as the arrowroot husk fiber, two types. This is why in our study we want to compare the performance between these two types of fiber. This is the chart for producing biopolymer. And we have arrowroot starch, and then we use the distilled water we add, and then the gelatinization process took place. We add glycerol at 3 different percentage, and we form the film solution and airflow oven, and then arrowroot starch film with 30% glycerol become our end product. Then we categorize that in terms of physicals, water barrier, tensile, strength, scanning electron microscopy, the TGA, and then also differential scanning calorimetry and soil bureau study. So we managed to do that, and this is the final product, arrowroot starch-based biopolymer developed using different glycerol concentration. And this is some, the study that we perform to compare the performance when we have different type of glycerol, different percentage of glycerol, and with control, and we find that the degradation is better with a higher percentage of the glycerol. And this is the mechanical properties. We can see that the tensile strength and modulus, they are inferior compared to the control when we add some kind of more the glycerol. So, and this is also the TGA DAC curve, and this is the SEM curve. The work we published in scientific report recently, and this is different work by other researchers. As a comparison, they just not doing the arrowroot starch biopolymer, but they also compare with blackberry powder, as well as the blend of blackberry and arrowroot carried out by Nogueira. So the meaning that the work of the arrowroot is not us in UPM only doing it. And also this is cranberry powder and arrowroot starch, and they blend it. And this is the paper that we published in scientific report by Nature, Springer, the Nature publication, the effect of glycerol plasticizer loading on physical, mechanical, thermal, and barrier properties of the arrowroot or Maranta arundinacea starch biopolymer. And earlier we published one recent one review paper we published in Q1 journal in Elsevier and then on the development of the arrowroot starch biopolymer, fiber, biopolymer composite, and their potential industrial application. And as we know, the work on arrowroot is not new per se, but the work on arrowroot composite is new. We are the first, investigators who carried out the research on arrowroot composite. Okay, biocomposite film from arrowroot fiber. The finding include we can enrich the knowledge in developing high performance biodegradable polymer derived from arrowroot starch blend, glycerol, arrowroot starch glycerol for food packaging, include the mix with glycerol for food packaging, and the characterization of arrowroot fiber from the arrowroot tubers, namely bagasse and husk, is expected to be explored their potential, to make the environmentally friendly composite film for food packaging. And the best ratio formulation, of glycerol plasticizer incorporated into arrowroot starch. Also, to form composite. Also, we have finalized it, and it expected to address the environmental issue, and also in terms of waste management. This work, can turn waste into wealth, and also the uncover the potential use of arrowroot starch and fiber, which normally people don't use it, but we try to make into the product like this. This is one of the experiment that we carried out, and this is how we make into the composite. And this is the final composite packaging. Hopefully, we can use in the for the food packaging like it's given in the picture. Okay, I think I almost finished. I think ahead of time, because I supposed to finish at 2:36 Malaysian time, which is about we got 7 minutes to go. So I think I want to review some of my recent book publication, maybe for the benefit of some of you who want to buy, you want to read, and because we have done a lot of work on tropical natural fiber composite and composite material. We published this book in 2014 on tropical natural fiber composite, which I wrote myself on the topic, which is related to this product, and the arrowroot. Arrowroot can be part of them. But during that time, we didn't start a research. We only start last year, and we published also on meta selection. We also publish work on neural network, and also the manufacturing process of polymer composite, natural fiber composite, and also the concurrent engineering aspect of polymer composite. And we published one with a Woodhead publication, Elsevier, meta selection for natural fiber composite. And we carried out the conceptual design and meta selection for natural fiber composite. And this is a series of books on green biocomposite. We published with Springer 4 years ago. And there's a reason of showing you can read this book, and you can enhance the knowledge of biocomposite, including the arrowroot. Like this is on natural fiber, focusing on vinyl ester and vinyl polymer. On the right-hand side, on the more on lignocellulose for bioeconomy. And this is focusing on another work on natural fiber composite as well as the sugar palm fiber. And this is for the application of biocomposite in biomedical, in the the implementation of the green material technology. And this is on biopolymer, biopolymer and biopolymer composite from the plant, for example, at PLA starch biopolymer. And this is more on the use of biocomposite in car and design for sustainability. And this is recent work on advanced composite in aerospace engineering. It's involved also biocomposite. And the right-hand side, hole making and drilling for composite, mainly on manufacturing of composite, including biocomposite. And this is the book that we wrote on the bio-based packaging. And this one is on the ballastic solution for composite, and as well as nanocellulose and nanocomposite, which is really involving the biopolymer composite. And this is another work that is going to be published soon on recycling of plastic composite, and another work locally published in natural fiber composite. And this is on safety of composite, as well as the mineral field composite, a series of books. So, ladies and gentlemen, because I'm really ahead of time, I got 4 minutes to go. So I'm very comfortable with timing. So conclusion, a lot of scope of research in bioplastic and biopolymer. Yes, definitely. And the application of bioplastic are huge, such as in food packaging and biomedical engineering, as I mentioned, but you can also find in aerospace, that we publish a book on that, can be in the defense industries, like in ballistic impact, and also in the automotive. We also published one book on that, with different and even now we are working on 3D printing, additive manufacturing of biocomposite, and the sandwich structure of composite. And we can combine biopolymer and natural fiber to form fully bio-based polymer composite suitable for many applications. For in this particular case is for the food packaging. And so we take the plant, arrowroot plant, which have good starch, amylose content, and also fiber source to form biopolymer composite for food packaging. Ladies and gentlemen, I would like to thank my university, University Putra Malaysia, for the research support, especially my PhD student, Mr. Tariq Jamil, in helping me to prepare this PowerPoint slide, and also to carry out the research work. And also from the University of Jember in Indonesia, one of the staff, they're giving me the idea to embark research on arrowroot fiber and composite. With that, ladies and gentlemen, I'm so happy that I am 3 minutes ahead of time. I would like to thank you for your attention. Thank you so much.
Yes, sir. We have a lot of time, sir. Thank you. Thank you very much.
Nandri, Ramba Nandri.
Yes. Yes. Any questions? Any questions to Dr. SM Sapuna.
Any question?
Any questions? Just if you have any questions, you can text in chat box. We'll be asking you behalf of you. Even after the completion of the conference.
Yeah, you can always contact me. You can always, ask the, the organizer to get my email address and to
Yes, we do have your email ID.
ask question.
Yes.
Thank you so much.
Yes. Thank you.
I think you understand.
Yes.
Okay,
I do.
I think my PowerPoint is no longer there.
Yes.
Okay, thank you.
Thank you very much, sir, for participating in this event. On behalf of organizing, yes, on behalf of organizing committee members of Material Science and Nanotechnology 21, we want to thank you for instant presentation. Looking forward to meet you next time in physical event.
Thank you.
Yes.
Welcome.
Yes. Thank you so much for joining and for your attention.
Yes.
Yes. Have a nice day.
Have a nice day.
Yeah, nice. Next, we invite Dr. Anil Ramdas Bahari from Kaviyatri Bahin Bhai Chaudhary, North Maharashtra University from India to start the presentation.
Thank you very much, sir.
Yes,
my screen is visible.
Just to be online, sir. I'm going to check.
Okay. Whether is it okay?
Yes, it's fine, sir.
Okay. Sorry for inconvenience faced during the technical problem. Now,
no problem, sir.
Okay. I'm very much thankful to the organizer for providing me to speak in front of you. Now, my topic of today's presentation is nano platinum modified zinc oxide as a DMMP sensor. Myself, Dr. Anil Ramdas Bari, that head and assistant professor from Department of Physics, Arts, Commerce and Science College, Bodwad. This college is affiliated to the Kaviyatri Bahinabai Chaudhary North Maharashtra University, Jalgaon, Maharashtra, India. Now, the outline of my presentation is introduction, preparation of that nanostructure zinc oxide powder, characterizations, fabrication of the thick film sensors, and preparation of platinum modified zinc oxide thick film sensors and its sensing performance, and finally the conclusion one. The introduction include, the general introduction is that we know that the highly toxic chemical warfare agents, that is in 1915, the chemical war occurred during the World War I. In that World War, the German forces released the 160 tons of the chlorine gas and killed 5,000 soldiers. In 1915 to 1918, World War I, German and British forces used 11,300 tons of chlorine, mustard gas and phosgene that killed 92,000 to 1 million people. In 1925, Geneva Protocol banned the using of chemical war as well as biological war, initially signed by these 38 nations. Now over 130 nations have signed this Geneva Protocol. But after that protocol signing, then 1913 to 1940, World War II didn't use that biological or chemical war, but the Germans developed the chemical nerve agents, that is sarin, tabun, soman, for that chemical wars. In 1970, during the Vietnam Wars, US used the defoliantants. Then in 1995, sarin gas released into the Tokyo subway system that killed the 12 people and injured over 5,500 people in 6 stations. In 2001 to 2010, anthrax in New York, pesticides in China, chlorine in Afghanistan that killed 250 to 3,000 was injured. And 2012 to 2015, rat poisons, pesticides, multiple chemical agents, sarin, mustard gas, and chlorine in the Afghanistan, Syria, in Iraq that killed 4,500 and injured near about that peoples. So we see that how toxic these chemical warfare agents. Now we can see what do you mean by chemical warfare agents? That any chemical which through its chemical effects on the living process that may cause the death, temporary loss of the performance of the permanent or permanent injury to the people and animal. So these chemical warfares are, or the agents are liquid, aerosol or vapor. It is highly toxic, not too difficult to handle, capable of being stored after a long period in the container without a degradation and corroding, resistance to the atmospheric water and oxygen, and it withstand the heat developed when it is dispersed. So the chemical warfare agents can be classified into nerve agents, choking agents, blister agents, psychotoxin protein, and industrial toxic agents. That includes tabun, sarin, soman, then chlorophlenic, chloric, phosgene, diphosgene, and other chemicals that include in that 4 classes. We are not going to discuss in detail. So we discuss about what do you mean by choking agents. The choking agents can be enter to our human body due to the inhalation. It can produce the burning of the nose and mouth with rhinothoria, the respiratory districts with the coughing fits and weakness to the headache also. While the nerve agents attack the nervous system by affecting the transmission of that impulses.
Hello.
Its routes of
Hi.
entry. Its
Hi,
routes
sorry
of
to disturb. Hello.
Okay.
Yes, yes, sir.
Actually, I can hear the 2 times, okay? What is that?
Just I think there's a problem in YouTube, sir. Just switch off from any YouTube.
Hello?
Can I continue?
Yes, sir. You can go. You can go.
Okay, so the nerve agents can produce the symptoms like increase the production of saliva, it increase the runny nose, feeling the of pressure on the chest. Then the blister agents. The blister agents is also called as vesicants. The routes of entry of these blister agents is readily absorbed by all parts of the body. It produces the general destruction of the tissues, inflammations, and blisters. You can see the photograph of the inflammations and blisters that are on the screen of the human due to the absorb of that blister agents. So these are some inflammations and blisters on the screens. Now, during these chemical wars, we can see some of the chemical wars in the atmosphere. Such type of troops are required during the operation, and this is some of the actual photographs of that troop where during the operation while leakage of that chemical warfare agents. Now, in the simulants of the chemical warfare agents we can use in the present investigation, because we cannot use directly chemical warfare because it is a restriction or it have a permission. So we have tested the simulant, that is the simulant of the serine simulant is dimethyl methyl phosphonate, while we can use the simulant of distilled mustard, that is 2-chloroethyl sulfide and 2-chlorophenyl sulfide, that is CEPS and CEES for the present investigation. Now, what are the effects that these gases or these chemical wars can produce? The global warming, ozone layer depletion, acid rain, health problem, chemical wars, and damage this environmental property. So it is necessary to detect and control these hazardous gases in the atmosphere. So for this purpose, the semiconductor metal oxides were used. For example, zinc oxide, tin oxide, tungsten oxide, titanium oxide, number of metal oxides were used for the gas sensor material. So one aspect is to use the prepared nanostructure semiconductor by using this ultrasonic atomization, or we can say that ultrasonic spray paralysis technique, and by using dipping to enhance the gas sensing property of that oxide material. So why these gas sensors are needed? It is to detect and control the pollutants in the environmental in the form of gas or moisture, to minimize the health hazards, to avoid the hazards of the global warming, and to avoid the chlorous episodes. So the sensor, what is the sensor? The sensor is a device that receives a signal, or we can say that the similar, and responds with an electrical or electronics or optical signals. The sensors were used in environmental protection and pollution control unit, office automation, industrial controls and atomization, vehicular exhaust detection, then security alarms, industries, bank and houses. The sensors technology we can use as a thin film technology, that is for the different thin film preparation techniques. Then screen printing technique is called as thick film technology, and third one is pellets. It is required to dye hydraulic press and the material at which the pellets to be made. So in the present investigation, we can use the simple screen printing technique to prepare the thick film sensors. So material, that is the sensing material we can choose as a zinc oxide, that is You can see in the left side the crystal and surface structure of that zinc oxide, and in the right corner we can see the properties of that zinc oxides. Now the experimental. This is the ultrasonic atomization technique. The upper part you can see the actual photograph of that ultrasonic atomization technique, and in lower part we can see the schematic diagram. This ultrasonic atomization technique is inbuilt in our laboratory, which is situated at Pratap College, Amalner, where I have did my all the research there. So you can see there is an ultrasonic atomizer. This is a liquid tank, and then number of trapping system. So we can prepare the appropriate molarity of the solution were prepared and filled into that liquid tank. This liquid tank slowly delivered the solution into the fine mist solution onto that ultrasonic generator. That generator consists of 3 piezoelectric transducer. This piezoelectric transducer convert the solution into that fine mist. This mist can be pushed forward with the help of cylinder. We can say that air as well as oxygen as a carrier gas, and put in the 2-zone furnace. There is a 2-zone furnace. We can see that the first zone temperature is to remove the water from that mist. So the temperature is maintained about 150 degrees centigrade, and the second then to convert that solution into the to convert the fine mist into that oxide nanoparticle. So the temperature is maintained at 1000 degrees centigrade. So in the first temperature zone, there should be the 150 degree, and in the second zone 1000 degrees there. So that converted fine mist into that zinc oxide nanopowder can be collected in the different number of traps. There are 1, 2, 3, 4 traps. We can see that trap can be sort. The nanoparticle that is heavier side can be reside in the first trap, then the lighter one in the next trap, then the lighter one is in the next trap, and then the lighter in the next trap. So size wise sorting can be done in this trapping system. So it is a naval trapping system which can sort the nanoparticle by their sizes. Now by preparing this powder, we can collect it and dry it into the IR lamp. After the drying, we can use the simple screen printing technique to prepare the thick film sensor by using this screen printing technique. We are not going to discuss this thick film technique. Then the sensors, the number of sensors we can prepare in our laboratory. So in the present investigation, this is a right corner sensor we can use to testing the simulant of the chemical warfare agents. Now, the pure material, that is a pure zinc oxide thick film, can be surface modified by using the platinum. So for this purpose, 0.001 m aqueous solution of the chloroplatinic acid was prepared in the double distilled water. Then the platinum modified nanocrystalline zinc oxide thick films were obtained by dipping them into the 0.001 molarity of aqueous solution of chloroplatinic acid for the different time interval. We can say that the dipping time interval of 1, 2, 3, 4, 5, 10, 15, 20, and 30 minutes, referred to as a sample 1, 2, 3, etc. Then these films were dried at 80 degrees under the IR lamp. These surface modified films were termed as the platinum modified zinc oxide thick films. Then as prepared, the nanostructure platinum xenon thick film samples were annealed at 500 degrees centigrade for half an hour to remove the moisture of that samples. Then we can use the 1, 2, 3, 4, and 5 minute dipping for our sensing performance to detect the simulant of highly toxic chemical warfare agents. So for this purpose, the indigenous sensing system, we can see the left side photograph of that sensing system, and in the right side we can see the schematic diagram. So this sensing system where we can use that consists of heater, gas inlet, sensor mounting, insulator, temperature indicator, and the chamber is there. Then we have measure the response, selectivity, response time, and recovery time of that sensors. For the simulant's response is defined as the ratio of the change in conductance of the sensor on the exposure of the target simulant to the original conductance in the air as given by the following relation, that is S is equal to Ig minus Ia divided by Ia, where Ig is the conductance of the sensor on air and Ia is the conductance of the sensor in the target gas, or we can say that simulant is there. Then the selectivity is defined as the ability of the sensor to respond to the certain gas, or we can say that simulant in the presence of that simulant, while the response time is the time taken for the sensor to attain the 90% of the maximum increase in the conductance of the exposure of the target simulant is known as that response time, and the time taken by the sensor to get back 90% of the maximum conductance when the flow of the simulant is switched off is known as the recovery time. Now we can see the actual graph. Now there should be the characterization. We can characterize this thick film by using the X-ray diffractogram. The X-ray diffractogram of 10-minute dipping platinum modified film, you can see the observed peak are matching well with the JCPDS reported data of zinc oxide. No peak corresponding to the platinum was observed. It may be due to the very small atomic percent of disperse on that surface of that zinc oxide. Then these films were surface modified by using the field emission scanning electron microscopy. We can see the FESM of the pure 2-minute, 10-minute, and 30-minute samples of that zinc oxide, pure and platinum modified. So unmodified Zedano film consists of randomly distributed grains on the size and the shape of the distribution, while the modified films consisting of spherical particles of the platinum species distributed uniformly with the smaller size shape on the Zedano grains. So this is a surface morphology. Now elemental composition. We didn't observe the platinum on that X-ray XRD pattern, but we observed the platinum in the elemental composition of the study. So the atomic percentage of zinc and oxygen in each sample was observed to be near to a stoichiometric proportion. All the samples were observed to the oxygen deficient. Also the film dip in the platinum were observed to be more oxygen deficient than the pure Zedano films, while atomic percent of platinum goes on increasing and atomic percent of oxygen goes on decreasing with that dipping time. So we can see that for pure there should be the platinum is no observed there. Then for example M1, that is 1 minute, observed is for platinum should be 0.4, M2 that is 0.12, M3 0.17. So the platinum goes on increasing as the dipping time goes on increasing, we can say that. Now the pure nanostructure, the sensing performance, we can say that the simulant response with that operating time, you can see the figure that consists of operating temperature with the simulant response. We can test it the DMMP, CEES and CEPS. So the variation of the simulant response with operating temperature of that nanostructure zinc oxide pure thin film. So the most sensitive element is observed to be the DMMP. The concentration of that DMMP should be 2 ppm. Operating temperature is 450 degrees centigrade and giving the response of 4.31. Also, the next most sensitive simulant is CEES at a concentration of 2 ppm, but the temperature is different, that is 400 degrees centigrade, giving the minimum response of 2.95. So the same sensors could be used to detect the DMMP and CEPS just by tuning the temperature, corresponding temperature. So if we tune the temperature to 400 degrees centigrade, we give the response to CEES. If we tune the temperature to 450 degrees centigrade, it gives the response to DMMP. So temperature tuned sensor can be observed by using this pure or we can say that unmodified zinc oxide. And here is the selectivity of the DMP against CEES and CEPS as 450 degrees. If we compare the temperature at 450 degrees centigrade, the maximum response is 4.31 to DMP, 2.96 to CEES, and it is 0.5 CEES. Now the response and the recovery time. So the response and recovery time of zinc oxide near about 3, and recovery time is near about 7 seconds is there. Now the most important part is the modified film. How the modified film can be response to that DMMP, CEES, and CPS. So the most sensitive of that pure sample should be the DMP sensor. So we only discuss here about that DMP response. We minimize that CEES and CEES response. So by variation of that response with the operating temperature of modified zinc oxide thickenings. The most sensitive A simulant should be DMMP. Concentration is 2 pm. So concentration is same. The simulant is same, but that there is a difference of operating temperature. Pure sample shows at 450 degrees centigrade, while the modified sample lower that temperature, that is 300 degrees centigrade. And the maximum response of the DMMP, that is for pure, should be 435, while one minute dipping time shows 125, and the maximum response given to 2 minute dipping time, that is 243, and then for 3, 4, 5 it should be minimized at 17, 15, and 5. So 2 minute dipping of that platinum given maximum response to the DMMP as compared to the other gases. So the sensitivity should be increased, and temperature of that sample should be minimized or decreased by modified the pure sample by using this platinum is one. So this is a selectivity. You can say that the nanostructure films are therefore highly selective to DMMP as compared to CEES and CEPS is there. Also the DMMP response with the dipping time, we can say that as the dipping time grows, increases, that is for 0, that is pure sample provides 0.76, while one sample 1 minute dipping time provide 125, 2 minute dipping time produces 243, and then it is decreases. So maximum response were observed to the 243, that is for 2 minute dipping time, having the 0.12% of platinum on that zinc oxide is there. So this is a response and recovery time, that is the 15 seconds and 45 seconds the recovery time we can say. So this paper is published in the Journal of Sensor and Actuator B Chemical, that is detection of dimethyl methylphosphonate, a simulant of sarin, the highly toxic chemical warfare using the platinum activated nanocrystalline zinc oxide film. So that impact factor is 7.1. So summary, we can say that the ultrasonic atomization technique is used to prepare the nanostructured zinc oxide powder. This technique is simple, inexpensive, and may be used for the large production of that nanostructured metal oxide powder. XRD analysis confirmed the zinc oxide, while the average grain size was observed to be 20 nanometer. The pure, that is unmodified nanostructured genome, was observed to be more sensitive to DMP than CEEPS and CEPS at 450 degrees centigrade, while the response is given to 300 degrees centigrade of that platinum modified zinc oxide, that is higher as compared to the other one, and 10 minute 0.% were observed to be the most sensitive element to that zinc oxide DMMP. So 2 minute dipping was observed. So the sensor showed quick response and fast recovery to that sensor. So the pure and platinum modified nanostructure zinc oxide could be the promising candidate as a sensor for detecting the simulants and hence the chemical warfare agents. So I'm very much thankful to the University Grant Commission, the Department of Science and Technology and Information, and Defense Research Development Organization providing me the laboratory facility and other things. Also the head Department of Physics Principal Pratap College Ammaner for providing the laboratories, and my college, that is principal and staff of my college, Arts, Commerce and Science College, Bodwadi is there. These are some of the publications that were published in the Sensor Actuator B Chemical, Advanced Powder Technology, then Current Applied Physics, Sensor Optical B Chemical, Material Science and Engineering. So number of papers were published in the elsewhere journals. You can see. Thank you very much. If any questions.
Yes, sir. Any questions? Any questions to Dr. Anil Ramdas? Just if you have any questions, even after the completion of the conference, you can share your comments or questions so that we can ask behalf of you. Yes, thank you. Thank you very much, sir, for participating in this event.
Thank
As
you.
you know, yes, as you know, due to COVID problems, we are unable to organize physical events. If everything goes well in 2022, we are planning to get together all the professionals from the nanotechnology as well as material science professionals.
Okay, sir.
Definitely, sir.
Okay.
Now itself we invite you to join this event for upcoming 2020 event.
Okay, sir.
Yes, thank you very
Definitely.
much. Yes, thank you very much, sir, for joining and for your attention,
Okay, sir.
for sharing your valuable experience too in this online event. Thank you very much. Have a nice day.
Okay, sir. Very much thank you.
Yes, sir. Even after the completion of the conference, after 2 to 3 days of the completion of the conference, we'll be sharing your soft copy of the certificate as well as booklet through officially through your email ID, sir.
Okay, sir.
Thank you.
Welcome.
Thank you.
Welcome.
Yes. Next, we'll go with keynote
Hello,
speak.
hello. This is Shumona Ghosh, Dr. Shumona Ghosh. Actually, I have missed my presentation slot, which was before this
Hello.
presenter. So, may I start my presentation now?
You may I know your good name, madam. Just I can.
Hello.
My,
My title of presentation was heat resistance. So, myself is Shumona Ghosh.
actually, we are no, madam. What we are asking is, what is the name? What is your name?
Name is showing Karthika, but myself is Dr. Shumona Ghosh. My title is High Heat Resistant Animal Feeds for Application in Aero Engine Parts.
Your college, the textile application of Carbona Ghosh, just to be online, madam.
Just earlier.
Yes, we do.
Earlier.
Yes, I got it, madam. I got it.
Actually, I missed.
Actually, we are confused. Just you can rename. Just you can rename.
Name is showing Karthika.
Yes. We are a little bit confused.
She is my student. Actually, I am now. May I start?
So we'll go with the video presentation first. First keynote speakers, or else you can, if you wait for at least 25 minutes.
25 minutes.
Yes.
If you say, I can wait.
Okay. We'll go with your talks, madam. Better.
Now.
Yes. If you are ready, I'll be inviting you.
I am ready.
Yes.
I am sharing my screen.
Yes, madam.
Okay. It is showing host disable participant.
Just be around, madam. I'll be. Just we have made the co-host under the name Karthika. Yes, madam. Just we invite next Dr. Sumana Ghosh from CSIR from India. The topic will be high heat resistant enamel fluids for application in aero engine parts. You can start sharing your PPT, madam.
Okay, I'm starting. Can you see the slides? Hello?
No, madam.
No. Okay, I am trying again. One minute. Now?
Yes, madam.
Now it is okay?
Yes, madam. Fine.
Okay. I'm very grateful to the organizer for giving me the opportunity to attend this conference. Actually, it's a webinar on material science and nanotechnology. Myself is Dr. Shumona Ghosh. I am working in the bioceramics and coating division of CSIR, CGCRI, Kolkata, India. My title of topic is High Heat Resistant Enamel Fluids for Application in Aero Engine Parts. So let us first, we are all aware that what is coating, why it is applied on metal, It is well known that it gives the resistance to oxidation, resistance to corrosion, hot corrosion, resistance to abrasion, hot abrasion, and resistance to oil. So coating is necessary. We cannot ignore coating application on metal to use the metal at high temperature application. And here we use a special, very simple technique that is called enameling to prepare enamel coating on metallic substrate. Enamel means glass coating on metallic substrate. This process gives impervious coating and defect-free coating. It's very simple process, cost-effective technique, yield variety of properties. Why we will take glass and glass ceramics? Because glass and glass ceramics is a versatile material. It gives a range of properties starting from high strength, high impact resistant, low coefficient of thermal expansion, thermal shock resistant, high oxidation resistance, and high toughness. And there are numerous applications. Engineering component, insulator, household appliances, cookware, bakeware, biomedical, advanced optical. So here actually we follow a process that is called enameling technique, wherein we actually prepare glass crete by melt quenching method. And after preparation of glass crete, we prepare the glass slurry, which is nothing but glass powder mixed some suitable solvent in order to aid it to spray onto the metallic substrate. Later on, we fire the glass powder coated sample, and a glass impervious glassy coating is formed onto the metallic substrate. If required, then if we want glass ceramic coating, then again we do heat treatment of the glass coating, and finally we characterize both the glass and glass ceramic coating. So this the technique that is called enameling technique. It's a very simple and cost-effective technique. On the left side, you can see the typical picture of glass crete and the glass ceramic coated sample. Here, the CGCRI has developed several heat-resistant glass ceramic coating of different properties, which are applicable at different high elevated temperature. So I am showing you several heat-resistant glass ceramic coating, which is actually prepared from glass crete. That is called heat-resistant crete. So first of all, we have prepared the crete. Then we have to apply the glass or glass ceramic crete to metallic substrate. How? Using enameling technique. So here, barium oxide MgO SiO2 base coating I have shown the surface microstructure as well as cross-sectional microstructure. And below two picture, ACM picture shows MgO Al2O3 TiO2 base coating. Surface microstructure shows some crystalline phases are present into the glassy matrix, and the cross-sectional ACM picture shows the coating and the substrate and the interfacial region. Another glass ceramic coating which is actually heat resistant, which are applied on mnemonic alloy, and we always know that mnemonic alloy or nickel based super alloy is used as coating, used as substrate on gas turbine component. So to increase the gas turbine efficiency, we have to apply some heat resistant coating. Herein we have in our lab, we have developed heat resistant glass ceramic coating, which are very suitable for application on mnemonic alloy. Another ZNO L2 SiO2 base coating I have shown here, surface microstructure as well as cross-sectional image, which shows the presence of some crystalline phases, ulemide. So this type of crystalline phases are present in this glass ceramic coating. The below picture shows how the glass ceramic coated substrate look. That means two glass ceramic, different type of glass ceramic coated metallic substrate have been shown here. So the main two properties that are very essential for application of pneumonic alloy substrate, that is called oxidation and thermal resistance. So we have evaluated the oxidation resistance of these three types of glass ceramic coated substrate and the bare substrate in terms of heating it at 1000 degrees centigrade at different period of time. So you can see clearly from this graph that bare substrate shows a huge weight gain due to oxidative weight gain. And the all glass ceramic coated substrate shows the lower weight gain because it protects the substrate. So oxidation is very less here. And thermal endurance test we have also evaluated at 1050 degrees centigrade for 100 hours. So the left picture shows the original glass ceramic coated substrate, and the right hand picture shows the how it looks after 100-hour exposure at 1050 degrees centigrade. No other microstructural changes we have noted, and we have also examined the cross-sectional interfacial microstructure, and there is no reaction, substantial reaction product that has been formed at the interface, and the surface is quality also remains good. So we can tell that no such abrupt and no such significant changes has happened in this case. So we have also thought of using this BAO SiO2 based glass ceramic coating onto gamma titanium aluminide, which is also a high temperature structural material. Instead of nickel based superalloys, this gamma titanium aluminide also used for gas turbine and other heat engine component. But here the only drawback is this gamma titanium aluminide has a tendency for oxidation and hydrogen embrittlement. So we have provided the coating and we have evaluated the oxidation resistance and hydrogen permeation effect after the coating formation. So you can see clearly from the left hand side graph which shows the changes in weight in terms of weight, time of exposure at elevated temperature at 800 degrees centigrade. So bare substrate shows significant weight gain, and we have coated it several types of different types of coatings, and it gives different types of protection to the substrate. And also we have evaluated hydrogen permeation weight gain, and here we have seen that bare titanium aluminide that is green colored, which is change in weight is very significant after 70 hours exposure at 800 degrees centigrade, whereas the ABK13, ABK 103, that is two types of glass ceramic coated substrate that shows very less changes in weight in terms of exposure to at 800 degrees centigrade. The paper published I have mentioned in the below. So we have applied the same glass ceramic coating as a corrosion resistant glass ceramic coating, and we have evaluated whether it can resist the corrosion, it can resist the oxidation that has been established, but whether it is able to resist the corrosion, we have evaluated that. So we have actually investigated the kinetics of hot corrosion in terms of time as 1000 degrees centigrade. And we have taken two types of method. That is, one is immersion in molten salt, another is suspension salt vapor to evaluate its hot corrosion kinetics. And we have observed that immersion in molten salt, actually this gives little bit lower hot corrosion tendency to the substrate in comparison to the suspension in salt vapor. And the letter B and C do these two ACM micrograph shows the ACM micrograph, cross-sectional micrograph after immersion in molten salt, another is after immersion in suspension in salt vapor. Both ACM micrographs shows the interface is quite defect-free and it remains intact. No such abrupt change or significant change have been observed. So the next table shows the materials which people have ever used for ever to evaluate their material in terms of hot corrosion resistance at different temperature and time. And similarly, we have also evaluated our barium magnesium silicate glass coating in terms of exposure to 1000 degrees centigrade for 35 hour time duration. And we have seen very negligible mass loss per surface area, that is 6 mg per centimeter square, that we actually nearly we have observed in our case. And whether it is too high, 75 in case of titanium silicon carbide, titanium aluminum, it is 4 mg per centimeter square, and exposure temperature is also lower compared to other compared to us. So we can say that our coating material is quite suitable to provide the hot corrosion resistance. This slide shows the enamel coated component, our high temperature resistant enamel that we have developed here, CGABK13 and CGB55A. One is white color coating, another is green color coating. So after application of the coating onto the component, how it looks, you can see clearly from this slide. And the below picture shows gas turbine component coated by heat resistant enamel. So I can conclude that it was observed that enameling technique is a simple and cost-effective technique for preparing suitable enamel coating on metallic components. And enamel coating offers versatile properties. You can get, even if not only the oxidation hot corrosion resistance, you can get highly erosion resistance, wear resistant, highly hot abrasion resistant coating using the enameling technique. It gives a fantastic coating properties. And we have developed high heat resistant enamel fluid that are still being used by Hindustan Aeronautics Limited, HAL, which is a well-known industry of of India, for the production of a number of aero engines. They actually take our glass fluid or enamel fluid time to time for preparing different coating with different properties for their actual application. So we are very grateful to them for providing us the opportunity to prepare this type of heat resistant enamel sheet for them for actual engine, aero engine application. And very recently we have completed 3 types of project actually with them, HAL, and it was very successful. I must acknowledge our director CSIR CDCRI for providing me the opportunity to in carrying out this type of research, and she also supported our research very much, and also approached HAL to come in our institute and just collaborate with us. I must I am thankful to head HOD CSIR CDCRI and the head advanced material characterization unit for doing various types of characterization. Thank you very much for your kind attention. Thank you.
Yes, madam. Yes. Any questions? Any questions to Dr. Sumana Ghosh? Just if you have any questions, you can just comment in chat box. We'll be asking behalf of you. You can text here to so that we can ask behalf of you. Yes. Thank you. Thank you very much, madam, for participating in this event.
Okay, thank you.
Yes.
Thank you.
Yes. On behalf of organizing members of Material Science and Nanotechnology 2121, we want to thank you for your presentation. Thank you so much for joining and for your attention.
Okay. Thank you.
Yes. Next, we welcome Dr. Manish Dev Sharma from Punjab University from India to join the event and start presenting.
Sir, good afternoon.
Yes, sir.
Sir, good afternoon.
Yes, good afternoon, sir. Just you can start sharing your PPT.
Yeah. I am audible and visible.
Yeah, we are audible with your voice, sir. We are not audible to. We're not getting any PPT from the screen.
Is it audible and visible, sir?
We are audible, sir. We are getting your sound, but no PowerPoint on the screen.
Okay. Fan बंद कर. Is it visible? Screen
Yes, sir. Yes, sir. It's fine.
So can I make it full screen?
Yes, sir.
Now is it full
Yeah,
screen?
yeah, it's fine.
Thank you. So should I start now?
Yes, sir. You can go ahead.
Yes, a very good afternoon and warm welcome to the Material Science Conference. So myself, Dr. Manish Dev Sharma, I am working as faculty in Department of Physics, Punjab University, Chandigarh. Here we have a Material Science Research Group, where 3 to 4 faculty members are involved in different types of research related to materials, engineering applications, and other noble materials as well. So today we will discuss a novel material chalcogenide glasses. Those we can use for material engineering applications. It could be easily used for different medical purposes, scanning and detection, for phase change memories, and various other solid state device fabrications. So let's have a start point about it. So what is there inside my discussion? So here we have chalcogenides, like what are basically chalcogenides and their properties, so that we can have the respective applications for this. Then starting with the preparation of bulk material for these chalcogenide classes, synthesis of single index and double index chalcogenide fibers from the glass. There are various techniques and I will discuss one of them, that is rod and tube technique. And potential field for their applications like biomedical sensing, chalcogenide fibers, phase change memory applications, and finally I will conclude the whole concept in a single slide. So starting with its origin, what are chalcogenides? So chalcogenides are basically compounds. Those contain one or more chalcogen group members, that is group 16 members. You can say other than oxygen, the whole members are included. So starting with sulfur, selenium, beryllium. So reason for the popularity of these glasses is their versatile property, whether it is a optical property, electrical property, electrothermal properties, and their widespread application in the area of science and technology. The other important point about their publicity is phase transition. They can also behave in two phases, phase transition from crystalline to amorphous, and similarly from amorphous to crystalline. This property of these glasses is exploited to make the phase change memory devices. So along with their natural tendency to be transparent in the mid IR region, mid infrared region, hence we can use it for the purpose of application in the fibers. So you can say that there are different properties of chalcogenides with respect to their application area. So starting with this is the first one that we call as transition in mid IR and far IR ranges. So here we have spectral range of 3 to 15 micrometer wavelength. The other is higher refractive index. So means with the help of their property of higher refractive index, we can use them in optical lenses. So other is low phonon energy. For that, it helps us to form thermoelectric devices, means conversion of or measurement of thermal energy to, yes, electrical form for recording, for detection, or for the purpose of conversion. So softer and lower transition, softer and lower tension required means we can have the fabrication of the fiber in a simplified way. So lastly is low optical losses recorded in the case of photon theory. So we can say we have a reliable transmission of data through fibers. The other thing is ideal for mid IR and high power laser delivery, chemical sensing, imaging, memory applications, etc. So these are the important properties that we have exploited till date. There may be some other properties in upcoming area of research that the budding researchers may find more interesting property, more interesting change in the behavior that they can exploit in the area of research and technology. So it is a brief slide that explain how we people prepare bulk material for chalcogenide glasses in our laboratory at Punjab University, Chandigarh. So here we start elements in powdered form. We have the powdered form, and like powdered form means you have basic elements. You just find some novel material formula, or you study the different materials and their bonding. So you make them a powder form, then weight them and make a quartz ampule sealing of the materials so that we can put it in the furnace. Then we heat for 12 hours in anneal form. Then similarly, at the same time, after heating in the furnace, we just use a melt quenching technique. So melting is done for 12 hours and quenching is done in the ice chilled water. So the purpose to doing this is to avoid the formation of covalent bonds. Then we remove the bulk material. We usually call it as ingot. So ingot is powdered to obtain a bulk material. So again, we have the exact powdered chalcogenide glass material. So similarly, we have synthesis of single index chalcogenide fibers from the glass, means solid preform placed in the furnace. Then we have softening of glass due to heating. Then we have softening of the same into fibers of few meter length and diameter in micrometer range. So it again depends the area of application which will define that how you will make a synthesis, how technique you will adopt it for the synthesis, depending on the type of application area. So this is a technique that is called rod and tube technique, which is used for synthesis of double index chalcogenide fibers from the glass. So you can see the structure. Here we have core glasses, where first of all we do heating of the ampules, okay, separately. We have core glasses and cladding glass. Core glass is left hand side and cladding glass is right hand side. We heat both of them parallelly and then we go for cooling of the same. And for cladding glasses, we have fast spinning and cooling together. Then we have core rod post to the cooling process, and similarly we have cladding tube. Then we infuse them and the thing is called solid preform. So you can say there is a core which function as rod and there is tube which is function as cladding. So fiber is formed in the this sophisticated process, which is called core glass and cladding glass. And in combination, the process is called rod and tube technique. The purpose is to form a double indexed chalcogenide fiber. So similarly, we have synthesis of double indexed chalcogenide fibers from the glass. So this typical fabrication technique is shown with the help of this diagram, where we have inlet for cladding material. So like if you see the previous slide, we are fabricating both the things parallelly. But here we have inlet for cladding material first. So in situ, you can say the core cladding, the process of core cladding casting is better technique to fabricate the fiber, as core clad interference is better as compared to rod end technique. Actually, that process, the earlier one, can be designed inside the lab easily, but this technique need a specific setup to make the things in core cladding form. Here we have inlet for cladding and inlet for core. Both materials are again parallelly introduced in the setup, and we find that the core and cladding are parallelly deposited on each other, so that we can form the synthesis of double indexed chalcogenide fibers in the same way as we have done in the last. So this is a brief idea of the fabrication. Now we can see that there are different fields of application, like chalcogenide glasses are found with phase change memories, optical lenses and fibers, thermoelectric powers, optical fibers. So in case of optical fibers, we have the upcoming area of large detection in the medical field. We have sensing, we have laser delivery, we also have the area of telecommunication for mobile networking. If we are moving toward medical application or biomedical application, we have sensing area that is linked to temperature sensing, medical endoscopy, gas sensing, and pathogens and chemical sensing. So pathology is also a upcoming area in which the optical fibers, the chalcogenide fibers can deliver a lot. So starting with this biomedical sensing, we have tried to elaborate with the help of this small diagram. Here we are showing the method which is called fuse, that is called fiber wave equivalent spectroscopy. So this is basically sensing of biological traces inside the human body. In fuse, when light propagating in optical fiber is of same wavelength as that of surrounding medium, then fraction of light is absorbed by medium and attenuated signal is obtained at the output end of the fiber. So you can see that here in the diagram, the object under study receive an infrared light source, and the object also under the observation of detector, where detector is tracing the biological idea, and finally the data analysis and the spectrum is studied. So with the help of fuse, we can have the chalcogenide fibers which are transparent in IR range, and most of the biological species like humans, they emit radiation in this infrared region. So we can say that chalcogenide fibers are not only used as transmission medium but also function as sensing element for the same. So analyte is basically detecting the pattern generated with the help of IR source. The IR source could be a human being in this case. So fuse basically a latest technique that can be developed to make a touch-free sensing of the human body, touch-free, characterizing the various diseases inside the human body, especially in the era of pandemic, when there is a pandemic like coronavirus that can transmit from humans to others. So chalcogenide glass fibers are transparent in IR region, and most of the biospecies show characteristic emission in this region. So we can say that when wave travel inside these fibers, they interact with outside environment, and the output is analyzed to detection of biochemical species. So it also help us, like with the using of fuse, the early detection of diseases. There are a lot of literature available. I have also mentioned one of the example from Bureau et al. That used test material, that is tellurium, arsenic and selenium combination, and along with fuse technology for characterization of different organic molecules like proteins, RBCs and blood cells. So fuse spectra of the serum obtained from a human body with cirrhosis, that is showing red line, without cirrhosis showing the black line. So this is a elaborated application of chalcogenide fibers. Those are showing the normal state of humans and pathologic state of humans, where different wavelengths are elaborating the same at the different human species, inside the different human species. So the fuse in IR spectra of human body, fluid samples with and without cirrhosis was done, and these results are clearly showing the application of fuse, the application of chalcogenide fibers in medical detection and sensing. Similarly, we can also apply the same for our research with the help of clinical trials. This is showing the study of mice liver on the right hand side. The mice liver with and without tumorous tissues was studied to check metabolic abnormalities by a researcher doc, and results were graphically shown with the help of a tool, fuse spectra. Those are obtained from traditional method. So the diagram, there are two A and B. The A part shows spectral and current transmission spectra of mice liver. Similarly, fuse spectra of tumoral mice liver is also showing, and non-tumoral mice liver disease is shown with the help of solid lines. So dotted lines, dashed lines are basically, yes, the current line of mice liver. So both the plots are showing the elaborated way of the same with different advantages. So similarly, one of the researcher also helped for the detection of organic pollutants. So like TAS fiber used to detect organic pollutants in water using FTIR spectrometer and MCT detection by Michael and their research group. So these 2-3 applications elaborate that how fine we can use the fuse and in the area of medical detection and sensing. So along with this, we can also have chalcogenide fibers in the area of solid state physics. The chalcogenide fibers have property of phase transition from amorphous to crystalline and from crystalline to amorphous. So diagram is showing the crystalline structure is shifting to amorphous, and similarly at the time of applying the electric pulse. By again applying the electrical pulse, you can switch back to crystalline structure of the solids. So this whole process is elaborating the phase change memory cell working. The amorphous phase being the high resistance state and crystalline phase being the low resistance state. This property make them useful for the application of phase change memory, which is among the solid state memory applications. Here, the high resistance phase shows binary 0 and low resistance phase show binary 1. So you can say by choosing the 0 and 1, we have the binary flip-flop of two states 1 and 0. By this way, you can make the data store inside it and wash the data by making it reset by 0, 0. So these transition can be achieved by three different methods. Of course, thermally by applying pressure and by electric pulse. So in case of solid state memories, we only use electric pulse. It depends on what is the size of the memory, and of course, electric pulse method is the first preference to make the memory more frequent, more responding, and smaller in size. So there are other applications, those we can elaborate with the time. The upcoming research group may find chalcogenides more prominent, more useful in area of solid state memories, phase change memories, and medical detection and sensing. So finally, I conclude my presentation by 4 points. So chalcogenide glasses are amorphous semiconducting materials. Those are exhibiting versatile properties like electrical properties, optical properties, thermoelectric properties, and of course, vacuum properties or pressure properties. Chalcogenide glasses are one of the most promising candidate for future devices like sensing applications, memory storage applications, gratings, imaging, solar cell, which are owing to their adaptable properties. The above mentioned research work indicate that with the future advances in chalcogenide glasses material, these can have numerous commercial applications in the area of medical and electronics engineering. Along with the improved characteristics like thermal stability and even better data retention capacity, means storage, can open the door for their use in optical fiber communication, optical fiber sensing, biosensing, phase change memories, and various other electronic chalcogenide device applications in a successful way. So there are maybe some other application area where chalcogenide glasses can be exploited and explored to have a successful fabrication of materials and devices. So with this, I thank you all of you, and I thank you my Department of Physics, Punjab University, Chandigarh, for allowing me to conduct this research. I thank you my scholar, Sakshi Sani and Kritika, for developing this materials and developing this PPT. Thank you very much. Now the session is open for any query. Welcome.
Yes, sir. Yes. Any questions? If you have any questions, you can text in chat box. We'll be asking behalf of you, even after the completion of the conference.
Yes, I welcome all of you. I will post my visiting card inside this, so you can note down the details. If somebody wants to know the details or contact details, they can contact me over the details shown. Thank you very much.
Yes, yes. Thank you very much, sir, for participating in this event. On behalf of organizing member of Material Science and Nanotechnology 21, we want to thank you for excellent presentation. Thank you so much for joining and for your attention. Next, we welcome Dr.
Thank you, sir. Thanks a lot.
Yes. Thank you very much, sir. Have a nice day. Yeah. Next, we welcome Dr. Adrian Grabs from Poland. The title of the talk will be Inconial 625 NBC Metal Matrix Composite.
Hello, good morning to everyone, or good afternoon. At least it's morning in Poland. I will share my screen in a second. This is it. It should be visible. Is it?
Yes, sir. It's fine.
Yeah. So Once again, welcome, ladies and gentlemen. I'm Adrian Graboś from Faculty of Material Science and Ceramics at AGH University in Krakow, Poland. I have a pleasure of speaking to you today about Inconel 625 NBC metal matrix composites, which is the topic of my PhD dissertation at this moment. And it is a main focus of our next few years of studies in strict cooperation with Hokkaido University in Sapporo, Japan. Let's quickly see how this will be going for the next 15 or so minutes. First of all, I will present the Inconel 625 superalloy for you and what are the potential possibilities of making a metal matrix composites and why we do this, how we can improve this superalloy, what it is suited for, etc. Then we'll go to the materials and methods. So basically, I will outline you what was the synthesis method, what were the parameters, and how we did the basic analysis of the materials we've obtained. And then we'll talk about the results, the basic microstructure analysis to show what is the result of the synthesis, what are the phases we are getting there, possible interactions. And then we'll focus on both mechanical properties we've measured, hardness and tensile resistance. So we can evaluate for ourselves if this composite has any potential for improving industrial materials, parts of machines, and we'll make some conclusions. So first of all, Inconel 625 is, as probably many of you know, a superalloy based on nickel. It contains also chromium, molybdenum, niobium mostly, also with parts of titanium, silicon, and iron, depending on the manufacturer, of course. And it is, as a superalloy, able to work in a high fraction of its melting point. Therefore, it is used for such things as jet engines, as shown here, or waste to energy combustors. For us, it is much more interesting to work on mechanical development, such as turbines, whilst for Japanese part of this collaboration, the combustor of waste is much more important due to the quite a few problems with waste in Japan at this moment. And therefore, it was a very potential collaboration. Inconel is known for being very ductile. It is an easily weldable alloy. And this is combined with high resistance to erosion and corrosion, which is a very important combination of properties when we are talking about high temperature applications, which we are aiming for at this moment. However, due to the still advancing industries, like faster airplanes, more how can I say, more advanced solutions, mechanical properties have to be still improved to meet those requirements, which are very important for future collaborations, for future products. Therefore, many ceramic materials, including niobium carbide, NBC here, are employed to increase those properties, because ceramics, as is widely known, is very hard, potentially tensile resistance due to the high Young modulus, and so on. Therefore, such composites are being synthesized, and this is one of them. Other metal matrix composites based on carbides include titanium carbide, tungsten carbide, and you can also read about such materials in our previous works. However, they were those materials that we obtained, namely with tungsten carbide, were full of TCP phases, topologically closed packed, which were not very good for Inconel 625 alloys. And therefore, we thought that it is possible that with employing niobium carbide, we can reduce highly this amount, which was proven to be true, as you'll see in a moment. And that's why NBC was utilized. For our process, we've taken powders of Inconel 625 and powders of niobium carbide. Then we employed the homogenization of powders in ball mill using steel milling media for 24 hours. It was a dry milling, very simple and very easy to perform at any university or laboratory. Then with such prepared powders, we've performed the spark plasma sintering at almost 1200 degrees C under the load of 45 megapascals. Then such a cylinder was mechanically prepared for hot rolling. Here it is stated the first stage of hot rolling. It is the only one hot rolling we've performed for this experiment. This is a mistake, a typo. It was performed at the same temperature with 10% reduction per step up to about 3-4 millimeters of final thickness, just to achieve some basic bars of metal. Then such materials was both observed microstructurally and mechanically tested. And then just to see how much further we can go with interactions of different phases, we've performed an annealing at 12 degrees C in argon atmosphere to prevent alloy from reacting with oxygen. And then the same analysis was performed. Now, microstructure analysis was performed by a combination of scanning electron microscopy and EDS to both observe microstructure and see the phase composition present there. Hardness tests were conducted by Vickers indenters. Therefore, in such scale, the hardness will be presented later on. Now, powder's composition is visible here. Initially, we've seen the powder site distribution of niobium carbide. It was measured by the ELS method, laser method, fractional. We can see that there are two maximums here of particle size, one of smaller grains around 0.1 to 1 micrometer and a bit bigger fraction. It was 99.9% of purity NBC, very good for sample synthesis, analysis. Our Inconel 625 powder from Japan had element composition that is visible below. There is 23% of chromium here. It is a bit small on titan presence, and molybdenum was up to 10%. There is a small fraction of niobium in Inconel 625 powders. Therefore, it is very interesting how niobium carbide will react with such matrix, because when titanium carbide or tungsten carbide is involved, there is additional reaction to this. Additional phases can occur, TCP phases, as I mentioned. Here, there is a strong possibility that this will not happen because niobium is naturally in Inconel 625, and moreover, it is important for creating gamma double prime phases. Our sample composition was created to see how much of a different niobium content will impact the metal matrix composite that is obtained. It was from 0 to 30%, 0 for reference, then 5, 10, 20, and 30%. Now, 30% of NBC was very hard to sinter. The amount of NBC was too high, and the samples were losing their composition, and therefore they are not present in future analysis because we were unable to do it. Spark plasma sintering, as you can see, was a very interesting process. In a graphite die, we've put powder in 3 layers of isolation to prevent from reaction with graphite, to get a good temperature flow going there. We have a nickel plate at the very contact of powders. This created a cylinder later on in which metal matrix composite was present. This was put in aluminum oxide fabric and then in carbon sheet. Graphite punches were on top and the bottom, as in all spark plasma sintering processes. It is a very interesting process, and it was put under the load of 45 megapascals, just to apply both pressure and temperature and make a synthesis. This was done in the atmosphere of medium vacuum, as you can see, to, of course, prevent for any reactions that might have occurred with atmosphere. The temperature was 1150 degrees C in the center, down to 1100 at the edges, something like this. Average heating rate was 60 degrees C per minute, and our samples were of 20 millimeters diameter, which after hot rolling was more than enough to produce plenty of samples for future testing. And such were the samples after our synthesis. As you can see, the NBC concentrations are present within the whole body of the material, and there are the more of the NBC was added, the more you can see it on the picture, obviously, of each composition. Now, 20% of NBC is showing a lot of cracks, of void spaces, because of the amount of NBC. And this is very interesting because at the beginning, this is the reference sample, you can see there are some vacancies, but with first 5 to 10% of NBC, due to the much smaller size of grains of NBC, as you saw, it's 1 to 10 micrometers when Inconel grains are bigger, 50 to 100. You can see that it filled a lot of those voids. But then in 20%, those voids are returning. This is because the amount of NBC is so big, so there is so many of NBC grains that between them there are new voids, and this is going even further for 30% of NBC, and therefore the loss of integrity I've mentioned before. If we investigate larger, we can see how the reinforcement influences matrix here, how there are a few additional vacancies on the edges of the matrix and reinforcement. And you can also see that there are plenty of precipitation that is typical to Inconel 625, even without NBC. But with more and more NBC added to the mixture, the more of precipitation is occurring, which was very interesting to us because such precipitation typically in Inconel 625 improves or is rather important for its high strength. And we are very interested if the hardness or tensile resistance would increase due to that. We've also distincted the phases during the EDS analysis. We found out that we can distinct three major phases here. There is obviously reinforcement and matrix of the composite, but there is also those precipitates. And there we found that such precipitation is very rich in molybdenum and niobium. Also some smaller present elements such as titanium and silicon were migrating towards them. We've also did such analysis on the reference sample here just to see if this precipitation will have the same tendency. And it is true. There is also, it is rich in molybdenum and niobium, and therefore we've later on referred to it as a molybdenum-rich, niobium-rich phases. Now, if we enlarge even further, we can see that due to this contrast in color, we can see that there is a small interaction between NBC and the matrix here on the edge, but it's more like and placing it in the matrix that there is a bit of reaction. However, it is possible, and we were to investigate how far we can go after the heat treatment, after the annealing. And this is where the most important and interesting, I think, part of this starts. As you can see on the left, you have after the heat treatment, after the annealing samples, and on the right, it is before. You can see here the tendency of the and how precipitates are more and more present with more NBC. But after the heat treatment, such precipitates are coarsening. There are less of them, but they are bigger. It is very visible on the reference sample, so it also happens for Inconel 625. This is annealing at 1200 degrees C, just to remind you. And this is very interesting how this will affect mechanical properties. The area fraction was dropped from at highest 30% here of precipitation to around 7 to 10%, which is a very high drop. We've investigated the hardness by a micro hardness intender Vickers method. You can see here that we could easily distinguish if we are targeting reinforcement here or a matrix here. That's why we could distinguish the average hardness for both. This is a typical hardness for Inconel 625 NBC, and you can see that even before heat treatment, the amount of reinforcement and precipitation as well was increasing the hardness. Here you can see that reinforcement is working properly, increasing hardness proportionally, but after the 5%, we can see that matrix is also having its hardness increased, and it reaches the average hardness of an NBC reinforcement. It's very similar to it. Therefore, this homogenical distribution is working properly for hardness. But more interestingly, after the heat treatment, even though there is the area fraction of precipitates is smaller, we can see that there is a significant improvement of reinforced materials, composites, whilst for a clear reference sample, it dropped due to this coarsening. we can see a very interesting hardness improvement. And it is interesting because for 5% of NBC is actually the highest. We've theorized about this, that it is probably because the reinforcement after the further reaction, which we saw only on the figure 7, we've seen that there was some interaction between them. After further reaction, reinforcement is scattered almost as precipitates, as other precipitates, creating the most homogeneous material of them all, quite resistant to hardness on average, and almost the same as a matrix. And the increase was quite high, of 15-20%. Now we've also tested the tensile, which was not yet published because this is very first study of it. You can see that quite obviously the elongation drops with a lot of ceramics addition, and 20% as well as 30% is just a bad sample. The loss of integrity is too big here. But for 5 and 10% of NBC, we have some promising results. Few things were improved here, including Young modulus, were most importantly not dropped below the reference sample. Therefore, with hardness improvement, those composites are possibly promising for some industrial applications. But of course, we have a lot more studies to do. This is very preliminary. This is the first article we've published, and there is more to go, including oxidation, corrosion, and so on. We are also thinking that if we improve the homogenization process by including planetary milling, planetary milling, for example, we can have much better results. This promising material will be only improved. Also, I like to point out that, as you saw during the microstructure analysis, TCP phases were not visible or present to our knowledge, and this also improved or was important for such mechanical properties. To conclude this, we've drawn 4 conclusions. First is spark plasma sintering is a viable method of obtaining Inconel 625 NBC composites. Yes, we can improve it. Yes, there is much to consider in this, but up to 28% of NBC, it is definitely possible to obtain it and use. This is different from typical works on Inconel 625 ceramic composites, which were mostly obtained due to the laser processing. Spark plasma sintering is something new here, and we are very happy that this worked out, and we'll be investigating further. Secondly, introduction of NBC into the Inconel 625 alloy is increasing the area fraction of precipitates, as you saw, and those are very important. If there are typical for Inconel, or if there are based from NBC, if there are carbides, if there are niobium rich, they are all good for mechanical properties of the final products, which is very good here. Additional heat treatment led to precipitate coarsening, and even though it reduced the area fraction, it was seen that the hardness can be improved by it. Therefore, such introductions creates a composite with increased hardness, and additional precipitation also increased matrix hardness, specifically, which we saw by involving micro hardness tester. And the best performance is obtained when we combine both heat treatment and such synthesis, such secondary phase distribution in the microstructure. In this study, it was achieved for 5% amount of NBC. And further, we will study around this amount, maybe 2.5, maybe 7.5%. We'll see. There is a lot to do during my PhD. I'm very happy to be a part of such studies. And just to acknowledge for you all, it was partially founded by National Science Center in Poland during the Preludium 13 grant. Authors declare no conflict of interest. I am very happy. I'm very grateful to them for all of their assistance. I'm grateful to my university, to Hokkaido University, for possibility to conduct both parts of research, to my colleagues and the professor who is working with me on this subject. I'm very thankful also for you for listening to me. I'm very grateful to be a part of this conference. I'm very thankful for your attention, and I'm open to your questions if you have any.
Yes, sir. Any questions? Any questions to Dr. Adrian Grabs? Sir, we'll be entering your name in the program by end of this day.
Thank you very much.
Yes, yes. If you have any questions or comments, you can text here so that we can ask of the participants. Thank you very much, sir, for participating in this event. Yes, on behalf of organizing committee members of Material Science and Nanotechnology 2021, we want to thank you for this. Thank you so much for joining and for your attention. If everything goes well in 2022, we can join in physical event. Yes. Next, we welcome Dr. Tanushree Chaudhary from School of Advanced Sciences from VIAT from India to join the event and start presenting.
Thank you, sir.
Yes, ma'am.
I'm sharing the screen, sir. See, this is not the instruction what I'm telling you today. You know this instruction for the past 1 year. Don't give an excuse that this is how you have been taken up the exam so far. That's not my problem. You have already got. Sir, is it visible?
Yes, madam. It's fine.
Thank you, sir, for welcoming me to this wonderful conference. I'm Dr. Tanushree Chaudhary. I'm working as an assistant professor in the chemistry division from VIT Chennai. And today my talk will be on the role of clay hybrid materials in treatment of wastewater. So we know that what is wastewater? Wastewater encompasses a wide range of potential contaminants. They range from that is being dyes, then inorganic organic substances, and any oxidizable material, any oxidizable species. And if we see that these contaminants, they are in very trace amount in the wastewater, and which is very difficult to remove. And that is why, according to Environmental Protection Act, they are also mentioned as emerging contaminants. And these emerging contaminants, they are not removed completely by any conventional methods. And that is why it augurs for a development system which can remove this contaminants, the low concentration contaminants completely from the wastewater. Titania has been used as a widespread photocatalyst for treating such contaminants. But then also, if we see that titania, the surface particle, that the particle size and the surface area particularly, particle size and surface area is small, and that is why it has low absorption ability. So we have prepared titania clay composite material membranes, which serves as the multifunction of both separation and photocatalysis. It's an integration of separation and photocatalysis, which has proven to be a novel and sustainable process of wastewater treatment. This is that is a structure of the clay, that is 2:1 clay, Montmorillonite clay. It is also known as the swelling clay because of a structure. It has a one octahedral layer being sandwiched between two tetrahedral layers, and it enjoys a very important property called the cation exchange property. And because of this cation exchange property, it exchanges the charge compensating cations with the hydroxy metal cations that are present in the solution. And as a result of which, upon calcination, it gives rise to thermally oxide pillars. And these thermally rigid oxide pillars, they have proven to be attractive membrane materials, because their pore size can be controlled by fine-tuning the properties during the pillaring process. And that is why today my topic that is of discussion will be on the preparation of these pillared clay materials, which enjoys a very important, it's actually a resurgent area in chemistry and resurgent area in material science, which can be used for the treatment of wastewater. Now, we know that is ceramic membranes, they are superior to polymeric membranes. And why? Because ceramic membranes, they have excellent mechanical property, they have excellent mechanical stability, thermal stability, and they have chemical stability over the polymeric membranes. So today that is the topic of discussion is on ceramic membranes, and the ceramic membranes that we have fabricated is of an asymmetric configuration. This asymmetric configuration is that consists of a base support clay membrane. Above all, and on the top of it, we have deposited an inner layer and at the top layer. And this three layers membrane, it actually serves as a very important parameter for a very low cutoff value and high fluxes. We have chosen natural clay as an excellent that is as a support material, because it provides a host of properties. We can see that it is very easily available at low cost. It has excellent mechanical and thermal resistance. It has large specific surface area and high cation exchange capacity, equivalent to 100 milli equivalent per gram. Then it has extremely good binding capacity exhibited by a structure. And that is why it became our obvious choice for being chosen as the support material, the membrane support. Now, why titania pillared clay membranes? Why not any other membranes? Titania pillared clay membrane, because the selectivity of any membrane material, it depends upon mainly on the thin layer, that is the active top layer that is being deposited on the support. And we have chosen titania pillared clay because titania has a plethora of very important properties. As we can see, it's mentioned over here, many important properties. Out of this, I would like to relegate to this important use, that is extreme amphoteric character. And this extreme amphoteric character, if you see, that is, it exhibits different charges at different pH values, as a result of which it results in the separation of cationic and anionic contaminants selectively. And because of the selective separation, it becomes very important that we study this property of the titania pillared clay membrane. So it actually serves as a bridge between separation and photocatalysis process for this. It's efficient integration between membrane and catalysis for any separation process. And also, this has not been studied till yet. That is the possibility of this as membrane material to remove the pollutants from water has not been explored till yet. Very little is mentioned in the literature of this titania pillar clay membrane as a membrane material. The methodology that we have used is a common sol-gel process that can be used in the laboratory. We have taken titanium 4 isopropoxide, which is the precursor. We've dissolved in water and isopropanol, that is the solvent, and that undergoes acid hydrolysis. Now this over here we have maintained two pH ranges, pH 2 and pH 3.5, to ascertain that is how the structure of the titania pillared clay material it changes with the different pH ranges. So it undergoes condensation to form the titania sole. And this titania sole, part of it, we have used it for dip coating method, which gives us the supported pillared clay membrane. And these supported ones we have used for the membrane rejection test. And the one which is the excess sole, which is being drained of this pillared clay material, which we have used it for that is the unsupported membrane. So unsupported ones we have just poured it into the petri dish and let it, and we have used it for drying. We set it for drying, gelation drying and sintering at different temperatures from 300 to 600 degrees centigrade, and we have used that material for characterization purposes. So in brief, this synthesis procedure is shown as a flow chart. That is, this is our symmetric membrane fabrication, that is, which consists of a flat disk support of clay, that is the base. And over there, this on the top, we have deposited interlayer of titania and binary interlayers of titania and clay, which give us, that is, titania and binary interlayers of titania and clay sold by sol-gel process at two pH values, pH 2 and pH 3.5, and that to ascertain the degree of the that is the structure, that how it changes at the two different pH. And that gave us the titania pillared clay membranes, which are formed by dip coating the support in the sole. Unsupported membranes were dried and sintered at various temperatures from 300 to 600 degrees centigrade, and the supported ones were used for the membrane rejection test. So over here we have prepared around 12 membranes, that is unsupported membrane materials, and 12 supported membrane materials at two pH ranges, pH 2 and pH 3.5. This characterization, if you see that this is the figures, they represent the FTIR spectra which has been taken at pH 2 and pH 3.5 respectively. So we see over here that is there's a vibration stretching peak of the OH group, that is around 3,400 per centimeter. It shows a broad, there's a peak at, it shows that interlayer water molecules that are associated with the molecule. And the another, if you see that's over here at 1049 per centimeter, it shows the vibration stretching peak of the SiO-Si bond, which is very much reduced in size, and that denotes that intercalation of titanium ions may have taken place into the lamellar space of the clay, leading to a delaminated material. And this has been confirmed by the XRD diagram. If you see that XRD diffractogram figure 3 and 4, if you see that over here, Montmorillonite clay shows a sharp crystalline peak at 2 theta value of 5.29. But over here, we see a broad hump over here at around 5.29 degree, 2 theta value, which denotes, this broad hump denotes that intercalation of titania 4 metal ions may have taken place, which should have led to a delaminated material. And there also we see a very sharp peak, that is around 25, 2 theta value of 25 degree, which is of anatase peak. And anatase, and on all temperature ranges, we see this, the formation of the anatase peak. And this anatase peak is of that of the titania, which refers to have the best photocatalytic activity. Then if you see that is this a 5 and 6, they refer that is the surface charge measurements which have been measured by the zeta potential, and these are the different membrane materials. So over here we see that at pH 3.5, the zeta potential values, they show that is a maximum of that is of minus 25 millivolt for all the membrane materials that have been prepared at pH 3.5. In other words, that is, it also denotes that is the membrane material to be more dispersed and to be more stable at this pH value, pH 3.5. So that is why our this choice of membrane material becomes obvious at pH 3.5. It gives the best membrane material because it is the best dispersed as well as stable. Now, when we find out that is the pore size distribution is very important, because it also gives a reflection about the separation and rejection of the contaminants. So over here we find that a narrow pore size distribution is effective for effective separation of the contaminants. So over here we see that both have been conducted at various pH, that is pH 2 and pH 3.5. We see that pH 3 and pH 8, both of titania and clay, they give a very narrow pore size distribution at pH 3.5. And that is why at pH 3.5, the membrane material not only gives a very stable dispersion, it also gives a very narrow pore size distribution curve, which is very effective for the separation of contaminants less than molecular weight, less than 500 DA. Characterization by SEM reveals that is the formation of anatase peak. The formation of anatase has taken place at all temperatures from 300 to 600 degrees centigrade. Anatase is one of the major phases that have been formed, and we know that anatase has the best photocatalytic activity. Now we conducted the membrane rejection test for the membrane materials that we fabricated, and we found that it shows around 100% rejection for all the membrane materials that we have prepared. So it also concludes that the membrane material that has been formed at 300 degrees centigrade and at pH 3.5 so it proves to be the best material, that also not because of the lower cost, but also because at 300 degrees centigrade, we have tried to make a better material than the gamma alumina, which has been reported in the literature. So as against the gamma alumina, we have prepared a better material, that is titanium pillar clay material, which can work at 300 degrees centigrade, and at a pH 3.5, it gives the best result. Now we have used these membrane materials, we have applied it for the wastewater treatment. So one application that we did was we have grafted the clay surface. Now clay surface, that is because of this charge compensating, that is high cation exchange capacity, it can be used for many synthesis procedures. So what we have done, we have taken this montmorillonite clay and we have reacted it with 3-amino-propyl triethoxysilane, which led to the drafting of the selenol groups on the clay, that is OH groups. As it can be seen that OH groups have been grafted on the clay surface. So it led to the formation of silane grafted clay. We have used this silane grafted clay for for the treatment of the wastewater. So we have added this titania sole to the silane grafted clay, and it led to the grafted titania pillared clay material. And this grafted titania pillared clay material, when it was sintered and that was dried and sintered at 300 degrees centigrade, we formed both the supported and the unsupported membranes. Supported membranes were used for the membrane rejection test, and the unsupported membranes were used for characterization. Unsupported membranes which were used for characterization, they gave the FTIR. We did the FTIR XRD characterizations with the unsupported membranes, and with the supported membranes we did the membrane rejection test, which is shown over here. So as we can see, that is at pH 3.5, with the various membranes that were prepared at pH 3.5, it gave around 100% rejection test with the methylene blue dye, and also with the anionic dye, that is methyl orange. So in the literature, if you find that that is the membrane materials which have been prepared till date, they have given that is good test with the cationic dye, but not with the anionic dye. So that has been possible because of this formation of this grafted clay, which has got selenol groups on its surface. So the mechanism that we cited in our this paper that we have published, that is on recent patents on nanotechnology, we cited that is because of the OH groups that have been grafted on the clay surface that reacts with the cationic as well as the anionic dye molecules to give an OH bond, that is hydrogen bond. And because of this hydrogen bond, it leads to effective separation of the that is dye molecule from the wastewater. But one drawback that was observed over here was that though it led to the effective separation, it led to fouling of the membrane because of the deposition of thin layer of this dye molecule on the membrane surface, which reduced the fouling, which increased the fouling as well as which decreased the flux rate. So that was overcome. We modified it and we prepared platinum doped titania pillared clay membrane. Now, because of this doping of this platinum into the titania pillared clay membrane, it created a positive charge on the membrane surface. So what we did is we took Montmorillonite clay, we treated with chloroplatinic acid, it gave platinum, that is, the platinum was doped, which upon drying and sintering, it gave platinum doped Montmorillonite. So when we studied this using 3IR spectra and XRD, as you can see over here, that is this is the platinum clay and this is the S1 and S2 refers to there's a platinum that is a FTR spectra of platinum doped titanium pillar clay materials. So as we can see that is the vibration stretching peak at around 1049 per centimeter, it has been completely lost, indicating that the titanium ions, titanium 4 plus ions may have intercalated into the lamellar space of the clay. Also, we can see the formation of an anatase peak in the XRD diffractogram, a very intense crystalline anatase peak in that's in the XRD diffractogram. When we did the zeta potential measurements for the development of the surface charge, we found that it showed a positive value, and that's positive charge. The membrane material contains a positive charge, which led to hydrophilic property. And when we did the pore size distribution pattern of the platinum doped titanium pillar clay materials, we saw a very narrow pore size distribution pattern as compared to the titanium. And that is very effective for the separation of the organic contaminants, which molecular weight is less than 500 Da. So when we exposed these membrane materials for membrane rejection test with methylene blue and methyl orange dyes, we found that they gave around 100% rejection test with methylene blue and methyl orange. But methyl orange, it gave rejection test good for only pH 3.5 and not with the membrane materials with pH 2. So that concludes that is the more the hydrophilic character, the more is the less is the fouling and more is the flux rate. So we took this membrane materials for the treatment of real wastewater treatment. That is real wastewater. We collected the sample from one of the that is textile mills in from Tamil Nadu, and we studied the characteristics of the wastewater. It gave us the pH 9.07, TDS around 11,385 ppm. The DO was around 1.55 ppm, and COD was around 1280 ppm. But when we subjected this wastewater to both the two membranes, that is the grafted pillared clay membrane as well as the platinum doped pillared clay membrane, so we found the drastic changes that have been taken to the wastewater. If you see, that is the grafted pillared clay membrane at pH 2, that is the pH was 3.73 for the treated water, and DO rose to around 4.46 ppm. The TDS was reduced to 6,622 ppm. The flux rate was around 7,200 liter per meter square per hour. For the grafted titanium pillared clay membranes at pH 3.5, if we see, that is the COD, was around 1120 ppm, but the DO rose to around 4.5 ppm. The TDS was 7,638, and the flux rate was around 70 to 100. When we compared this with the platinum doped titanium pillared clay membranes at pH 2 and pH 3.5, we saw a very significant increase in the flux rate, and that is just because of the hydrophilic character. So this is very important when we study the membrane characteristics, because good flux rate is very important for effective separation and also for a best membrane material. So flux rate, if you see, that is rose to around 280 to 285 liter per meter square for pH 2, and for pH 5 also it was around 280 to pH 3.5, it was around 280 to 285 liter per meter square per hour. And other properties also, if you see, the DO was comparatively better. It was 4.55 ppm. TDS was around 7,983 ppm. And COD also got reduced to quite low, that is 450 ppm. So this was a comparative study between the different membranes that we prepared in the laboratory. Though the work is going on for preparation, how to upscale the membrane for use in the industrial process, and that will be taken care in the future. So So I would like to conclude my talk by thus mentioning some very important points that over here we see that pH is one of the most important parameters that is expected to affect the effective rejection of organic compounds. The surface charge of the material depends upon the pH of the feed solution, and that is also very important parameter for realizing the efficiency of a membrane separation process. And the one that we have prepared at pH 3.5 and we centered at 300 degrees centigrade, it shows the best result and also is a low cost membrane material which can be used for further applications as compared to the gamma alumina which has been described in the literature. And we see that sintering at low temperature produces anatase as a major phase. And we know that anatase has got number of hydroxyl groups responsible for hydrogen bonding and also higher rejection of organic pollutant, though it led to the fouling, which we tackled with by the doping process of the membrane by precious metals such as platinum, which induces a positive charge and is responsible for resistance against fouling. So in the nutshell, I can say that by controlling the surface charge, we can lead to selective removal of the pollutants. This work has been a part of the Water Initiative project, which was funded by Department of Science and Technology, Government of India. And I would really like to thank the organizers for giving me such a wonderful chance to present my work in this conference. Look forward to sharing such experience in the future as well. Thank you.
Yes, thank you. Thank you very much, madam. But we are getting a little bit of voice from your side, madam, while
Yeah,
you are
actually,
delivering.
I think so. The classes are going on, sir. I'm very sorry because I'm in the department now. So
Yes,
I'm
yes,
very sorry. Yes.
yes,
Yeah.
yes,
I shall mute
yes,
myself, sir. Yeah.
yes. If you have any questions or comments, you can text here so that we can ask few of the participants. Any questions to Dr. Tanushree
Yes.
Chaudhary? Yes, sir, you
Yeah,
can go
yeah.
ahead.
Yeah. Thank you, Dr. Tanushree, for your very nice presentation. It's a very good work.
Thank you, sir. Thank you, sir.
But I have a little queries about the industrial water treatment. So regarding the
Yes,
pharmaceutical industry, the wastewater contain a tiny drug materials, different kind of drug materials. Say, for example, chloramphenicol, paracetamol,
yes,
Dronate,
yes,
ofloxacin, or Nirazole, etc. And
yes.
as well as most of the industry contains a little bit of like arsenic, lead, mercury, cadmium,
Metals, heavy
chromium,
metals.
etc.
Yes.
Can these titanium clay composites move successfully these types of components like heavy metal components and the tiny drug components?
Good question, sir. Actually, my next project is on that only, and it is in review process. So my next is that how to remove the heavy metals by the titanium pillared clay composites. So I'll be starting that work soon, sir.
Exactly.
So,
Actually, if you conduct these types of experiments, it's have a huge commercial impact.
exactly, sir. Exactly. And I have written.
Another thing is you measure the COD levels. So what is the COD level experiment and what's the COD level after experiment?
Yes, true, sir. And I would like to say that my next work is actually when I subjected this proposal to DST, both the works were together, but they cut short it and they told only now you concentrate on the dye removal, and that is why my next project is on the treatment of the wastewater. That is where I can remove the heavy metals from the wastewater because that is very important. If you see the Chennai wastewater, it contains chromium-6. So my next topic, my next.
Thank you, Dr. Tunusri. It's a
Thank you.
very nice work. Go
Thank,
ahead.
thank you, sir. Thank you, sir.
Okay.
Yes. Any question further? Yes. Thank you. Thank you very much, madam, for participating in this event.
Thank you, sir. Thank you.
Yes. On behalf of OCM of Material Science as well as Nanotechnology 21, we want to thank you for this presentation. Looking forward to meet you again next time if everything goes well in physical event.
Sure,
Yes,
sir.
yes. Next, we will go with the starting keynote speaker, Dr. Soshu Kihara from Joining and Welding Research Institute from Osaka University from Japan. We will be playing a video presentation.
Okay, today I would like to talk about a new additive manufacturing process of the name is ultraviolet laser lithography. Okay. So in our investigation group, we try to fabricate various kind of metal and ceramic structures composed of 2 dimensions and 3 dimensional structures. Okay. So there are structures and composed of periodic patterns and self-similar patterns. The periodic patterns has integer dimensions, 1 to 3 dimensions, and the self-similar structures is a non-integer dimension like this. Anyway, we can control the electromagnetic wave and the electric and magnetic field and the force and the sound dynamic field and the material diffusion flow, and by using 3 dimensions and 2 dimension and material patterns. So today I would like to talk about the photonic crystals, the functional materials of our. It's possible to control the electromagnetic wave by wave diffractions. Okay, here is our photonic crystals. Okay, this artificial crystal composed of dielectric materials and the periodic structures. And this is electromagnetic waves whose wavelength is similar to this periodicity. In this case, the wave will be reflected by Bragg diffractions. In this case, then, the 2 different standing wave form in the crystal structures. For example, the one wave and the wave A vibrating in air region with higher frequency, and the wave B vibrating with lower frequency in the material regions. And the standing wave A and the standing wave B, between these frequency, the all electromagnetic wave will be reflected by Bragg diffractions. So in the limited frequency range, photonic bandgap form. This bandgap is possible to prohibit the electromagnetic wave propagations in these frequency areas. Okay. Anyway, the photonic crystals are artificial crystal composed of dielectric material periodic structures, and it's possible to open the photonic bandgap for the typical crystal directions. Okay, what is the ideal photonic crystal structures? The one type is like this, the diamond type. These are the 4 coordination number. Okay, if you introduce the electromagnetic wave for these 111, the 110, the 100, the crystal directions, the photonic bandgap will be opened for all crystal directions in the similar frequency range. This blue band shows the common regions for all crystal directions. So in this perfect photonic bandgap areas, all electromagnetic wave impossible to transmit to the opposite side for any directions in the artificial crystal patterns. Anyway, and the perfect photonic crystals, the diamond type photonic crystal, possible to open the perfect photonic bandgap. Okay, however, these has very difficult crystal structures, 3-dimensional patterns, so it is difficult to fabricate by using a conventional mechanical processing method. So in our investigation group, we try to fabricate the diamond type photonic crystals by using a stereolithography, one type of the additive manufacturing process. Okay, here is a photosensitive resins, and the UV laser scanned on the liquid surface to create the 2-dimensional patterns. And the layer by layer stacking, we can obtain the complicated shaped 3-dimensional structures. And the most important things in the liquid phase, ceramics particles are dispersed and to increase the dielectric constant of the 3-dimensional patterns. Anyway, we can obtain the composite materials, dielectric ceramics and the resin matrix, and by using a layer by layer stacking, stereolithography, additive manufacturing process. Okay, at first our additive manufacturing material 3-dimensional printer ink was fabricated by using rotation revolution mixing machines. The aluminum particles, particle diameter is 117 nanometers, were dispersed into the photosensitive acrylic resin, the 40 volume %. Okay, and this liquid phase and the solid phase mixed materials enter into like this small pot, and by using rotation rotations, and the liquid phase and solid phase of the mix in here, and by using revolutions, so the gassing will be realized. So by using this mixing machines, we can obtain the paste materials. Okay, this figure shows a schematic illustration of the stereolithography. The paste materials are spread on the glass substrate by using mechanical knife edge. In this case, the layer thickness about 30 micron. Sorry. So on the liquid surface, paste surface, laser beam scanned on the like this, and to create the cross sections of the solid layers. And the spread and the laser scanning and the layer by layer stacking process, we can obtain the 3D solid structures in unsolidified paste materials. These 3D structures are picked up after fabrications, so the composite materials will be transferred to the full ceramic structures through the conventional dewaxing and sintering process. Anyway, in this case, the alumina particles and the particle diameter is 170 nanometers were dispersed into the acrylic resin and 40 bottom percent, and this paste materials were used. And the ultraviolet laser beam wavelength is 355 nanometers, and the diameter is 13 microns, and the laser power is 100 microwatt. Okay, this figure shows obtained the stereolithography the samples, and you can see the micrometer, the 3D lattice was obtained. Okay, of course, this is composite materials. This yellow color means resin matrix. So through the waxing process about 600 degrees C, you can see the resin matrix burner at perfectly. So after the waxing and the sintering will be executed about 1000 degrees C. Okay. So this figure shows obtained the full ceramics micro lattice. You can see there are very fine lattice structures was obtained. In this case, a relative density reached as a 99.8%. High density micro lattice was obtained. Alumina structures was obtained, and you can see that translucent micro lattice was obtained by using stereolithography and dewaxing and sintering processes. So the terahertz wave transmission pattern was measured by using this optical system. So the micrometer or the photonic crystals possible to control the micrometer or the electromagnetic wave. That's name is a terahertz wave. Okay. Anyway, at first the femtosecond laser beam the incident into the like this micro antenna emitter, and generated and terahertz wave or terahertz wave pulse transmit a sample and detected the same shape the micro antennas, and we can obtain the like this time and intensity pulse data, and through the Fourier transformation we can obtain the spectrum. Terahertz wave transmission spectrum for the sample. The sample, of course, this is the photonic crystals. Okay, you can see there. This figure shows the attenuation properties of the terahertz wave, the frequency and the attenuation. Okay, and you can see the photonic band gap open for all three directions: 111, the 100, the 110 crystal directions. And this blue band shows a common region for all crystal directions. For example, the 0.4 terahertz wave impossible to transmit for any directions by formation of the photonic band gap. So this means a perfect photonic band gap formations. Okay, this figure shows natural semiconductor crystals composed of the periodic structures of the atoms. Okay, in this case, here is an electronic wave, whose wavelength is similar to this periodicity. The wave will be reflected by Bragg diffractions. So in this case, the electronic band gap opens in the electronic band areas. And and if you introduce the donor and the acceptor, so that you can create the various kind of the localized mode in the electronic band gap, and you can control the electronic wave transmission and the reflections by semiconductor structures. Okay, the photonic crystals are the imitation, the artificial structures that are imitate to the natural semiconductors, and the composed of the periodic structure of the dielectric materials. And in this case, the photonic band gap opened by electromagnetic wave diffractions. So if you introduce a point defect and line defect and a plane defect, you can create the various kind of the localized mode in the photonic band gap. Okay. So this figure shows a point defect introduced into the perfect photonic structures, photonic crystal structures in the diagonal lattice. Okay. So here is one unit and cubic shape, and cavity was introduced inside of the photonic crystal structures. Okay, this figure shows our calculation result. Okay, incident wave in this case localize and resonate here, and one wave and localize here, and increase the power, making us here is the perfect reflection areas, and the wave diffractions and the wave vibrations and the multiple reflections occurs and increase the power and transmit to the opposite side like this. Okay, in this case, the incident wave and the localize resonate here, and one wave localize this directions, and here is a high intensity wave, and so the localize resonate, and the surrounding here is our perfect reflection areas, so the multiple reflection occurs and increase the power and transmit to the opposite side. Okay, the frequency the 0.43 and the 0.46. Okay, so this figure shows the measurement result, and the perfect photonic crystals possible to open the photonic band gap in the limited frequency range. And the 0.42 and the 0.46 terahertz wave, and you can see the transmission mode is occurred like this. Okay, these are localized mode. And the perfect photonic band gap, photonic crystal open the photonic band gap, and they introduce the structural defect, the point defect, possible to create the localized mode of the transmission peak like this. Of course, you can control the peak frequency by changing cavity size. If you introduce more large cavities, and this peak frequency shifted for low frequency. And if you introduce a more small point defect, you can control the peak frequency for the shift for the higher frequency anyway. So this is same figures, however, and in this investigation, in these trials, we have to use two different process. And at first, the stereolithography process, 3D fabrications, and the dewaxing process. So the next trial is a directional fabrication of the ceramic structures by using only one process, using a laser stereolithography process. In this case, the schematic illustrations is similar to the conventional stereolithography. However, the laser beam power increased into the 1 watt. This is not so high, looks like. However, this is 10 times higher than the conventional stereolithography process. Okay, laser beam scanned on the liquid surface. Of course, the liquid surface means a ceramic particle dispersing resin paste like this. And the high power UV laser will be possible to do the waxing, the resin decompositions, and the sintering through the electromagnetic wave resonance, localization, and absorption like this. So you can create the ceramic structures only the UV laser stereolithography, only one process. Okay, this figure shows a process photograph, and you can see the bright color obtained, and the laser beam scanned on the like this and the paste surface, so we can obtain the plate-shaped structures. Okay, here the solid structures, and this figure shows a microstructure of the plate-shaped structures samples, and you can see the large-scale ceramic sparks was obtained, and the bulks and grain were obtained. Okay, and grain size and the particle size, grain size is about 5 microns and 10 microns. So at first, dispersed ceramic particle the diameter is under 1 microns, and for example, 500 nanometers. So the particle, the resin or the gases and the gas and the particle were sintered by UV laser irradiations. So in this case, the spread paste thickness is 50 microns. And however, after laser drawing and the layer thickness decreased to the 25 microns. Okay, this means the surrounding particle dispersion is just 50 volume percent equal to the volume percent. Okay, the shrinkage. So the dewaxing and sintering shrinkage occurs only the Z directions. So it's possible to realize a layer by layer processing. So this figure shows a calculated result. In our investigations in the ultraviolet laser beam were used to create the three-dimensional structures. And in this case, a laser beam, the wavelength is the 355 nanometers. So in this case, the shorter wavelengths were easy to propagate the inside into the paste materials. So the inside resonation and the localization will be occurs. So the resin dewaxing and the powder sintering will be realized inside of the paste materials in this case. However, if you use using an infrared laser beam with higher wavelengths, longer wavelengths in the 1200 nanometers, the longer wavelengths impossible to propagate inside into the paste materials. So on the surface, the scattering will be occurred, the laser beam and return to the backside, to the laser source. Okay, this figure shows the fabricated titanium photonic crystal, the lattice structures. Okay, yeah, at first, and the spot size was set for the 10 microns, and the scanning speed was 15 millimeter per second. Okay, and in this case, you can see the nano-sized particles were coagulate in the three-dimensional structures. These black areas, of course, remain the carbon element. So the scanning speed increased twice, and okay, like here, okay, we can obtain the micrometer or the very fine structure. However, there are black areas, remain the carbon areas is increased like this. So the irradiation power was increased to the 600 microwatt to the 700 microwatt. Okay, so by using this laser scanning conditions, we can obtain the like this what you say, the white color, the titanium dioxide micro lattice successfully. So okay, this figure shows measurement results and the X-ray diffractions created the titanium crystal paste. Okay, so you can see there the rutile structures was obtained. So they're sintering the temperatures and reached at about the 1000 degrees C. However, so you can see anatase phase were remained like this. Of course, that at first the nano-sized particles, all nano-sized particle has the anatase phase. However, after laser sintering and the rutile phase obtained like this. However, the anatase phase remained. So, and okay. So the other photonic crystal structures was fabricated. In this case, a plane defect was introduced into the photonic crystals. Okay, these figures shows the twin photonic crystals. Okay, in this case, the left side and the right side and the right side has mirror symmetric lattice patterns. Okay, this dotted line shows introduce a plane defect. Okay, here is this is and this is, and these are the perfect photonic crystals, and these dotted lines means introduce the plane defect. Okay, so this figure shows a calculated result. Okay, the incident electromagnetic wave are localized and resonate in the introduced plane defect, and reflect between the perfect reflection, the lattice, Okay, the make a much for reflections in the plate shape areas, and increase the powers and transmit the opposite side. And the transmitted wavelengths electromagnetic waves plane wave because the resonation areas are plane shape cavities. So okay, this figure shows the the purple color shows the calculated results, the electromagnetic band gap, the photonic band gap, and the yellow line shows the measurement result. And the calculations and the measurements has good agreements. And perfect photonic band gap, photonic crystal structures open the large scale band gap, and introduce plane wave, plane defect structures possible to realize localized mode formations like this. And the peak frequency there is a very, they have good agreement in the measurements and the calculated results. Yes. So there, here is the plane defect. So there we can enter the surface, the grass, and create the cavity areas, and we can introduce the aqueous solutions, so that we can mix the terahertz wave vibrations in the aqueous solutions by using this module, that is photonic crystal and photonic crystal twin structures. So this figure shows, this photograph shows created the photonic crystal resonators, and here is a resin case, and here is the photonic crystals, and the micro tube enter into the like this, and the aqueous the cavity areas. So, and the most important thing is the terahertz wave is a micrometer orders and the higher frequency electromagnetic wave. So there it's possible to localize and resonate with the micrometer orders and the molecular structures. This is the polysaccharide molecular structures, and in this case the spectrum, the absorption spectrum, terahertz wave, and many peak frequency. So the higher frequency vibrating these molecules for large scale, and lower frequency, lower wavelengths is the vibrating each saccharide by a higher frequency. So anyway, and the terahertz wave is possible to control the chemical reactions of the large scale molecules. So if you introduce like these molecules into the cavity areas, so you can mix and successfully and terahertz wave and the molecular vibrations, so you can control the chemical reaction like this. Okay, this is last slide. In our investigation group, we try to fabricate various kinds of ceramic and metal structures by using stereolithography process and directional fabrications or the ultraviolet laser beam lithography. And of course, three-dimensional structures and the two-dimensional structures have the periodic structures with integer dimensions, and self-similar fractal structures with non-integer dimensions. Anyway, and in the near future, we try to connect these three-dimensional structures to control the energy flow and the material flow controls by using a three-dimension and two-dimension, non-integer and the integer dimensions. There are complicated structures. Thank you very much for your attention.
Yes. Just if you have any questions, you can text in chat box. That this is the previous video was delivered by Dr. Soshu Kirov from the Joining a Welding Research Institute from Osaka University. So we'll be going with another video presentation by Dr. N.M. Ferrara from University of Aveiro from Portugal.
Hello, my name is Nuno Ferreira. I'm a researcher of I3N at Aveiro University. I work in collaboration with CISECO, Aveiro Institute of Materials, and also with the University of Zaragoza. My talk will be about the laser processing of ceramic-based thermoelectric materials. Knowing that only 34% of our primary energy is used, the remaining energy lost as heat is necessary to increase this efficiency. So we are seeking new technology, new process to recover that heat. One of the solutions is the use of thermoelectric models that allows to recover this heat and convert it into electrical energy and retrieve it to the electrical net to be used. A thermoelectric generator consists of N and P-type semiconductors that have electrical connection between them. Due to a thermal gradient along them, a voltage is generated, and adding a charge, an electrical current is observed. A thermoelectric generator will be composed by several of these pairs, allowing to increase the power that is generated. To characterize the thermoelectric materials, you use the power factor that gives you the relation between the Seebeck and the resistivity or the conductivity. Also, we use the figure of merit, ZT, that gives us a relation between the power factor and the thermal conductivity of our material. We are looking for ZT near 1, while the power factor values of 0.15 to 0.3 are good enough. We see that the relation between the Seebeck and the electrical conductivity are due to the number of charge carrier. While increase the charge carrier, you see that Seebeck decrease, while the thermal conductivity increase. It means that is the optimal value of power factor. This optimal value depending of the composition and also by the process method. So you are looking for the good compositions and the effect of the method. For thermal conductivity, you see there are two parts, the lattice and the electronic. While the lattice is intrinsic from our material, the electronic you can change by the doping or also by the method. Is where it's looking. So you see that when we try to increase the Seebeck coefficient, the electrical resistivity also increase. There is a relation between to the charge carrier. Nowadays, you can find thermoelectric models that are composed by heavy elements. They are toxic, rare, and not stable at high temperature. We propose the use of oxides that are eco-friendly, is abundant, is stable at high temperature. We focus our research in bismuth transfer cobalt materials and also with calcium manganese. They are stable at high temperature. This temperature application depending of the type of applications that you intend. So what you're looking is increase the ZT of our materials and also the power that can generate according to the application that we intend. Since we work with ceramics, the traditional ceramic processing is the solid state wood. We consist in to get the oxide compositions that is mixed to get homogeneous powders. After that, we perform the sintering or the melting in the furnace. After that, we perform the characterization. In our work, we use a non-conventional crystal growth method, that is the laser floating zone. The basis is the Bernoulli method, where the powder is melted by the gas burner, allowing to grow single crystals. This method suffered several improvements due to the technique to melt the powder. We use a CO2 laser, where you get the feed rod, that is the powder, the raw materials, and is molten, and after that we use the seed to start to pulling and get the orientation of the fibers. This is called floating because in the molten zone is keep constant volume constant. This is the photo of our system. You see here a CO2 laser to allow to melt the material. You see the chamber growth when everything occurs, and you also use a CCD camera to see in situ the melting process. We have a homemade control program that allows us to control the power of the laser, the grow rate, and the camera to see the process of the melting. You operate at room temperature, room conditions, and you can reach high temperature in a few seconds since we control the power of the laser that go to 0 until 100% of the power in few seconds. We use oxide powders as starting materials as we work with ceramic or glassy systems. We study mainly the condition of the laser processing on the crystallization mechanisms and their influence on the properties. We perform the structural, optical, thermal, magnetic, and electrical characterization of the process samples. You show here the scheme to prepare our samples. We start with our oxide powder mixture that we intend to prepare. After we add a PVA as a binder that allows to make a cold extrusion, and you get these green bars that you use to melt by the laser floating zone. We operate the laser floating zone at certain conditions, and the grow rates can go from 5 to 200 millimeters per hour. The fiber dimension go up to 12 centimeters length and diameters below the 5 millimeters. You see here a fiber that was processed. After that, we perform the structural, thermal, electric, magnetic, and optical characterization. Now I show you a movie of the starting this process. First of all, we do the laser the feed in order to get a drop of melt material, as you can see. After that, we have a drop of the melt. We join these two parts, the feed and the seed, to get here a floating zone of melt material, as you can see now. Okay. After this region is stable, we start to pull in this constant velocity and feeding this constant velocity. The velocity of the pulling is related with as the cooling rate. Okay, for high pulling rate is like a high cooling rate and the freezing of the system, and low the mechanism of solidifications occurs and crystallization can be controlled. The laser floating zone is known to produce dense materials since we start for the molten material. We are able also to obtain single crystals or polycrystalline materials with texture, as I show you is the micro or a polished section of the sample. You see here different phases that align with the growth direction. We are also able to tune the phase materials as we control the growth rate in general. For lower pulling rate, you obtain single phase, single crystals since the system have time to organize, rearrange the phases. When you start to increase, polycrystallines appears, and if for higher pulling rate, amorphous materials is observed since is such we freeze in the molten zone. This method represents follow advantage: no contamination, that are free crucibles. It's easy preparation, that is just mix the powder, extrude the rods and heat the laser. We perform at room conditions. We can reach high temperature quickly since we control the power of the laser. Since this method we produce dense material, and with the pulling rate control we can texture and alignment the materials. We can tuning the phases from amorphous to single crystal. The geometry of the fibers are good for employing in thermoelectric models. Since this is a homemade system, we can improve the process, such as applying a two-sphere external fields such as electrical or magnetic. However, these have some advantage, of course. The fiber dimensions, diameter is very low. For instance, for thermal conductivity is very difficult. Since you have a grain alignments, is not possible to measure the charge carrier due to the Hall effect. The melting point of such elements, for instance, the oxide zinc, the evaporation temperature is near the melting. So when you hit the laser, they melt and evaporate instantaneously. And the composition that you want to grow must absorb the wavelength of the laser. Otherwise, it's transparent, is not possible to melt. For some systems, such as tungsten titanate, we obtain incongruent growth that is not possible to grow. And some condition of growth results in fragile fibers that are not allowed to perform the characterization. With this work, we intend to develop new materials with high thermoelectric performance using laser processing. For the next step will be build the models with these processed materials to see how is their performance as a model. For the future, use these materials in the real applications. Now I will present some results on P-type oxide materials that we have made. Here we present the P-type sample of bismuth strontium cobalt oxide that was prepared by solid-state route and laser floating zone. For X-ray, we detect the main phase thermoelectric and also secondary phases composed by bismuth strontium oxides and strontium cobalt oxides. When you see the fiber that was processed by laser floating zone, you see the same main phase, that is the thermoelectric, and also the secondary phases. However, when you sinter these fibers, you observe that secondary phases decrease due to the reaction in order to promote the main phase. When you observe the micrograph for the solid state root samples, you see the aspect characteristic of these samples. When you observe also the micrograph for the fiber, you see that the alignment with the growth directions, which is also characteristic. When we sinter the fiber, we see that some reactions of the secondary phases, and we increase the magnification, you see that they are on uniform aspect, and the orientations that is characteristic of the laser floating zone. When you see the resistivity, that solid state sample presents high resistivity, while the processed fiber have a lower decrease of the resistivity. But when we sinter this fiber, the resistivity decrease higher. This is because of the orientation of the fiber, and also by sintering that reduce the secondary phases. When you observe the power factor, you see the solid state route presents a good power factor, but as a floating zone fiber presents an increase of the power factor. However, when we sinter this fiber, the power factor increase 2 times the value, and you obtain the higher value that is much higher than the report for this material. We can prove that sintering the fibers is good because it increases this thermoelectric performance. Here in this slide we present the results of calcium cobalt oxide material prepared by laser floating zone. We observe that after processed by laser, these two oxides don't react, and you obtain the phase of calcium oxide and cobalt oxide. Well, after the sintering at 900 degrees 24 hours, you see that these two phases react, and you obtain the thermoelectric phase aspects and increase the time of the duration of the heat treatment. These secondary phases start to decrease. By the resistivity measurements, you see that resistivity decreases with the increase of the duration of heat treatment, which is according with the reduction of secondary phases. And the Seebeck increase also with the duration of the heat treatment. For the power factor, you see that 24 hours is a good performance, is a good value for power factor, and increased 2 times for 72 hours, indicating that this duration is optimal for the improvement of the thermoelectric performance of this material. Our system of laser floating zones is a homemade system allow us to make some improvements, as I told you previously. So one of the improvements that we made was applying the electrical field, and we call electrical assisted laser floating zone. In this case, we have a DC power supply that you can allow to direct the current in direct direction or inverse direction depending of the growth direction and the current. This means that in the voltage zone we have a constant tension and allowing to get a higher alignment of the phases in our material. We apply the electrical field in these samples with calcium cobalt oxide samples, and you observe that by the normal growth of the fiber without current, that thermoelectric phase is formed, and also secondary phases. When you apply a direct current, you observe the formation of the thermoelectric phase and the reduction of secondary phases. However, when you apply a reverse current, the thermoelectric phase is not detected and the other phases are formed. And by micrographs, you observe that for the sample grow without current, the normal orientation, the characteristic of the LFZ. When you apply a direct current, that increase of the orientation of the phase are observed, and the reverse current, no orientation is observed in the phases. Moreover, we observe some materials fluid from the fiber, as you observe here, indicating that is the material try to get out of the grow system. Is indicating to us that exists a direct current orientation that should be applied in order to increase the performance of the material. Moreover, when you pull figures of the fiber without current, you see some orientation of the phase thermolytic phases as we expect, but increasing the current, we see that this orientation increased. This was also confirmed by some observation when you see the alignments of the fiber without current and with 300 milliamps, we see this orientation. This is a result in the power factor values that we improve 4 times when compared the sample without current with the sample grow with the 300 milliamps, in obtaining high power factor when compared with a single crystal sample. We have also prepared N-type materials in the system of calcium manganites, and we prepared a pure material and also doped with niobium with substitution of manganese by niobium and also a substitution of calcium by lanthanum. In these systems, we are prepared with different pooling rates, 200 millimeters and up to 10 millimeters. And you see that decreasing the pooling rate, the formation of secondary phases appears when compared with the high pooling rate. This is observed also for the other samples doped. From the resistive measurements, you see that doping our pure material, the resistivity decrease. However, you see also the effect of the pooling rate, that for higher pooling rate, you obtain lower resistivity. From the CVEC, we confirm the same results of the resistivity, that the pure sample presents higher CVEC and decreasing with the use of dopants, and where the lanthanum sample doped present the lower CVEC, and also the higher pooling rate present the lower CVEC. These results originate that the power factor of the pure sample at 10 millimeters present the best power factor, while the lanthanum samples present the higher power factor and the opposite, and increasing the pooling rate decrease the power factor. Is the same observed for niobium and for the pure sample, indicating that the pool rate is important, have an effect, and you can turn the results and also the dopants. When you compare the results of power factor with the pooling rate, you see that power factor decrease when you increase the pooling rate. Moreover, when we dope with niobium, the power factor increases a little bit, but increases more when we dope with lanthanum. This increase of the power factor with the pooling rate is due to the increase of the conductivity. Moreover, based on these results, you start to study these samples grow at 100 millimeters per hour for next studies. The present results want to show you the effect of the dopant lanthanum or dope with niobium because of the substitution of manganese and their oxidation states. While with lanthanum the power factor is higher than the others, you see the thermal conductivity is higher for the niobium sample. So it means that the ZT decrease from the lanthanum doped to the niobium, indicating that the substitution of manganese for other elements is not good because change the oxidation state. In the literature, it's told that when you sinter the fibers, the secondary phase decrease because they react and originate the main phase. So we have performed our sinter the fibers at 1300 degrees per 10 hours, and you see that secondary phases decrease after sintered for all the fibers, as the pure with niobium and also with lanthanum. In echograph, you observe the fibers as grown here, and after sintering, and you see that you have a better region definition of the secondary phases that will, because of the alignment, they react and
so they will improve the performance of our materials. Overall, what you see is the power factor that after sintering, they increase the reaction. And you see that niobium increase their performance after is lanthanum, and the pure is lower the power factor. This is because of the conductivity that stays, and also for the seeback that these fibers react and increase also after sintering because of the secondary phase that decrease. Based on our goal that you want to study the materials that you made previously and show some results. Now I want to present a model built by our fibers that was grown, and this is where I show you next. In order to prepare our model, we show you here the scheme that you use. So you have the oxide, powder mixture, and prepare the rods after melted and obtain the fiber. After that, we cut the fibers to form the legs of our thermoelectric model. The diameter was approximately 2 millimeters and the length was 4 millimeters for each pair. So you build the two pairs model, and N-type and P-type, and here is the scheme of the ceramic bases and the electrical contacts here that you can see. After the assembly, we have here the electrodes to make the connections. Was chosen this N-type and P-type was chosen two N-types. The calcium is doped with niobium and also doped with lanthanum. And P-type was the bismuth, barium, cobalt. Nevertheless, we had performed also the thermoelectric characterization to see if our fibers that we had grown for this bulk model was everything perfect. And what you see here is that bismuth, barium, cobalt have the same behavior as calcium, lanthanum, manganese, and while the niobium present the lower power factor. Also, in order to see how the materials react with the temperature, you have performed the dialectometry measurements and see that they are present the same dialectometry with the temperature. Is good because it gives the stability of our model in mechanical stress. In this case, we had performed our model with two pairs, as I told you previously, and here is the dimension square of 1 by 1 centimeter that is assembled and performed the electrical connections. We have performed also the voltage in open circuit to see how is the voltage that our model can generate, and you see that the model bismuth, barium, cobalt with calcium manganese doped with niobium present the high open circuit voltage, while the sample with the lanthanum present the lower. For this is the thermal gradient when compare the heat sides with the cool sides, while the cool sides will keep at maximum 30 degrees Celsius. Here you can see the power with the thermal gradient of our model and see that increasing the resistance of the charge or electrical charge, the power decrease. This is because the voltage is constant, but the current start to decrease. But we see what we want to show is that increasing the thermal gradient, the power increase. This is a characteristic of our oxide materials and with the application that we intend. Moreover, considering that the volume of our model and the power that it can generate, we are is the first best that we find in the literature for oxides. Is good because this was the first time that we make a model, so no optimization was done, and moreover the fibers was used as a ground. So if you sinter the fiber, you expect to increase this thermoelectric performance. This is next step that we do. So in conclusion, we see that the LFZ allow obtain good thermoelectric oxides and P-type materials. Applying electrical field during the growth improve the performance of the fibers. Sintering the fibers after growth improve their thermoelectric performance. And with this technique of laser processing allow us to tune the performance of thermoelectric because of the pulling rate. So with this technique, you are able to prepare new composition and opens, and was done a real mold test of PN type grow. Based on the efficiency of this model, give us a great potential of such approach when compared with another models. As future work, we want to increase the thermoelectric materials performance. So you want to use fibers after heat treatment. We're testing whether laser materials as N-type and P-type. You see the combination, as you see that Lanthanum and niobium is different. You want to optimization of the model fabrication to assess the optimal length, the number of legs, the area ratio to improve the electrical contact or to obtain a better thermoelectric model performance. And thanks for your attention.
Yes. Any questions? Any questions to Dr. Ferreira? Just if you have any questions, you can text in chat box. We'll be asking behalf of you. Yes, sir. Thank you. Thank you very much, sir, for participating by sending your video presentation. On behalf of organizing committee members of Material Science and Nanotechnology 2021, we want to thank you for your presentation. We're looking forward to meet again next time. Thank you so much for joining and for your attention. Next, we'll go with Dr. Santan Manu from Johannes Kepler University from Austria. Hello. Sir, okay.
Hello.
You can go with your presentation.
I see. Let me share my screen.
Yes, sir. So the topic will be gas quantum dot, a promising solid state quantum emitter grown by droplet etching, a novel growth technique.
Yeah.
Yes, sir.
Can you see my screen?
Yes, sir.
Okay. Okay,
Right.
so you can see the
Yes.
full screen, right?
Yes, yes, it's fine. Sir.
Okay. Nice. Hello, everyone. So I am Dr. Santanu Manna, now university assistant in Johannes Kepler University, Linz, Austria. So I will be talking about gallium arsenide quantum dot, which is a promising solid state quantum emitter, and it's by a novel growth technique. And so before continuing, so I want to express my thanks and appreciation to the organizers to give me opportunity to talk about my research. And this research is done in completely it's done in Johannes Kepler University, Linz. So there are many collaborators I will show at the end of the presentation. And yeah, so welcome everyone to my talk. So my aim is towards achieving a quantum internet. And we know that this classical transactions, like for money transactions, for like conversations, like for election voting, it's not so secure when it's classical. And when we go to quantum, it will be secure enough which will be secured by the principle of quantum mechanics. So if you have a key or some, let's say, one-time pad OTP, you cannot break if it is generated by some quantum system. So my aim is to get this quantum internet, where to get quantum communications between any points between 2 points on Earth. And for that, we need quantum nodes and quantum channels. And this quantum node will be used for generation and processing and storage of the quantum information, like 0, 1 bits. Of course, maybe you know that in classical, whereas in transistors, we use 0 and 1 bit, these 2 bits, but in quantum, there will be another one, like superposition of 0 and 1 together. So that is the advantage of these quantum things. And then the quantum channel, which can be used for the information transfer between different nodes. So different examples I can tell that one is secure communications via quantum key distribution. Then secure, let's say, secure access to quantum computers. Then blind quantum computing, like to prevent, let's say, if you want to compute something, so you are maybe using some cloud, some server. So maybe another server which can cheat your server, so that this blind quantum computing can be done to prevent that cheating server actually. Then we can use also the fundamental science and metrology applications. And for all of these things, we need this quantum bit. And this quantum bit can be generated by some solid state materials. And here we'll use photon as a quantum bit, which is also known as like flying qubit. So, and photons, one can use this the direction of electric field, like a polarization or time beam, as different degrees of freedom for this quantum bits. And as I am saying, this potential candidate for generating these photons. So mainly, I will concentrate on single photons and entangled photons. I will talk about later. But for generating entangled photons or single photons, the potential candidate will be some kind of solid-state quantum dot. So here I am showing some indium gallium arsenide quantum dot, which is embedded inside gallium arsenide layers. I will show later different kind of quantum dots also. So now, if I see, look at the state of art, so I can find many groups like in United States and also in Europe, mainly in Europe. So there are plenty of groups like Professor Senelar's group. This is from Cambridge, Professor Shields' group. Then this is from Professor Pellucci's group. Then Professor Peter Mikla's group in Stuttgart. Then Professor Julia's group from KTH Institute, Sweden. So they all are concentrated on these solid-state quantum dots. So, but Professor Mikla, so he is the one who showed that, okay, quantum dot can be used as a nice entangled photon source. And maybe someone, you know that Professor Jian Wei Pan from China. So he is known as the father of quantum photonics or quantum physics in China. And this recent satellite launch for making this entangled like some quantum key distribution, or let's say, yeah, this kind of secure things from satellite to the ground. So he's the one leading these projects. So, and he also thinks that the quantum dots can become the perfect source of entangled photon source compared to the SPDC source. SPDC source means a spontaneous parametric down conversion, which is now used for generating entangled photons. So I will describe anyway the entangled photons later on. Okay, so let me talk about my quantum dots, which I grow in this institute now. So this is a 3,5 molecular beam epitaxy chamber, which is a very high vacuum chamber. The base pressure is 10 to the minus 11 millibar of torr. And so 3,5 means, let's say I use gallium arsenide, which is a compound one, then aluminum gallium arsenide, gallium indium arsenide, something like this. So this is this molecular beam epitaxy is the finest or the best technique to grow. Like it takes time compared to chemical vapor deposition, but the quality is the highest. Like if you consider with respect to the mobility of the electrons or something like that. So, and also during you can do the epitaxial growth like layer by layer, which is lattice matched, and you can monitor by reflection height electron energy diffraction, you can check how the growth is continuing. So we know that mainly there are 3 different growth modes. Like one is layer by layer, and then another is island on the substrate, and then another is layer plus island on the substrate. So what does it mean? So let's say you have a silicon substrate, and you want to you want to deposit some germanium. So what happens that you have then since there is a lattice mismatching like 4.3% between germanium and silicon. So after few monolayers of let's say few monolayers of germanium, then it becomes like dot shaped, because it has to compensate this elastic strain to relax this one. So that's why it makes islands. So for, let's say, another example is if you deposit, if you grow some indium arsenide dot on gallium arsenide, it will be also nicely quantum dots because of the lattice mismatching. So that's why this kind of quantum dot. So you need this lattice mismatching. So if you have a lattice matching like here, so let's say if you have hello.
Yes, sir. You can go ahead.
Okay, so let's say if you have a system of aluminum gallium arsenide and gallium arsenide, so those are actually for all of these means aluminum concentration, these are more or less like a lattice matched. So then if you want to grow some quantum dot for this kind of lattice matching system, you cannot grow it. So what we have to do then, so we can grow like 2 different methods. We can use droplet epitaxy and droplet etching epitaxy. So what is this droplet epitaxy? Let's say you have a gallium arsenide substrate, then you deposit some aluminum gallium arsenide barrier, and then what you have to do, you have to sprinkle some gallium gallium metal flux. So it will be like a metal droplet according to this method. So here you have lots of lattice mismatching. So it will become directly island on the substrate. It's also the same. So if you sprinkle gallium on this aluminum gallium arsenide due to high lattice mismatching, so you will have this gallium droplets. Now you send some arsenic flux. So arsenic will be incorporated within this gallium, and you make gallium arsenide, and it will be crystallized. So you can get this gallium arsenide quantum dot. And this way you can get gallium arsenide quantum dot with the lattice matching system. But we have seen that this kind of epitaxy doesn't give you very high quality quantum dots, which we want for entangled photon generation. So that's why we use this technique, local droplet etching. So what do we use? How do we do that? So let's say we have a gallium arsenide substrate, and then we deposit the aluminum gallium arsenide. Then in absence of this arsenic, so we just sprinkle some aluminum and give some time. So then it becomes this aluminum droplet formation, like the last one we showed for gallium droplet. So here we are using aluminum droplet. Then we allow little bit of arsenic. Then what happens? Then this aluminum droplet will react with this aluminum gallium arsenide beneath this droplet, and it will make nanoholes. And these nanoholes can be filled. Then we deposit gallium arsenide so that these holes will be filled, and then we deposit another aluminum gallium arsenide so that your this type 1 structure is complete, and you have an optically active structure. So let's see. Okay, let's say this is an aluminum droplet, and this is a substrate or aluminum gallium arsenide. Then if you give some time, then it etches like this. So you have a droplet, and then it's etching beneath this one, then etching, and then yeah. So then it just etches like a very symmetric nanoholes. And this is a, let's say, 3D cross-sectional view of this kind of quantum dot. Now, like if you fill gallium arsenide until this one, so you can see that it's perfectly symmetric nanoholes, and you can see that this is a nanohole on the surface, and the density is quite less. I'm going to talk about the density now. So let's say we grow germanium quantum dots on silicon substrate, and you can see that the scale is 200 nanometer, and you see plenty of quantum dots. Of course, if you give some annealing, then it will be agglomerated quality and it will be broader and the density will be less, but still it will be very high. This is for indium arsenide, quantum dots, and gallium arsenide. And we can see that in both cases, the density is pretty high, so that you cannot very nicely excite only one single quantum dot. But whereas for our this gallium arsenide quantum dot, which is grown by this local droplet etching epitaxy, you see that the density is quite less than even 0.5, or in this case it's 0.2. So that means this area you can very nicely excite with the laser spot. You can excite only one quantum dot. And okay, let's check the band diagram of a quantum dot and about the carrier recombination. So generally, this is aluminum gallium arsenide. This is gallium arsenide. This is aluminum gallium arsenide. It's a type 1 band structure. When this barrier is X, the aluminum concentration is less than 40%. So in that case, let's start from here. Let's say you have an electron in the conduction band and you have a hole in the valence band. So it makes an exciton. If you have two electrons here, two holes here, of course, a spin up and down to include the Pauli exclusion principle, then this is called a biexciton. It's a pair of two excitons. It's a biexciton. Let's say you have two electrons here, one hole here. So you have one electron more in the system. So it will be X minus. So if you have two holes here, one electron here, it will be X plus, because now you have one plus charge, surplus charge in this total system. And let's say if you excite one of this hole to the exciter level here, then you get X2 plus. You call it X2 plus. So now let's say we will concentrate to this system, XX and XX. And let's say for this kind of system, let's say one pair, let's say spin up and spin down, it combines and gives a photon emission. Then after this pair recombines, then it will be the time for another pair to recombine. So that means it can be a cascade, one after another. So let's check how this entangled photon can be generated. So as I have shown here, let's say you have this exciton, you have this biexciton, right? So we can represent like this. You have a ground state, you have an excitonic state, you have a biexciton state. So now let's say one biexciton. So from you excite by something, some laser, then this biexciton decays to exciton state, giving one photon, let's say. Then it will be another one, then another will be exciton to ground state. That means one photon you can generate, then it will be for another one. So this will be one kind of photon cascade. So we call it biexciton exciton cascade. So now the thing is, let's say, so it can happen that if it emits right circularly polarized light, then this one will be this one will be left circularly polarized, and also vice versa. Now, if these two paths, let's say if this excitonic level is degenerate, means it has the same energy, so then these two paths you cannot distinguish that which path it decays. So then what happens? Then these photons, this right circularly polarized and left circularly polarized, they become entangled with each other. Now what happens, let's say if due to some interaction between electron and hole spin, you have some let's say now this excitonic level is no more non-degenerate, it's now it's no more degenerate, it's now non-degenerate, so it's splitted with some energy, let's say fine structure splitting we call it. So then what happens, this energy and this energy, you see this energy and this energy are different. So that means now you can distinguish two paths now. So that means now this exciton and by exciton decay cascade is no more like these two photons are no more entangled. So but let's say if we decrease this fine structure splitting, we can at some point we can get this entanglement. And when we can get it, when this fine structure splitting is comparable to the line width of this photon actually. So what happens for this for our quantum dot? So we make it very much symmetric to make this fine structure splitting very negligible or to be completely zero. So then we can get a very nice entangled photon. Whereas for indium arsenide dot or some other dots, we cannot get so much. Like let's say we cannot get non-zero fine structure. So for local droplet etching, it's much better. So let's see. So this is the emission photoluminescence emission spectrum from only one quantum dot. So this is a neutral exciton, and this is the charged excitons like X plus, X2 plus, something like this. So so here I cannot see this by exciton. For to see the by exciton, we have to excite by a resonant excitation. This is by an above bandgap excitation, which is a non-resonant excitation. And this is the distribution of our quantum dot. You can see that we have, let's say, 6 nanometer of distribution of the quantum dot emission, because this quantum dot depth can be a little bit more or less. So you can have a distribution of the emissions. And this is the fine structure splitting. So you can see that the mean is 2.5, standard deviation 1.3 microelectron volt. And we have a handful numbers of, let's say this is 60, total 60 dots. And we can get like 10 dots within below 1 microelectron volt. And the Fourier limit of a quantum dot is like 2 or 3 microelectron volt. So that means that we can get a very nicely entangled entanglement ready quantum dots actually. So but the problem is when you have a solid state material, like its refractive index is, let's say 3.3, 3.5. So you cannot extract light very nicely when you have a quantum dot inside because of the very high index compared to the air. So then what we have to do, we have to grow some DBR, distributed Bragg reflector, which is a kind of a dielectric mirror, which is also epitaxially we grow by our molecular beam epitaxy machine. So this is like some refractive index difference, aluminum 20, aluminum 95%, and it's this quantum dot is sandwiched between one lambda cavity, and you can extract a handful amount of light compared to without any kind of distributed Bragg reflector. So this is and also we put a solid immersion lens on the top. The solid immersion lens will like help like 3-4 times more to extract light actually. And this solid immersion lens is like zirconia lens, zirconium oxide, ZrO2, and it has a refractive index at 780 nanometer, like 2.1. And we can also use a gallium phosphide solid immersion lens, which has the refractive index of 3.5, and it will give like more extraction efficiency. So you can see here that this is without a solid immersion lens on the top, and this is with seal on the top, and with different numerical aperture. It's nothing but the solid angle, okay? So this is the corresponding this angle from the normal actually. So you can have quite, you see, 10% more efficient when you put a solid immersion lens, of course, as told by, I think this lens, all means this kind of lens is now used by everyone to extract the emissions. Also, there can be different strategies to increase the photon collection efficiency, like antenna. So let's say we have this gallium arsenide, aluminum gallium arsenide membrane, and we put a metal below, a reflector, and a top semi-transparent metal, so that it works like a Yagi-Uda antenna. And we can see that we have a very nice extraction efficiency, let's say at 40 degrees angle from the normal. So that means, let's say 0.65 numerical aperture. And this is a very nice technique, because you have plenty of quantum dots, and you do not have to do deterministic positioning of the quantum dots. So you can access all of the quantum dots. And there is another strategy to collect very nicely, which is the best one till now, till date. So this is a circular Bragg grating, which is also called a bullseye cavity. So you have a second order grating, which can outcouple very light vertically very nicely. And you have an impurity, or let's say a cavity bullseye at the center. So in this way, you can collect like more than 90% all over this wavelength range where our quantum dot emits. And then also we can have a very nice Purcell factor. So this Purcell factor is nothing but the emission rate of the quantum dot inside this kind of cavity with respect to when it's within a homogeneous medium. So this is a technique now everyone is using to get more parcel factor and also high extraction efficiency. So let's say that we have plenty of quantum dots, right? So this is a 50 by 50 micrometer, this area, and you can see that we have a kind of setup. So we have an infrared LED to illuminate this marker. You can see this black one, and then we have a blue LED which can excite this quantum dot, and you can see each and every individual quantum dot, and you can go by nano positioner. You can go, I say that, okay, go to this quantum dot and measure the spectrum. Then it goes to this quantum dot, only one quantum dot, and it measures the spectrum. So as usual, you can see a very nice neutral exciton line, and this is charged exciton lines here. So then, and I can, since I know this coordinate of these lines, let's say this 1, 0, 0, then I can easily find out the coordinate of this one. Then I can put this one at the center of this one, and I can write this circular bracketting around this, and then I can collect very nicely the extraction efficiency, parcel factor, everything, as I have shown in the earlier slide. So let's go to the entangled quantum key distribution, which is very important. Let's say that this is a photon, entangled photon source, which is a quantum dot. Then we have an let's say an polarizer analyzer like this, and we can collect horizontally polarized emission, let's say exciton. Actually, we have seen that exciton and bi-exciton both are entangled. Okay, so that means, let's say we send exciton to this direction, bi-exciton to this direction. Now this exciton we can measure by a horizontal polarizer, vertical polarizer, diagonal polarizer, and anti-diagonal polarizer. It's not a polarizer. Let's say we select by lambda by combination of lambda by 2 and lambda by 4 and other polarizer. So let's say it's horizontally polarized. This is vertically polarized. This is diagonally polarized. This is anti-diagonal polarized. So we call it 0, 1, 0, 1. Now let's say this exciton we measure with me. So we get this kind of bits 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, and I measure in this kind of basis. So this is rectilinear basis. This is diagonal basis. I measure in rectilinear basis, and I get 1. That means I get the click on this vertical detector here. So similarly, let's say this is my diagonal one, and I get a click at 0. That means I get a click at this diagonal polarized light actually. So then it's the same like for 1 means here I get this one, this one. So now the bi-exciton, which is entangled like to a twin brother. So this is sent to another lab. So this is generally called Alice. This is called Bob. And this Bob, let's say Bob measure also in his polarization basis, let's say diagonal and rectilinear basis, and he measures 0, 0, 1, 1, 0, 0, 0, 1. And let's say he gets also the basis. He knows that the basis is like he measured this 0 is for this one, then 0 is for this one, 1 is for this one, something like this. Then what it does, so then Bob send this basis and the timestamp to Alice to compare, so whether which one is matching with my key. So I can see that this is not matching, this is not matching, because you see, because this is different, or also the basis where we measure is different. But here it matches completely. Here it is matches, here it matches. So the basis and this one which matches, so we keep those bit values. Okay, so that means we keep 1, 0, 0, 0, 1, 1. And then I send this one. I do not send this bit, but I send the time stamping corresponding to these bits to Bob to check which one matches with him. So then we check that, okay, these two bits are equal, and we can keep this as our key. Now this will be like a OTP. So let's say 10011 is our OTP, and we can use that kind of OTP to let's say we have this virus picture, and we can use that kind of key to encrypt this one by a XOR gate, and we can encrypt it, and you cannot see anything here, and no one can break, even by quantum computer you can break this image. And when you use the same key to decrypt, then you can see this one. Now Alice can see this image, Bob can see this image, because both has the same key. Okay, and so this is done by, let's say, a quantum dot here. So we send this we kept, let's say we kept exciton with us, and by exciton sent to other lab, and then we did this kind of key exchange, let's say bit exchange, and then we match it, and then we check it, and we compare it, and when the keys are similar, then we keep it, and we use that key for the quantum encryption. And this key, let's say if you have a secret conversation, if you have, let's say, conference, you can use this OTP to use it as password or something like that, and no one can break it. So, and as I told you before, this kind of solid state quantum dot can generate this kind of entangled photons, and for that one, the main parameter is the fine structure splitting. So you can see that it's very less than 1 microelectron volt, and let's say we have a Fourier limit of line is like 2.3 microelectron volt. It's quite below, so that's why it's showing entangled. Let's say that if it is 5 microelectron volt, it will not generate entangled photons. So that's why in that respect, our quantum is now the best in the world, and we are generating this one by our molecular beam epitaxy machine. So, but the problem is, you know that for a quantum dot, a solid state quantum dot, a colloidal quantum dot, it has always blinking. That means you excite by laser, some light, it emits some emission, it gives some emission. After some time, it stops. So that means that time it becomes optically inactive. After some time, it again becomes active. So you can get this kind of curve, decaying curve in the second order correlation. If you measure the second order correlation of a, let's say, of a photon, let's say exciton or by exciton, you can see that at 0 time it has a peak, and then with time it saturates. So it decreases because of this blinking phenomena. So if we divide, let's say saturation point, if I normalize this one as a 1, this is the saturation one, then it will be, let's say, for our case, it's 3. So that means if I divide 1 by 3, then it's 33%. So we have a 30% on time fraction. That means 70% our quantum dot is off, and this is very bad. So for that one, we need to charge stabilize the environment of the quantum dot. And if we do that, we can make like blinking free quantum dot, which will be like 100% on this quantum dot. And we can put inside this quantum dot inside a PIN diode, and we can make it. So so this is the kind of structure. So we have a distributed Bragg reflector, and we have an n-doped layer. Then we have a quantum dot, and the tunnel it's separated by a tunneling layer, and we have a p-type. So then you can sequentially charge, like, so this is like an electron reservoir, and you can sequentially charge the quantum dot one after another. And let's say the band diagram. Let's say this is an N site. So you have an electron reservoir, and this is your quantum dot. So now when we apply the voltage, so let's say positive voltage, then this goes down, then this aligns with this let's say ground state. Then you can put one electron from here to the quantum dot. You apply more voltage, then you put another electron. So that means you let me go through this one. So that means, let's say you do not have any electron inside, but then you put one electron, then you put two electrons inside the quantum dot, and you can, when you can excite by a laser, you can get the emissions. So this is let's say our quantum dot, and we generate exciton and by exciton by sending a resonant laser, and you can see this one is completely flat. This is the G2 values. This is completely flat. This is at 5 Kelvin. This is at 30 Kelvin. It's completely flat compared to the last one. So this means that our dot is now blinking free when we put inside a PIN diode. Here you can see the comparison together. So this is without diode. So which one I have shown before. So now this is completely flat. So this has many implications now, because now your quantum dot is 100% on, and this way we can get this key rate actually. So key rate, like if you excite by a pulse laser, let's say 1 megahertz, then you can get 1 megahertz counts like that. But when you collect, of course, there will be losses. So this is a recent laser where recent result where we got the quantum key distribution at higher temperature, like 20 Kelvin. We have this PIN diode. We have this dot inside. Then we have, of course, this seal zirconium oxide seal on the top. And let's say we keep by exciton with us, send exciton to the other lab, and check these keys, match these keys, and then we get these encrypted keys. And then let's say we have a virus image, then we encrypt with this with that key or a OTP, and then we decrypt. We can decrypt by that the same key. So this image is also no one can break, even a quantum computer cannot break. So summary, so gallium arsenide quantum dot grown by local droplet etching comes out to be an on-demand single as well as very nice entangled photon source. And local droplet etching using molecular beam epitaxy produces very gallium arsenide quantum dots with very excellent optical properties. And we have used this gallium arsenide quantum dot for entangled photon source for quantum key distribution using entangled protocol, which is known as BBM92 protocol. We are working on the exciton dynamics of the quantum dot so that we can use these quantum dots in a Starling cooler. So now you can see that we can get at 20 Kelvin. We want to get at 30 Kelvin so that we can make use inside a Starling cooler, and we can send to a space satellite for using this kind of source for entanglement distributions. And we are working on extending the quantum dot emission towards the telecom C band, which is 1550 nanometer. And you know that, all of you know that all of this fiber optics is for 1550 nanometer, which has very low loss. So that's why we want to grow some dots, which will be giving emission at telecom C band. And we make quantum key distribution with that kind of dots. And I acknowledge to my boss, Professor Armando Rastelli, and my whole group here in JKU, and then University Roma Sapienza, University of Wien, Vienna, and also FWAF for sponsorship, and then European Horizon, then LIT Secure and Correct Systems Lab, and of course JKU from I am getting funded. Thank you very much for listening.
Yes, sir. Yes.
Yeah, please, some questions.
Yes, any questions to Dr. Santano? Any questions? Just if you have any questions, you can text in chat box. We'll be asking behalf of you. So thank you very much, sir. Thanks for sharing your topic in front of all this. Looking forward to meet you again next time.
Okay,
thanks.
sure.
Yes,
sure, thank you very much.
Yes, yes. So you'll be getting the soft copy certificate as well as electronic book within a couple of days, sir, after the completion of the conference.
Okay, thank you very much.
Thank you. Thanks for taking time out of your busy schedule. Next, we will welcome Dr. N. Gokarnesh, SNS Rajalvanshi College of Arts and Science from India to join the event and start presentation.
Good afternoon.
Yes, sir.
Am I visible?
Yes, sir, it's fine.
Okay, very good afternoon to the organizers and the participants. Now, my topic will be on textile applications of carbon nanotube. As you may all be aware that nanotechnology is gaining more prominence in all areas of science and technology. So, this carbon nanotube is an important aspect of the nanotechnology. This carbon nanotubes are also known as CNT. They find a wide range of applications in various fields of science and technology. Now, I'll be confining my discussion to the application of carbon nanotubes in the field of textiles. Okay. Now these carbon nanotubes have a speciality in that their diameter ratio is more than 10 lakhs. So various methods have been evolved in the manufacture of CNTs, that is carbon nanotubes. So these carbon nanotubes that are produced have potential applications in areas like nanoelectronic, biotechnology, material science, polymer, composites, and textile industries. Now, when we consider the area of textiles, the carbon nanotubes result in the manufacture of a broad range of conductive textiles having various electrical properties. Now, the wear performance of fabrics applied with CNT to open the potentiality of producing composite materials for conventional and innovative applications that range from conventional apparel and sportswear up to protective clothing, heat clothing, automotive textiles, building, covering, geotextiles, biomedical textiles. So as you can see, largely these carbon nanotubes are being initially they have been applied for textile applications, that is for dress materials and all. Now their area of application has increased so much that they are being used in the area of technical textiles. Now this technical textiles has come up like anything in the field of textiles. Lot of research has been done. There are various segments of technical textiles like agricultural textiles, medical textiles, sports textiles. So many segments are there in technical textiles. Lot of research has been done, and carbon nanotubes fit into the various areas of technical textiles. Now let's have a glimpse into the CNT structures, that is the structure of carbon nanotubes. Now basically, carbon can form different structures with sp2 hybridization. The chemical bonding of nanotubes is composed entirely of sp2 bonds, which are similar to those of graphite. Now these bonds are stronger than sp3 bonds, and they provide nanotubes with having their unique strength. Now besides the popular graphite, carbon can build closed and open cages with honeycomb atomic arrangement. So the structure of the carbon nanotube is something like a honeycomb-like structure. I'll show you the figure that will make you more clear. Now the first such structure was the C60 molecule. All the various carbon cages were studied. It was only in 1991 when it was observed for the first time that tubular carbon nanotube structures have been discovered. Now nanotubes are members of the fullerene structural family. They get their name from the long hollow structure with walls formed by one atom thick sheets of carbon, which are known as graphene. So we can fundamentally classify the nanotubes into two categories, namely the SWNT, that is single walled nanotubes, and the MWNT, known as multi-walled nanotubes. Now I'll show you the figures for these single walled and multi-walled. You can see here one more. You can see the structure, the single walled carbon nanotube and the multi-walled carbon nanotube. You can see the difference between the two. It's visible in this figure. I hope all of you are able to see. Now, when we consider this SWNT, it comprises of a single graphite sheet that is seamlessly wrapped into a cylindrical tube. Now, the majority of SWNTs have a diameter of about 1 nanometer, but can be more very often. The structure of a SWNT can be imagined by wrapping a 1 atom thick layer of graphite called graphene into a seamless cylinder. So the nanotubes comprise of many tens of graphite cells that are known as multi-walled carbon nanotubes, known as MWNT, with adjacent shell having high length diameter ratio. Now, two structural models of MWNT are parchment model and Russian doll model. In parchment model, it is the same as a rolled up scroll of paper sheet. A single graphene is bored around itself many times. But if a CNT contains another nanotube inside it and the outer nanotube has a greater diameter than thinner nanotube, it is called as Russian doll model. Now there are different methods of manufacturing these carbon nanotubes. Though so many methods are available for the manufacture of carbon nanotubes, there are some popular ones that are used widely. And these comprise of the arc discharge technique, the laser ablation technique, high pressure carbon monoxide disproportion technique, and chemical vapor deposition techniques. These are the popularly used methods of producing the CNTs. Now, most of these processes take place in a vacuum or with process gases. So the chemical vapor deposition growth of CNTs can occur in vacuum or at atmospheric pressure. So large quantities of nanotubes can be synthesized using any of these methods mentioned or techniques mentioned. Now you can see here the simple chart showing the different methods of carbon nanotube manufacturing. Now let's look into the properties of the carbon nanotubes. The carbon nanotubes have unique electrical properties, heat conduction efficiency, stability and resilience, and very outstanding strength. So the CNT structure has a great influence on the electrical properties of nanotubes. Now nanotubes are capable of being superconductors at low temperatures. So the cause of this arises because of the carbon to carbon sp2 bonding in the CNT. They have high stiffness and axial strength, and they are the stiffest known fiber with a high Young's modulus. Now the CNTs have expected elongation of failure of 20 to 30%, which combined with stiffness and the tensile strength is more than 100 GPa. So CNTs have incredible mechanical properties. So they are the fastest known oscillators and are very well suited for building blocks for molecular electronics. The carbon nanotube has thermal properties that directly relate to their unique structure and small size, and they are ideal materials for thermal management studying. So all nanotubes are good thermal conductors along the tube, that is ballistic conduction, but they are good insulators lateral to the tube axis. Now let's look into the application areas of the carbon nanotubes. Now the carbon nanotubes or the CNTs have outstanding structural, mechanical and electrical properties, and this enables them to be used in various fields of applications such as medicine, manufacturing, nanotechnology, electronics, construction, polymer, textile, and so on and so forth. So these CNTs find use in energy storage and energy conversion devices, high strength composites, hydrogen storage media, actuators, nanoprobes and sensors, electronic devices, and catalysis. You can see here this figure depicts the varied applications of the carbon nanotube. As you can see, electronics, polymer, textile, construction, material, nanotechnology, biotechnology, medicine, manufacturing, and other fields of applications as well. Now we will look into the role of CNTs with relevance to nanocomposites in textile. Now, these carbon nanostructures, such as carbon nanotubes, have a wide range of potential applications, and they have attracted great interest because of their unique anisotropic properties. So the outstanding properties of the carbon nanotubes have consistently attracted a lot of research interest. Many researchers have been attracted towards the properties of the CNTs. So there is great interest and activity, and a lot of research is being done in the areas to explore newer and newer areas of applications for CNTs. Now, when we consider SWCNTs, that is single wall carbon nanotubes, they have similar electrical conductivity as copper and similar thermal conductivity as diamond. This is an interesting aspect you have to note. So the composite fibers using CNT have potential applications in various industries. So the CNT can be applied to the fabric by different techniques, and the important ones being spray coating, exhaustion, or simply dipping into the textile into a CNT solution. Now this figure gives you a good idea about the textile applications of the carbon nanotubes. So it gives you a overall picture of how the carbon nanotubes are used in the applications are used in the textile industry. That is water or oil repellents textiles, UV protection textiles, fire retardant textiles, reinforcements, EMI shielding, filters, sensors, antimicrobial textiles. Then you have super capacitors, then crease resistant fabric, conductive textiles, scaffolds. Scaffolds means it's nothing but medical area, tissue engineering. So this tissue engineering is useful mainly in the cancer oncology research and other related medical researches. Scaffolds are growing very popular, particularly in oncology and other related tissue, where tissue growth culture is developed. Then they are used in textile wastewater, that is effluent. The textile industry, effluents are discharged, they are wastewater. They contain dyes and chemicals which are harmful for animals and plants. So they are used for treatment of, they are used to render the textile wastewater or effluent water less harmful. Also by different fabrication processes like wet spinning, carpet spinning, and aerogel spun methods, the carbon nanotubes have been assembled into macroscopic yarns or fibers. They are made into the form of yarns or fibers by various techniques. Now the carbon nanotubes could cover a wide range of textile functions, which we'll discuss here. Now when we take the area of conductive textiles, so the materials that only consist of carbon atoms such as graphene, carbon black, and carbon nanotubes can have a wide range of conductivities from the insulated diamond to conductors. So the purity of the carbon compounds is an important factor for conductivity level. So in order to produce electrically conductive fibers, yarns or fabrics, many methods are being used. Also, different electrically conductivity materials such as metal powders, graphite, carbon black, carbon nanotubes, or intrinsically conductive material polymers like polyaniline, thiophene, and polypyrrole can be used. Now for the fabrication of intelligent clothes, which are applicable in military, workwear, and sportswear, portable power, foldable displays in healthcare, integration of electronic elements, and conventional textiles, it is important and essential. So a good deal of research has been done on the electrical conductivity of the fibers and fabrics using carbon nanotubes, and the findings of the conductive textiles have been reported by various researchers. Now there are different pre-treatment methods like oxidation by potassium permanganate, enzyme treatment and protease, and nano titanium dioxide finishing that have been investigated well. So anionic and cationic surfactants, namely sodium dodecyl sulfate (SDS) and cetyl trimethyl ammonium bromide (CTAB) have been used to provide the best conditions for dispersing the nanotubes. It is concluded that CTAB has been more effective for dispersing MWCNT, that is multi-walled carbon nanotube in water. Wool sample has been pre-treated with protease and treated with 5 gram per liter of CMWCNT, and it is possible to achieve highest electrical conductivity. Then in another interesting research, PET fabrics, that is polyethylene terephthalate, that is nothing but polyester. Polyester is chemically polyethylene terephthalate. So polyester or PET fabrics have been modified by coating with MWCNT. Now the nanotubes have been deposited using the padding technique on fibers surface from water suspension. So the treated materials were flexible and easy to shape, and also the conductivity of network was durable. Another interesting research reports on the polyethylene imine used for pre-treating the cotton yarn to enhance the affinity of CNT for the yarn. So due to the density variation of SWCNT, the yarn that is obtained can be used as chemical resistors which demonstrate electrical response to ammonia gas at room temperature. So the functionalized yarn can possibly used to produce wearable sensors. Another interesting area of research, the conductive properties of polyester cotton woven fabric has been investigated with a spatial network of carbon nanotube that was formed on its surface. Now the conductivity of the PET or CO woven fabric depends on the quantity of the carbon nanotubes deposited on the fiber surface. Studies have revealed that it is possible to obtain electroconductive and hydrophobic composite fabrics that find applications in many industrial areas. So this diagram shows the manufacturing of the MWCNT MHV cellulose composite fibers using wet spinning process. Now in spinning these fibers, 3 techniques of spinning are used. That is dry spinning, wet spinning, melt spinning. So the wet spinning technique has been adopted in manufacture of the multi-walled carbon nanotube cellulose composite fibers. High electrical conductivity has been achieved. So other researchers have reported electrospinning technique for large-scale production of CNTs based composite films that can be used. Carboxylated multi-walled carbon nanotubes, then polyvinyl alcohol nanofiber mats have been produced. Melt extrusion technique, that is melt spinning technique, already I told you 3 spinning technologies are there, that is dry spinning, wet spinning and melt spinning. So the melt extrusion method means melt spinning technique that has been used in one area of research to coat polyester yarns with polypropylene and multi-walled carbon nanotubes. So a certain level of electrical conductivity has been reported. So the processing technologies can prepare polypropylene multi-walled carbon nanotubes coated with PET conductive yarns, which have satisfactory electrical conductivity and can be used in functional woven and knitted fabrics, that is wearable electronics and battery heated armor. So you can see the procedure for the diagram is representing the how the coating is done. The carbon nanotubes, how they are coated on to make a conductive yarn. This is the PET yarn. You can see this is the PET yarn, and this is a coated layer. You can see the bare PET yarn, polyethylene terephthalate yarn or polyester yarn, and how it is being coated with the multi-walled carbon nanotubes as a coating layer on the yarn. So the research findings reveal that most of the research is related to electrical conductivity of fabrics. MWCNT can be used for the purpose. So by these methods, conductive yarns and fabrics that have satisfactory electrical conductivity have been prepared, which can be used for electric and electronic equipment industry. The weight concentration of CNT is a very important factor. And one interesting aspect to note is that CNT treated materials, textile materials, have great potential for smart textiles. So nowadays, the smart textiles have gained a lot of importance. Smart textiles is a very important area of the technical textiles, smart textiles. So carbon nanotube treated textile materials are used in a varied forms of smart textiles. Then supercapacitors, another area. So during recent years, researchers have shown interest in producing flexible, lightweight, and implantable energy storage system to address the energy supply problem of wearable electronics. So wearable electronics ranging from high performance sportwear, military garment devices, and personal health monitors to wearable computers. So there is a great need, immediate need to develop mini-sized and lightweight energy storage system for wearable electronics. So electrochemical capacitors, which are called supercapacitors, can store energy using ion absorption or desorption at the electrolyte surface near surface reversible reactions. So textile supercapacitors are typical sorts of examples of such kinds of novel energy storage devices, and they have been designed by either directly converting the textile and fabrics into electrically conductive and electrochemically active and carbonization by coating with fibers with functional thin film layers like carbon nanotubes. So researchers have found that there is excellent electrochemical properties that have been attributed to the nanostructure and synergetic effect of each component. Lightweight and highly conductive membrane substrate have been developed. The substrate was based on CNT, ethylene vinyl acetate copolymer, and lens wiping paper. They are used in supercapacitors. EVA and 40% by weight of CNT paper hold great promise of low cost, lightweight, and high performance flexible energy storage applications. Such textile electrodes necessarily maintain its whole structural integrity. Then sensors. Another area is sensor. CNTs are attractive nanomaterials for variable sensor fabrication due to their unique properties such as ultra weight, high aspect ratio, high electrical conductivity, high mechanical strength, and high thermal conductivity. So CNT sensors are functional, flexible, and ideal for energy saving. Then another important area is EMI shielding, electromagnetic induction shielding. So in a polymer nanocomposite, the EMI shielding effectiveness depends on the concentration of conductive filler, electrical conductivity, and formation of conductive networks. Now, research have been directed towards electromagnetic shielding fabrics that have been produced by knife over roll coating and using combinations of CNT, metal nanoparticles, and conductive polymer. So silver nanoparticles, nickel coated carbon fiber filler, MWCNT and polypyrrole nanoparticles have been used as conductive materials. It has been possible to achieve EMI shielding of 95 to 99.9%. To that extent, electromagnetic shielding has been achieved. Now the next area is fire retardant textiles. Carbon nanotubes are flame resistant and thermally anisotropic. So the CNT can conduct heat along the axis of an individual tube. So they are relatively insulating across the tube's diameter. So the anisotropic behavior of CNT is useful in firefighting, and they can combat firefighting, exhaustion and heat stress. So carbon nanotube embedded textiles like cotton fabric are more flame retardant and thermally stable compared to raw textiles or untreated textiles. So direct utilization and stabilization of CNT resulted in achievement of high efficient flame retardant finishing of cotton fabrics with improvement of its thermal properties. So carbon nanotubes can be used for improving the flame retardancy of textiles and composites. Next, we consider the crease resistant fabrics. Now, what is creasing? Basically, creasing is nothing but the folded configuration of the fabric. It's called creasing. So a fabric should be ideally crease resistant. It should not get folded. It should be straight. This is what we mean by crease resistant. So crease resistance finishing of fabric is very important. By penetrating carbon nanotubes and carboxylated CNTs into cellulosic chains of cotton fabrics, crease resistance and strength of cotton textiles have been improved. So crease recovery angles have been measured in research studies relating to crease resistance properties. So various crease recovery angles have been recorded. Generally, crease resistance of fabric is measured in terms of crease recovery angle. Okay. So different types of materials could have different crease recovery angles. For raw cotton, it has been tested and various crease recovery angles have been reported. The values are given here. Now, researchers in this area conclude that cross-linked cotton has better crease resistant properties than CNT embedded cotton, has CNT concentration lower than 1500 ppm. However, by increasing the concentration of CNT to more than 250 ppm, the crease resistant properties of CNT embedded cotton are better than raw cotton. Now, another area is reinforcements. So CNT is introduced into fiber reinforced polymer composites. So CNT is the effective filler that can improve the polymer properties. Now, when we consider ballistic protection, a new kind of polyurethane or P-aramid multi-axial fabric composites with improved dynamic mechanical properties have been investigated. So in order to enhance the properties of the composites of polyurethane or P-aramid, that is para-aramid multi-axial fabrics, oxidized CNT and modified silicon dioxide nanoparticles have been added. So these have had a great influence in improvement of thermomechanical properties of the composites. The mechanical properties of CNT fibers improved due to enhanced crystallinity and interfacial interaction between CNT and aerogel by thermal treatments. One area of research points to that way. So there is better wear resistance of the MWCNT or epoxy composite, which arises due to the high mechanical property and dispersion quality of CNT in epoxy matrix. Now, next area we can consider is the water or oil repellents textiles. Now, because of CNT nanostructures, the aligned carbon nanotubes have super hydrophobic properties. So this is used to advantage in the development of water or oil repellents textiles. The repellents can be measured in terms of contact angles, which the water or oil makes with the fabric surface. So contact angles can be more than 15 degrees, which indicate the repellency effect or resistance effect. Next is UV protection textiles. So inorganic UV blockers are chemically stable and toxic. So nanoscale semiconductor oxides efficiently absorb and scatter UV radiation. Now contact fibers that have been functionalized with CNT using surface coating methods. This kind of CNT can improve the UV blocking properties of the polymer materials. However, one disadvantage that is associated is the coloration effect is reduced. That is, the color shade of the fabric gets affected by coating CNT. Cotton fabrics are known to become black after the treatment. That is one disadvantage. If they have some color shade, means that color shade gets blackened. Now, in order to reduce the coloration effect of CNT on textiles, it is advised to combine CNT with other UV blocking additives. So SWCNT and MWCNT can be introduced in UV protection finishing for textiles. Then another important area is biological applications. So CNT in polymer matrix have been studied for biomedical applications very recently. So with regard to MW and T, they are used in biomedical scaffolds. Now, as already I have mentioned earlier, the very basic structure of the carbon nanotubes is that of honeycomb-like structure they have. So owing to this kind of structure, special structure, they have very good potential for scaffolds and tissue engineering. So researchers have designed electrolyte-free muzzles with guest-filled twist spun CNT yarns. Polymer or carbon nanotube fibers can be produced by solution, that is, as I already mentioned, wet, dry, dry jet, or gel spinning, or even weld spinning. Then shape memory polymers can be used widely in many areas such as textiles and may have good shape fixity but do not have enough elasticity and water vapor permeability. The conductive fillers like CNT can improve the thermal conductivity of shape memory polymers that contribute to a fast response. Now, when considering one type of shape memory polymer, a study has been done on fibers that contain a large fraction of CNT embedded PVA, polyvinyl alcohol, which enable to obtain the highest recovery stress of shape memory polymer composites. It has been found that the achieved fibers have multifunctional applications that are suitable for industrial fabrication. Then coming to the area of textile wastewaters, how CNTs can be used for treating textile wastewater or effluent waters. Safe drinking water is highly desirable for mankind, as all of us know. So available supplies of water are decreasing and researchers are sincerely probing options for water such as wastewater and industrial wastewater. They are finding ways to effectively treat wastewater and industrial wastewater so as to make availability of safe drinking water more readily available to mankind. So one researcher has investigated a method for the removal of a bacterium called Escherichia coli from water using as produced from modified or functionalized carbon nanotubes under the effect of microwave radiation. By merely using CNT, there has been a low removal rate of 3 to 5% of the E. coli bacteria which was present in the wastewater. But by combining it with microwave irradiation, the unmodified CNT were able to achieve removal rate up to 98% of bacteria from water. You can see what a big difference it has made. So high removal of bacteria up to 100% was achieved when CNT and C18 was used in the same conditions. Textile waters are mostly non-biodegradable and toxic. So for treating the environmental pollution, semiconductor photocatalysis can be used. One of the most important photocatalysts are titanium dioxide, but it has the drawback of narrow light response range and low efficiency. Combining titanium dioxide with CNT can increase the photocatalytic activity. Now the SWCNT can be used for commercial purpose in the textile wastewater treatment, and there are potential absorbents that are used for removal of dyes, and also by growing the nanotube diameter, the binding energy between dyes and dye substrates. Then they are used as filters. Fabrication of carbon nanotube filters using electrodynamic deposition of aerosolized CNT at room temperature has been reported. Antimicrobial activity of CNT. There is increasing need for antibacterial materials and fabrics in many applications. So highly purified single-wall carbon nanotubes exhibit strong antimicrobiality, and it was first evidence that was found. CNT have fibrous shape with large accessible external surface area, high aspect ratio, and well-developed mesopores. It has been found that longer SWCNT exhibited stronger antimicrobial activity at same weight concentration. The aggregation between bacterial cells and CNT caused the cell death in the bacteria. The effect of plasma pretreatment on absorption of carboxylated carbon nanotubes on surface cotton fabrics have been investigated. So it has been found that plasma treatment is effective on improving CNT absorption by cotton fabric. Also, antimicrobial activity of cotton fabric when modified by low temperature plasma and stabilized with CNT has improved. You can see here how the coating of the coating of plasma coating on CNT fabric. Finally, we can deduce that from all the discussions, we can finally deduce that carbon nanotubes are highly conductive, lightweight, and owing to distinct physical and chemical properties, they have created new interesting field in textile industry for further studies. So they are useful, CNTs are useful for design of conductive textile composites. Carbon nanotubes are promising candidate due to their special properties. Then CNT coated textiles have wide applications in wearable electronics and smart textiles. They can be used in smart textiles and electronic textiles, scaffold, structural health monitoring and flexible sensors, fire retardant and UV protection textiles, composite reinforcement, nano reactors, etc. Finally, we can say that CNT could cover a wide range of textile functions from flame retardant fabrics to antibacterial textiles by the integration of various kinds of CNT with different applied production methods. Okay, thank you. I come to the end of my discussion here. Thank you all for your patient hearing. Thank you.
Yes. Thank you very much, sir. Any questions to Dr. Gokarnation? It's a long PPT, sir.
I reduced it, otherwise it would have taken longer time. Some points which are not so important, I just left out because of time constraint.
Yes. But if you come to this conference, just they'll be adding only 25 to 30 slides they are going to add, sir, actually.
Yes, sir. But
yes.
As this topic was very interesting and it is of a recent current interest, I could not delete the points. But in my presentation, I omitted some less important aspects.
Even
covered
in,
only the more
yes,
important aspects.
even in physical event also, they'll be they'll be going within 25 to 30 slides, sir.
Yes, yes, I can understand. Sir.
Yes, thank you very much, sir.
Thank you, sir.
Any questions? You'll be getting the soft copy of certificate as well as electronic booklet, sir, within 2 to 3 days, sir, after the completion of the conference.
Thank you so much, sir.
Yes.
Thank you for the opportunity.
Yes. Looking forward to meet again next time.
Thank you, sir.
Thanks for taking your time out of your busy schedule.
My pleasure, sir.
Yes. Next, we asked to Dr. Sumendra Darbar from Jadavpur University from India to join the event and start presentation.
Is it visible to?
Yes, sir. It's fine, sir.
Yeah. Good evening, all of you. Before start my presentation, I convey my heartiest thanks to the organizer, especially Dr. John, to giving me the opportunity to present our work in this international webinar. So today my topic is the novel green synthesized silver nanoparticle act as a nanozyme and are potentially useful against oxidative stress challenges and opportunities. So I am Dr. Soumendra Darbar from Jadavpur University, India. So from bones sun and creativity to hepatic fire, every medical treatment, a potential drug treatment. So how can small things help us fight big medical problems? So what we scientists to nanotech is the medical application of the nano. It is finest. The developed nanoparticles is used for therapeutic medical therapy. It's called the nano medicine. It's a tool in the nanotechnological research, have a potential medical effect in various diseases. Involves the use of nanomaterials, as the biochemical nanoparticles, and in living organisms. So of the advantage of nano is getting
Hello. Hello. Actually, we are unable to hear your voice, sir. We are getting an internet problem from your. I think there was a problem from your side, sir. Hello.
Hello.
Yes, sir, you can go ahead. Just there was a internet problem from your side, sir. We are
Slide
not
is
getting.
visible. Slide is visible.
No, no, sir, no.
Okay. Just a minute. Is it visible?
No, sir.
Maybe it's visible. Maybe it's visible.
Sir, you need to join again, sir. I think you are left.
Yeah. Just a minute.
Yes, take your own time. Hello? Hello? Yes, sir. We are unable to hear your voice. I think there was a internet problem from your side, sir. So, meanwhile, shall we go with another speaker, sir, if you give permission? Hello? So, shall we go with another speaker? So, we'll do one thing, just to, we'll ask an alternate speaker, that is Dr. So, we'll be going with an alternate speaker, sir. Hello?
Hello.
Yes, sir, you can go ahead.
Okay.
So, there was a problem from your side to, I think, internet problem. Just.
There is a connectivity problem, I think.
Yes, sir. So, meanwhile, just shall we go with another speaker, sir, if you give permission? Hello.
Hello.
Yes, sir. You can go ahead, sir.
Yeah. So, we're now going in COVID-19 situation. This is a pandemic situation where the hepatic dysfunction has been seen in 14 to 53% of the patients with COVID-19, particularly in those areas, the patients, those are COVID. We found the acute liver injury has been reported and associated in the higher mortality. This is published in the Journal of Hepatology in June 2020. Another report published in the Lancet Gastroenterology and Hepatology in March 2020, where it showed that the patients, those hospitalized due to the COVID-19 infections, which have the elevated aminotransaminase effects, as well as the bilirubin levels, which might be a fatal one. Another report published in the World Journal of Gastroenterology, published in May 2020, where the liver injury is the common in COVID-19 patients, especially in the infectious diseases, and it alter the bile-related parameters and it creates hepatic damage. So this is very in the modern age, therapeutic use of nanomedicines and become very popular. So why nanomedicine become very popular? Because the synthetic drug various disadvantages like reduced bioavailability, non-specific distributions of the entire body, metabolism in the GI tract, undesired adverse side effect, and low retention in the listening area. So now the scientists interested to develop nanomedicine because of its transport across countries, high specificity and bioavailability, high reactivity due to the higher surface to volume ratio, and targeted drug delivery. So now, till date, FDA approved 51 nanomedicine and 77 nanomedicines pipelines. So here we discussed about the hepatic fibrosis. It is a liver-related disease where increased accumulation of extracellular matrix and activation of hepatic cells is observed, and which if the fibrosis persists, it's developed hepatic cirrhosis and ultimately hepatic carcinoma. So various factors are involved in the hepatic development of the hepatic fibrosis, like alcohol, cigarette smoking, toxin, environmental toxin, heavy metals, drugs, etc. So we motivate about various published in the international journal. We know the liver disease is the 5th most common causes of death. In every year, there is 400 million of patients detected liver-related dysfunctions. So scientists throughout the world are very much interested to develop a new drugs which have a targeted delivery system. So phytometallic nanomaterials that can be used orally, especially orally, not the parental route, against the chronic diseases because of their nanospecific distribution. So here, our main aim and objective is to develop metal-based green synthesized nanoparticles, and we synthesize silver nanoparticles coupled with androgaphis paniculatum as a therapeutic agent against chronic liver disease, particularly hepatic fibrosis. And we apply the developed nanoparticle through oral route. So free radicals are involved to develop various kind of diseases, and if body generate or develop numerous types of free radicals like oxygen, superoxide anion, peroxidase, hydrogen peroxide, hydroxyl radical, hydroxyl ion, etc. These free radicals destroy the cell membrane and ultimately develop cell apoptosis. So there is a balance in between reactive oxygen species and antioxidants. If there is an imbalance between antioxidant and ROS, if ROS generation is more in comparison to antioxidant, the cell functions. So cell apoptosis occurs. So now we talked about the nanozymes. There is a difference between enzymes and nanozymes. In enzymes is a high efficiency, high specificity, high cost, low stability, requires specific condition. But in nanozymes is a high efficiency, low specificity, very low cost, targeted delivery, and highly soluble. So nanozymes act generally in the four ways: oxidative activity, peroxidase activity, and superoxidase activity. So here we developed the silver nanoparticle coupled with androgapis paniculator. This is the plant extract. This is the silver nitrate extract, and we developed the nanoparticles. So here is the characterizations of the nanoconjugate. Confirm that the presence and formations of the silver APAGNP, so silver nanoparticle coupled with androgapis paniculator. The UVVs, TAME, and XRD, as well as the FTIR, confirm the presence of nanoconjugate. So now the in vivo experiment. The treatment protocol, we choose the four groups. Group 1 control, group 2 CCl4 treated. It's a very common toxicant to develop liver fibrosis. Group 3 CCl4 and nanoparticle, develop nanoparticles, and group 4, that is the only developed nanoparticles, where we our intention is to find out whether our developed nanoparticles have any toxic effect or not. So here is a very interesting, the three morphological parameters: body weight, food consumption, and water consumption. So body weight significantly decrease after applications of CCl4, and it's prevented after applications of nanoparticles. So food consumption and water consumption also we measured. The food consumption is gradually increased in the CCl4 treated groups, where it is normalized when we apply the nanoparticles. The water consumption is gradually decreased in the group 2, that is the CCl4 treated group, and this water consumption leads to normalizations after application of the nanoparticles. So here is a key point, that when the metabolism occurs in the body, there is a balance between solute and solvent. So within our body, the solvent is water. So if the water content decrease after applications of the CCl4, the body metabolism is significantly hampered. So this is the morphological and some biochemical parameters. We observe the liver weight and liver weight, body weight index, where we observe the liver weight is significantly increased in the CCl4 treated group, and it is almost normalized, 90 to 92% normalized after applications of our developed silver nanoparticle coupled with androgapis paniculator. So here is the liver body weight ratio. The liver body weight ratio is significantly decreased in the group 2 animals and is restored after applications of the nanoparticles throughout the experimental period. So now the body fat. Body fat is another interesting parameter, which is increased in the group 2 animals, and it is almost significantly normal in the group 3. that is carbon tetrachloride plus our developed nanoparticles, application of our developed nanoparticles. Here, some biochemical parameters with the key parameters of bound blood urea nitrogen, total bilirubin, and direct bilirubin. We found the significant protections from our developed nanoparticles. The liver function test. We know that four enzymes parameters are essential to denote the liver function, like AST, ALT, AL, that's the alkaline phosphatase, and GGT, gamma glutamine transcriptidase. So these four liver specific enzymes significantly increased in the 2, and it is normalized in after applications of the nanoparticles. The group A, B, group C, and group D. Now figure E and figure A, where we observe the total protein concentration is gradually decreased in the group 2, that is the experimental group, and it is significantly restored after application of the nanoparticles. Now, the amino liver acid dehydrogenase is a marker enzyme of liver fibrosis. This enzyme is significantly decreased after applications of CCl4, and is restored when we apply our novel nanoparticles on the experimental animals. Now, in the lipid profile parameters, we measured all types of lipid profile parameters: triglycerides, LDL, VLDL, total cholesterol, and HDL. If liver fibrosis develop, the triglyceride, LDL, VLDL, and total cholesterol significantly increase. The same result we observed in the group 2 animals, and when we apply developable silver nanoparticle coupled with speniculator, we found the significant protections. We also measured the HDL, which is called the good cholesterol. The HDL level is gradually significantly decreased when we treated CCl4, and it is increased or normalized after application of the nanoparticles. Now, this is a blood parameter, hematological parameter. We observed the significant effect in WBC, RBC, platelet count, and hemoglobin. Now, come to the ROS parameter, that is the antioxidant parameters. We measured the MDA, that is the lipid peroxidation, the marker enzymes of membrane damage. We found in the 2, that is CCl4 treated, the MDA content significantly increased, and it is restored normal conditions after application of antibiotics. Here is the ROS, total ROS content is also significantly increased in the CCl4 treated group, and is restored after applications of the nanoparticles. We found the very interesting result in superoxide dismutase study, SOD study. In CCl4 treated group, SOD content is significantly declined, and SOD is very now come to ROS-related enzyme, that is glutathione peroxidase, reduced glutathione, both liver serum.
Hello. Sir, I think again you existed from this. Hello. Sir, we are unable to just Hello. Yes, sir. Just we ask again to share your PPT, sir.
Okay. Okay.
I think there was a poor internet problem from your side, sir. That's why we are. Internet strength.
Is it visible now?
No, sir. No. Are you presenting through from? It's going to opens. Yeah, it's fine.
Yeah, yeah. Okay. This histological sites. The normal histology eosin hematoxylin. This is the serious grade. The special strain. This is the collagen 1. We found the liver architecture, alteration of architecture in the second group, and this is after applications of the nanoparticles. We found the nectar is 4 after applications of the CCl4 and is almost 0 after application of the nanoparticles. So the inflammatory score, where in the second it is significant the nanoparticles. From study, second, both in the second group, found liver is significantly ruptured, the spookler of the liver is completely destroyed. After applications of the particles, it's recovered. So this is interesting that our developed known particles have protective upon liver fibrosis. So in summary and conclusion, we developed the silver nanoparticles synthesized with Andrographis paniculator act as a nanozymes. It's have huge redox potentials. This plant extract being a very eco-friendly and cost-effective materials. Since nanoparticles seems to have the antioxidant effect and chemistry approaches towards the synthesized silver nanoparticle through the grain route. So now these challenges of what's the challenges in the developmental study? That is structure, development, and characterization is another challenge. Stability is another challenge, both accelerated and real-time stability study. Clearance of animals from the animal ethics committee if we conduct the in vivo experiment. Clearance of human ethics committee, success completions of BAB study. It's a challenge in the clinical research. In the licensing, regulatory approval is another challenge. And in the market side, the pharmacovigilance study and the marketing strategy is another challenge. So in our molecules, we developed or we discovered the molecules, and we are in the preclinical stage. We conducted all type of preclinical stage, and we need to clinical applications molecules. So now there is an opportunity. Nanomolecules or nanomedicine is safe, very easy to high efficacy and right. So now medicines, the nanomedicines, especially is the future medicine. So this is our we acknowledge Professor Somit Kumar Pal, Professor Siddhartha Bhattacharya, Professor Pal, etc. And this is my group. So thank you all. So if you have a future any collaborations or any questions, may easily contact me. Thank you. Thank you, the organizers. So there is some connectivity problem. We are sorry for that.
Yes, sir. Yes. Any questions? Any questions to Dr. Sumendra Darbar? Just if you have any questions, you can text in chat box. Will be asking behalf of you. Yes. Thank you very much, sir, for participating in this event. On behalf of organizing committee members of Material Science and Nanotechnology 2021, we want to thank you for your presentation.
Thank you.
Yes, thanks for taking time out of your busy schedule. Next, you will be getting the soft copy of certificate as well as the electronic booklets or within a couple of days after the completion of the conference. Yes. Next, we invite Dr. Carlos Luna from Autonomous University of Nuevo Leon from Mexico.
Hello,
Yes,
good afternoon.
yes, sir.
I'm sharing my presentation.
Yes, sir.
Okay.
It's fine. It's fine, sir.
Okay. Okay. Thank you very much for giving me this wonderful opportunity to present this work and be part of this conference. This work is entitled Pseudo-monocrystalline Properties of Cylindrical Metal Nanowires and Deceptive Interplanar Spacing in Electron Microscopy Studies. And the authors are Enrique Díaz-Barriga Castro, Javier García, Raquel Mendoza Resendez, Víctor Prida, and myself, Carlos Luna. Okay, this is the plan of the presentation. The controlled growth of one-dimensional nanostructures have opened exciting and challenging opportunities to explore new phenomena and technological applications. These materials can be used in different nanoelectronic devices, such as field effect transistors, in the transport of electrons and excitons, logic gates and computation, and light-emitting diodes, among many others. Nanostructure magnetic materials with Taylor anisotropies have attracted the attention of many researchers due to their different magnetic behaviors. Interestingly, cylindrical magnetic nanowires can exhibit magnetic vortex domains at remanence under a strong competition between shape and magnetocrystalline anisotropies. Since regularly nanomaterials tend to crystallize with isotropic growth habits, few techniques allow the preparation of nanostructures with controlled anisotropic shapes. With few exceptions, single crystals naturally grow with faceted shapes with a low aspect ratio. So the use of templates is often used in the preparation of one-dimensional single crystals materials. For example, nanowires of different composition can be grown into the pores of mesoporous anodic alumina membranes by means of pulsed electrodeposition. Here is an example of a membrane, mesoporous membrane, and this is an illustration of the growth of nanowire by electrodeposition techniques. Okay, The accurate characterization of the morphology and crystalline properties of nanowires is crucial to understanding the physical properties and phenomena of these materials. In this regard, the transmission electron microscopy techniques, including high-resolution electron microscopy and the electron diffraction, play a fundamental role, allowing the study of the morphological and structural properties at the nanoscale. However, on many occasions, no special attention is paid to particular effects that emerge due to the complexity of the electron specimen interactions and the finite size and crystalline properties of nanomaterials. In these circumstances, deceptive data and erroneous interpretations could be extracted from the transmission electron microscopy analysis. In the present study, apparently monocrystalline nanowires of nickel, cobalt, copper alloy, and also multi-segmented cobalt nickel nanowires with 40 nanometers or 200 nanometers in diameter were synthesized by electrode position into the cylindrical pores of nanoporous alumina membranes. Different analytical techniques related with the transmission electron microscopy were performed. Okay. In these samples, we observe that exhibit pseudo-monocrystalline properties. Before discussing the results obtained in this investigation, I would like to revise some fundamental notions about the diffraction laws in crystals. When an electron beam hits a crystal, the atoms scatter the electrons in all directions. Bragg's law describes the condition in which the scattered electrons experience a constructive interference. Okay. This is the fundamental law of the diffraction. The atomic arrangement in a crystal is characterized by the Bravais lattice. The point of this lattice are generated by discrete translation in the three dimensions, giving the primitive vectors. Right. From the Bravais lattice, we can construct a new lattice named reciprocal lattice, which is the Fourier transform of the Bravais lattice. This is an artistic representation. Okay. The points of the reciprocal lattice can be associated to the electron wave vectors when the Bragg's diffraction condition is satisfied. The reciprocal primitive vectors are generated from the primitive vectors of the Bravais lattice with these equations. Okay, let's go to the concept of the equal sphere. For elastic electron diffraction, the incident wave number has the same magnitude than the scattering wave number, and it is equal to 2 pi over lambda, where lambda is the wavelength of the incident electrons. Then the scattering wave number lies on a sphere with the radius is 2p over lambda. And this sphere is the Ewald sphere after Paul-Peter Ewald. Therefore, the diffraction spots recorded in a diffraction patterns are related to the reciprocal lattice points touched by the surface of the Ewald sphere. If we rotate the crystal, this is the reciprocal lattice. If we rotate the crystal, the reciprocal lattice also rotates and the diffraction pattern change depending on the rotation angle. we can see some representation of this effect. Okay. Let's go to the results and discussions. The microstructure properties of the nickel nanowires were studied by transmission electron microscopy and electron diffraction. These nanowires exhibit single crystalline-like patterns, electron diffraction patterns, as you can see in this figure. And the well-defined diffraction spots can be indexed to the 111 zone axis of the metallic face-centered cubic nickel phase. This is the indexation. And we found that the -101 duration, this duration, is the duration of the long axis of the nanowire. Okay. Additionally, spots associated to forbidden reflections were also observed. These points are forbidden reflections. The occurrence of forbidden reflections in nanostructural materials is ascribed to two causes. One, this is the forbidden reflections. One of the causes is due to a reduced number of cells units, or two, due to the presence of crystal defects. Forbidden reflections in very thin crystals are due to because the crystal has few unit cells in their thickness. Some diffraction signal can be detected from the reciprocal lattice points located in the proximity of the Ewald sphere, due to there are few diffraction planes and the destructive interference of electrons is weakened. The other cause is the presence of crystal defects. The presence of crystal defects, such as stacking faults, can produce forbidden reflections in the electron diffraction pattern. In this video is illustrated the presence of stacking faults in the close packing sequence ABC ABC in a face-centered cubic structure. You can see that here we have a stacking fault. Our nickel nanowires are not particularly thin. They have the diameters around 200 nanometers. Then the observation of forbidden reflections cannot be only attributed to finite size effects. Therefore, we attributed the forbidden reflections to a rather imperfect crystalline structure. Our hypothesis is that these nanowires have 111 stacking faults and parallel twins. In these circumstances, the occurrence of forbidden reflections can be explained as follows. The Bragg condition is strictly satisfied when the surface of the Ewald intersects with a reciprocal lattice point. Okay. However, the stacking faults produce a relaxation of the diffraction condition, which is manifested in the reciprocal space as an elongation of the reciprocal lattice points in the 1-1 direction. So we can see that some elongated points touch the Ewald sphere even when the Bragg's law is not satisfied. In this fashion, these crystal defects favor the appearance of forbidden reflections in certain zone axes, specifically in the 1-1 zone axis or in the 1-1-2 zone axis. In order to corroborate our hypothesis, we try to observe this stacking force by transmission electron microscopy. For that, the electron beam has to be oriented in the 1-1 direction, which is the nanowise growth direction in our case. However, the nanowaves tend to fall parallel to the plane of the transmission electron microscopy Kapper grid. So, in order to observe these crystal defects, freestanding single nickel nanowires were embedded into a polymeric resin and slicing it with an ultramicrotome to investigate the microstructure of the nanowires on its top end. This figure shows a transmission electron microscopy image at the top end of a single nickel nanowires cut with the ultramicrotome. Okay. You can see in this image that electron diffraction pattern of this part of the nanowires and the high resolution transmission electron microscopy shows clearly the presence of a dense distribution of stacking force. You can see here very clearly. Such crystal defects are produced by probably the formation of these crystal defects in our nanowires are produced by the confined growth of the nanowires into the cylindrical pores of the aluminum membranes. With this, the natural formation of crystal facets becomes frustrated, and the rates of the crystal growth of different crystal directions are disturbed and governed by the confinement. Okay. Another astonishing feature of the diffraction patterns is that they change very little with the variation of the sample tilt angles. We can rotate the sample in the x-axis or in the y-axis with the alpha angle and beta angle. Okay, and so when we rotate the sample in these angles, we observe that the electron diffraction patterns are more or less the same. Please compare this image with these figures, this image where this is the experimental patterns, and these figures are patterns simulated for an ideal single crystal viewed at different alpha angles with respect to the zone axis 111. This is this image correspond to the zone axis 111, and these patterns corresponds to the different rotations in alpha angle. Okay. The only observed change in the with the rotation is the distance of the diffraction spots to the pattern center as the sample is tilted. You can see that, well, it's very subtle. You can see that the distance or the distance of the spots is slightly is varied with the angle. Okay. Here, the distance of the diffraction spots to the pattern center as the sample is tilted display different tendencies for different spots. It yields to calculate the spacing values considerably different than expected, with variations up to 14%. Such variations yield to deformed patterns at certain rotation angles that can be unrecognizable for a face-centered cubic nickel single crystal. Why we observe these tendencies? It can be explained with our picture of the elongation of the reciprocal lattice points due to the occurrence of stacking faults. Such points can intercept the equal sphere even at large angle away from the zone axis. I try to represent this in this animation. This fact led to diffraction spots in the electron diffraction patterns with unusual dependencies on the tilting angles. In this respect, Malm and O'Keefe demonstrated using simulated high-resolution transmission electron microscopy of a perfect nanocrystal that the lattice spacing directly measured from this image deviate from the real values when the sample is tilted away from a zone axis, up to 10%. This effect has been also experimentally observed in other articles in high-resolution transmission microscopy micrographs of ultrafine silicon nanowires. In agreement with these facts, and given the relationship between direct and reciprocal spaces, variations of the distance of the diffraction spots to the center of the pattern when the sample is tilted away from a zone axis should be expected, observing a distorted electron diffraction pattern. These behaviors are not anecdotic for the nickel nanowires. We have studied a lot of nanowire systems prepared by the same technique, but with different compositions. And we have observed the same behavior in cobalt nanowires with face-centered cubic structure, the same behaviors, forbidden reflections, change of the apparent de-spacing values, and also in multi-segmented cobalt nickel nanowires, even with other crystalline structure, in particular with an hexagonal phase. Also, in cobalt copper nanowires, we observe also the same behaviors. So we can, you can find more details in this article that is published in an open access journal. And we can conclude that in different composition, nanowires with different composition and crystalline structure, grown by the electrodeposition techniques into the cylindrical channels of porous alumina templates, exhibit properties that apparently can be considered monocrystalline if we don't perform a study carefully. It's very important to rotate the sample and verify if we have unusual behavior, diffraction properties that probably are due to crystalline defects. Probably these defects are produced due to the confined growth of these nanowires in a reduced cylindrical volume. The comprehension of these effects is crucial for the understanding of the physical properties of one-dimensional materials with cylindrical morphologies and their exploitation in a wide variety of emerging technologies based on these nanostructures. The authors thank to Universidad Autónoma de Nuevo León for the financial support and their research projects. And for further information, or if you would like to collaborate with us with different materials, you can contact me on this email. Thank you very much for your attention.
Yes, sir. Any questions? Any questions to Dr. Carlos Luna? Just if you have any questions, you can text in chat box. We will be asking behalf of you. Yes. Thank you very much, sir, for participating in this event.
Thank you very much.
Yes. On behalf of organizing committee members of Material Science and Nanotechnology 2021, we want to thank you for an insight presentation.
Thank you very much.
Us. Looking forward to meet again next time in physical event if everything goes well in 2022.
Thank you.
Yes. Next, we will go with keynote speaker of the event, Dr. Gunnar Suchenka from TU Dresden from Germany.
Can you hear me?
Yes, sir. We are going to play yours.
Thank you, Mr. Chairman, for your kind introduction. Also, I want to thank the organizers for inviting me to present my research. The title of my today's presentation is Spin Polarized Tunneling Magnetoresistance in Strontium ferromolybdate, strontium molybdate core shell structures. It's a joint contribution from TU Dresden and the Academy of Science of Belarus. This is the outline of my talk. I will give a brief introduction after I consider shortly ceramic fabrication. I will characterize the mechanism of spin polarized tunneling and finally some conclusions. Oxide perovskites with ferromagnetic behavior around room temperature were first reported in the 1950s in the pioneering studies on manganite. The discovery of the low field magnetoresistance and half metallicity of strontium ferromolybdates by Kobayashi in 1998 renewed the interest in these materials in the context of their potential application in the field of spin electronics. In the following years, the number of publications replicate the Gardner hype cycle for emerging technologies, an innovation trigger, a peak of inflated expectations, a trough of disillusionment, and a slope of enlightenment. What is still absent is a plateau of productivity. Strontium ferromolybdate double perovskites are good candidates for magnetic electrode materials for room temperature spintronic applications because they present a half metallic character that is a 100% spin polarization theoretically, a high Curie temperature. Note that ferromagnets should be operated in their ordered state below Curie temperature and the already mentioned low field magnetoresistance. The physical origin of intrinsic magnetoresistance in strontium ferromolybdate is half metallity. That is, the material is an insulator in one of the spin channels, but the metal in the other. This leads to a complete spin polarization at the Fermi level, making it suitable for application as a source of spin polarized charge carriers in spintonic devices. The tunneling magnetoresistance manipulates the tunneling of spin polarized conduction electrons across insulating barriers separated by two adjacent metallic regions by the application of an external magnetic field. In detail, the tunnel magnetoresistance in strontium ferromolybdate looks like this. Strontium ferromolybdate is a half metal where only downspin states are active at the Fermi surface. Correspondingly, tunneling of only spin down electrons is obtained in parallel spin configuration of the two strontium ferromolybdate layers separated by a thin barrier. The tunneling magnetoresistance has a finite value. In the anti-parallel spin configuration, tunneling is forbidden even for the spin down electrons, but also for the filled band of the spin up electrons. The tunneling magnetoresistance is 0. For the synthesis of strontium ferromolybdate nanopowders, the citrate gel technique was used. The starting high purity strontium and iron reagents were mixed, citric acid and the molybdenium reagent were added, the pH was adjusted, a sol was obtained, the sol was dried, cured, finally annealed, and quenched to room temperature. The shown scanning electron microscopy image demonstrates the formation of core shell structures in the individual grains. The extrinsic low-field resistance in perovskites was discovered by Wang et al. In 1996 in polycrystalline lanthanum strontium manganite ceramics. It was shown that the magnetoresistance in polycrystalline lanthanum strontium manganite ceramics exhibits two distinct regions: large magnetoresistance at low fields dominated by the spin polarized tunneling between the grains, and the high field magnetoresistance obtained also in single crystals. 2 years later, with low field magnetoresistance was obtained by Kobayashi et al. In strontium ferromolybdate. This work describes already the typical resistivity behavior of strontium ferromolybdate, a semiconductor-like behavior at low temperatures, followed by an upturn to a metallic behavior at high temperatures. 3 models are applied for the description of magnetoresistance. The empirical exponential model is simply a good approximation of the experimental results for both sintered and granular strontium ferromolybdate ceramic samples. The tunneling model, developed for barium strontium ferromolybdate, considers the conductivity due to elastic tunneling occurring through a barrier between two non-interacting grains possessing in equal spin polarization P but different directions in the neighboring grains, under an external magnetic field ash. Think the average cosinus of the angle between the magnetization directions of two neighboring grains yields the squared reduced magnetization m square. The resulting magnetoconductivity equals m squared times p squared, equation 1. On the other hand, the grain surface is a defective double perovskite, whereof the geometry, vacancies, and anti-site disorder act as random spin penning centers with the breath ferromagnetism. Therefore, the bulk-reduced magnetization is replaced by a magnetic field-dependent magnetization M sub GB of the region close to the grain boundary, which was taken in a functional form widely used for spin classes possessing a weak anisotropy field, equation 2. Rewriting the first equation in terms of magnetoresistivity, we arrive at equation 3. Intragrain magnetoresistance is accounted by adding a linear term. Equation 4. It is typically large, near the magnetic ordering temperature. In the limit of large fields compared to the magnetic field parameter H sub 0, the empirical model coincides with the tunneling one. In order to improve the fit of the magnetoresistance data of pressed barium strontium ferromolybdate powders at low fields, a hyperbolic tangent function correction was added later. Analyzing the magnetoresistance of the fabricated strontium ferromolybdate strontium molybdate core shell structures in terms of the Serratus tunneling model, we obtain a quite well fit. Here the parameter alpha decreases linear with temperature, that is the magnetic field parameter P sub 0 in the order of 1 millitesla slows down quadratically with temperature. We have developed a more complex model for intergranular magnetoresistance of strontium ferromolybdate ceramics caused by spin polarized tunneling. The resistivity of a granular metal network in which the metal grains are interconnected by insulating barriers is given by equation 1, where F is a barrier shape factor, F equals 2 for rectangular barriers, F equals B half for parabolic barriers, Xi is a reciprocal localization length of the wave function, with m star the effective electron mass, v sub 0 the barrier height, stroke h the reduced Planck constant, w is the barrier width, E sub c the charging energy of the grains, K is the Boltzmann constant, and T is the absolute temperature. Note that we are considering thin enough barriers in the order of 1 to 3 nanometers, where direct tunneling occurs which is not disturbed by localized states in the thin barrier film. An estimation of E sub c for grains of diameter d much larger than the barrier width d w is given by equation 2. Note that the charging energy is reciprocal to the grain diameter. Charging effects become significant only at small grain sizes. In our case of nano-sized granular strontium ferromolybdate, with a grain size d equals 75 nanometers and the barrier width W equals 1.24 nanometers, the charging energy E sub C yields a value of 0.4 millielectron volt, that is, it is negligible. Tunneling itself is a temperature-independent process. Spin-dependent electron tunneling depends on the relative orientation of the magnetic moments between the ferromagnetic grains of strontium ferromolybdate. The tunnel resistance decreases when the magnetic moments of the grains are aligned in parallel in an applied magnetic field. If the angle between the magnetization on both sides of the tunneling barrier is randomly distributed between 0 and P, the resistivity is given by equation 3, where M is a relative magnetization, that is magnetization M scaled to the saturation magnetization M sub S, and P is a spin polarization in the magnetic grains. Taking into account only small changes of the barrier height by the applied magnetic field, this yields a magnetic resistance of equation 4, where ρ is a resistivity for a given magnetic flux density B. For very large barrier heights and very soft magnetic materials, we obtain the well-known relation 5. In the latter model, the maximum magnetic resistance is minus 50%. This slide shows the derivation of the modal parameters. Approaching the Curie temperature, the square of the reduced magnetization changes as a Curie temperature T sub C minus T divided by T sub C. Therefore, we approximate this value by a series expansion, equation 1. The coefficients of this equation are slightly different for powders and ceramics. The magnetic flux density dependence of the reduced magnetization was modeled by means of a traditional analysis of the approach of magnetization to saturation, equation 2, where each term of this expansion is associated with a certain source of magnetic inhomogeneities, I equals 1, 2, and 3 for point, linear, and layer sources respectively. The first term of the series expansion equation 2 can be also related to spin classes in the limit of weak anisotropy. Grain boundaries are absent in powders. Consequently, the first term is missing. At magnetic flux densities higher than 0.5 Tesla, powders are dominated by the second term. Tunneling spin polarization and interface magnetization followed the same temperature dependence. In result, the spin polarization resembles the spontaneous magnetization behavior at low temperatures, known as a Bloch T to the 3 half law. Equation 3. Here the fitting parameter G is generally larger for surfaces than for the bulk, being very sensitive to surface contaminations. Now, we assume that spin polarization dependence on andesite disorder is similar to the dependence of the magnetization on andesite disorder. In this case, the spin polarization is given by equation 4. The magnetic field dependence of the tunneling barrier we take in the form of a series expansion. The coefficient beta is attributed to Zeeman splitting, amounting about 1 Bohr magnetron for magnetic field perpendicular and about 20 Bohr magnetrons for a magnetic field applied parallel to the current. The coefficient gamma is adapted from data of a magnetic sensor based on a tunneling device comprising a 2 nanometer thick double perovskite lanthanum cobaltite manganate layer grown on top of a niobium doped strontium titanate substrate and capped with a thin platinum layer. A theoretical estimate of gamma yields a slightly higher value, since we are not dealing with collision-free electrons. This slide illustrates the calculated temperature and field dependencies of the magnetic resistance originated by spin-polarized tunneling. The model slightly overestimates the temperature dependence of the magnetic resistance in the low field region, since the coercive field was not accounted. On the other hand, there is an increase of the contribution of the conventional magnetic resistance at higher magnetic fluxes above 6 Tesla, which was not included in the present model. Therefore, this model is valid only for the field region up to 6 Tesla. Low field measurements of the magnetic resistance in strontium ferromolybdate are scarce. This figure compares the calculated low field magnetic resistance with available experimental data for magnetic fluxes up to 2 Tesla. Here, the anti-side disorder of different samples varies strongly depending on synthesis conditions. It will be different from the value of 0.1 used in the calculation. The agreement of the model with the experiment is worse, but acceptable. These are my conclusions and the sponsor of this work. Thank you for your time and attention.
Any questions? Any questions to Dr. Ganhar Sushank? Just if you have any questions, you can text in chat box. We'll be asking behalf of you, even after the completion of the conference. Yes, yes. Thank you very much, sir, for participating in this event.
Thank you, you too.
Yeah.
See you next time.
Yes. On behalf of organizing committee members of Material Science and Nanotechnology 2021, we want to thank you for an instant presentation. Thank you so much for joining and for your attention.
Thank you, you too.
Yes. Next, we welcome Dr. Gerhard Klimik from Purdue University from USA to join the event and start the presentation.
Good morning. For me, it's morning. I'm going to share my screen.
Yes, sir.
Pardon me. So I'd like to share my story about NanoHub, which is a largest nanotechnology facility in the world. It's a virtual facility. It has 2 million users annually. It has 1,800 contributors in 172 countries, and it's typically faculty, students, and industry practitioners participating. Here's an integral view of 1 year's worth of users in the site. And as you can see, there's global interest in nanotechnology and learning about it. And there is has been for 20 years a significant investment in nanotechnology. So the United States alone invests about $2 billion annually in nano research. And there is more, of course, in other continents being invested in an industry. And lots of software and data is generated in this. And the broad audience cannot really learn from these artifacts because they're not accessible. Therefore, we created NanoHub that converts these resources into usable apps that have now a global user base. Our vision is to accelerate innovation through user-centric science and engineering to really provide information and tools to a broad community, not just specialists. Our mission is to make science and engineering products that are really usable by and discoverable, reproducible, and easy to create. So we also have enable people to deposit their artifacts, their tools, their seminars. And we do that for learners, educators, researchers, and business professionals. So with that, I'll give you a brief overview of what it is. I already mentioned the user base. And now, what is it? We have over 700 nano apps that are running in the cloud. We have over 6,500 lectures and tutorials, over 170 courses. So we are a MOOC, a massive online open courseware. We are a cyber infrastructure that is running 24/7 with 99.4% uptime. So it's down very few times in the year. We measure research impact, and we do this in a variety of ways. One paradigm shift, a change in what happened in the last 4 years is we created a new type of publication that is now listed in the Web of Science and in Google Scholar. Our nano apps and compact models are now listed in the Web of Science as a new type of publication. That is a change in expectation than what was done before. There's also over 2,500 papers that cite NanoHub. And pardon me. So these are people outside of NanoHub, not the core group, that are citing NanoHub in use in research. And we were told early on that nobody will ever use these apps for research. So this is really a proof that it can be done. And we measure educational impact. And I'll show you the methodologies on how we do that. We have now identified over 90,000 students that use these tools in classrooms in 185 institutions. So we change curriculum rapidly. So the essence here is there's a fundamental change in approach and underlying assumptions. And there's this word called paradigm shift that is often overused. But I would say here's 3 examples of how we introduced a paradigm shift in research, in the type of publication, and in doing education. To me, these are just existence proof. This can be done in any field of science. It doesn't have to be nano. And indeed, we spun out NanoHub into Hub Zero. I want to try to give you a view of what I mean by going beyond specialized capabilities and the tools that we deliver, and give you an analogy. So here is a pretty cool new device. In 1894 or so, the first car in Germany, developed by Benz, and it had certain properties. It was very expensive. And the driver that you had was not only the driver, it's probably also the mechanic and the gasoline fetcher. And you had to be pretty rich and be dragged around in this vehicle. Now, the true innovation and the impact came by making these things usable and accessible, meaning many people could afford it and use it by themselves. They didn't have to be rich to do it. There's something similar. If you're old enough in the audience, you might remember tablet PCs coming out. And when the iPads came out, people said, well, these tablets are much more powerful. Yeah, they are, but they weren't usable and they weren't accessible. And that was the true impact of tablets, that they were usable and accessible, easy to use. You didn't have to read a 200-page manual with an iPad, but you do have to do that with a tablet PC. Now, if you're in the field of material science or nanoelectronics, these names might mean something to you. To me, they stand for very powerful tools and engines that can do a lot of work. And in many ways, they're similar to this car. Up front is the graduate student. In his hands is the X-term on a Unix machine. The car is the supercomputer where these things run on. And I'm the fat professor that's in the back directing the graduate student to do his work. So what we've done with NanoHub, we made these tools usable and accessible. We put them into apps that are easy to use. And once we've done that, when we went away from web forms, we saw a dramatic growth in simulation users at the time. So, and now, as I mentioned, these tools are now listed in the Web of Science. There's a tool set called NEMO that's dear to me because we built it in my research group over the last 25 years or so. And this tool set is powering 9 apps, 9 out of 700 or so on NanoHub, and it's being used in industry to design transistors today. Now, how do we measure impact on research? So here is a social network chart of papers. These are, in this graph, over 2,000 papers, 2,000 dots that are color-coded in a specific form. And the lines between the dots are common authors. So this is a social network chart that involves the use of NanoHub. Now, I made these points already. I'm going to skip over this. Here, 65% of the papers are outside of the realm of people that I know and that were originally at some point funded some 10, 15 years ago for NanoHub. The color coding goes as this: 82% are in red. These are nano research papers. There's a lot of people on the computer science side that look at us from the outside. We wrote really very few papers about NanoHub. And astonishingly, there is a bunch of papers now where people write how they use NanoHub in education. So these are papers in the field of education describing and assessing the use of NanoHub. So there's educators present. And from the affiliations of the papers, we can see that 7% of the authors are in industry. Now, so you have another aspect that you can look at is which was related to the challenge we were facing. We were told that no experimentalist will ever touch these apps. And that's patently false now. We color-coded these papers here by having content of experimental data or a bona fide experimentalist on the author list. So we are moving computational science tools into the realm of experimental work. So again, that's a paradigm shift in impact. So we can demonstrate to be translational from one research field, one research arena into another research arena. The next question is, can we be translational in education? And I would like to show you how we figure that out. So here is a pictogram of a user who comes on one day and uses the green tool, and then doesn't come back the next day, and then uses 2 days in a row the orange tool, and then maybe the green tool again, and then doesn't come back for 3 days and uses the green tool again. So we have a bunch of users where we look at their temporal behavior patterns. And here you'll see an animation of that rushing by. And it looks very much disordered, as you could expect from random behavior of people, except when you start to stare there, you see some stripes like this, some patterns, some chunks, then some bigger chunks. And you start to wonder whether there's a correlated behavior between people. And we wrote some of the first clustering algorithms in that area, where we can, over time, on the horizontal axis, we can cluster people together. For example, here's a group that comes for roughly a week, uses the yellow tool. Here's another group that comes throughout a whole semester in a rhythmic pattern, just uses one tool. Here's spring break. And another group where they come and use 1, 2, 3, 4, 5, 6, 7, 8 different tools in a rhythmic pattern. These are students in classrooms. We can actually measure the classroom size by student behavior. And this is a new approach to measure impact on students, measure what they're doing, what tools they're using, and it's not done by surveys. This is really scalable. It doesn't involve one-on-one human interaction to do assessment of this work. And we've done this analysis. We bonified some of these classes one by one to make sure this is correct. And in this shape or form, we have now actually over 90,000 students that behaved in this fashion. So this is a new paradigm in assessment. Then there's people that seem to behave completely erratic, independent of each other. We can identify some of those to be experimentalist researchers or computational researchers. And then we have another group of persons here that we haven't really identified what they're doing. It's about 50% of our population on NanoHub that appears to be working really randomly. We call those self-study users. Now, if I have a class like this that uses the purple tool, or say the green tool, that classifies the tools as being used in education. So I can make a scale from 0 to 1 and rank each tool, where each dot is a tool now, from 0 to 1, whether they're used heavily in education or not so heavily in education. And I've shown you these social network charts. I can rank the tools now in terms of research use, right? On research behavior use from 0 to 1. And people think that these two are orthogonal. In fact, on my annual review in one of them some 10 years ago, I was asked, well, how many of your 121 tools at the time are research and are education? Well, I couldn't really truly answer that question, because not these 120 tools were not my tools. I was not the author. I had no idea what the intention of the tools were. Now with analytics like this, I can show you now that these tools, many of these tools actually bridge research and education. So these are tools that are being used in education and in research. And there's a bunch of tools that are only used in education and a bunch of tools that are only used in research. So it's really dual use in education and in research. And what's really cool is I have a lot of data to look at, and I can backtrack in time and see when the tool is born. I don't know what the usage is going to be. And I'm looking back at data back to 2001, 20 years worth of data. At that time, we had web forms, very few tools, hard to create. The NCN, the organization I lead, was founded in 2002. And then we created a new interactive system we call Rapture, which allows rapid application deployment. So there's a lot of tools coming in. They're popular. We grow in number of tools and we grow in number of users rather rapidly because they're easy to use. And what you can see is how these tools migrate nicely, interestingly, from the research side into the education side. And there's a coupling. This is truly translational work, which is, I think, kind of cool. All right. Now I can, since each of these tools has a digital object identifier, I can measure the time to adoption in the classroom. So the time to first adoption. And I can measure this time and compare that to a typical textbook rewrite, which takes about 4 years. And I put this on a rather strange scale from a week, a month, 6 months, and so on. And we find that the median time to adoption after tool publication is less than 6 months, meaning we can influence and innovate teaching rather rapidly compared to writing textbooks. And we have an adoption outside of NanoHub where people just find the tools, and we have an inside adoption where we develop these tools and use them then also for education ourselves. All right, so NanoHub is a platform that really is a framework for computational researchers and a nano app store for end users, and it is a publisher of tools. And what I like to show you now is how some of these tools work and what we can do with them and analyze people's behavior. So here, NanoHub users follow the typical simulation approach where iterative parameters changes drive towards a specific design solution. So, and they've generated over 4 million simulation data sets. But we have not used these massive data to improve the user's design and exploration experience. Therefore, we began to develop prototypes to analyze this user behavior. So let me show you how we're going about this. And we call this platform Instant On. So here's one example of one of the early tools, early interactive tools. This is a p-n junction lab, very simple to use. Interestingly, it is actually powered by a very sophisticated engine that designed transistors at Bell Labs. So this is a classical semiconductor device tool called Padre. It's an industrial tool that is underneath this app. And as I mentioned, this tool has a publication date, it has a DOI, it has citations, we have detailed users, there's question and answer forum, reviews, wishes. And so if I now go in and hit simulate, I can get, in a couple of seconds, I will get a bandage diagram like this, for example. There's more data available that's here under pull down, like electric fields, and you can see how the p-n junction works as a bias, under bias. And if I now click on this doping here, I can change it to say 1E17. I can hit simulate again, and I get a different bandage diagram. And what's really cool, and that's true for all the Rapture tools, you can click the all button and you can compare these and drive towards a certain set of solutions. So the interesting thing is now I've shown you in a sort of in a pictorial way a description of 2 simulations that were run in one session. So within one session, you can have many different simulation runs. And I want to show you some analysis of what people actually use. So the point here is you can run what if questions and compare results. And the question then is, what do users really simulate? I'm going to compare 2 different groups. So there's the golden group here, 19 users or students that had 20 sessions. So they basically, each user had 1 session and they've done 237 runs. So basically each user had done about 10 simulations within one session. There's another group, 18 users and students, they had 29 sessions. So roughly half of the users had 2 sessions, but in total, they also had done about 10 runs in each session. All right, so what did they do? In this tool, there's actually 17 parameters you can change, and these groups have changed 10. So you can change the material, say silicon, gallium arsenide, you can change the p-type length, the intrinsic length, the n-type length, the intrinsic doping, in the p-type region, the intrinsic region, the grid points, temperature, applied voltage, and the p-type doping. All right, so let's look at those 19 students, the golden group, with 237 runs. This is how they behaved. They didn't change the material properties. There's a little bit of change in the p-type length, and they focused on the intrinsic doping and the temperature effect. So this is what they pursued. And this is called a Sankey diagram for data analysis. So here I'm highlighting what they're doing. And now let me compare that to the purple group of 18 students. They interestingly behave in a very different way and focus on different properties, different types of doping. So they didn't look at the intrinsic doping, they looked at the n-type doping. And really, you can see that these groups of students behave very differently in these classes. So they have probably different instructional materials or exploratory advice. And here you can put them all together. And this flows quite well with faculty that have asked me, what did my students really simulate? And we're working on trying to provide that information and integrating NanoHub into learning management systems. Now here's a more modern view of the same tool that we are revamping now, and we're revamping the user experience. So what's the normal process? How do we normally simulate? We provide some input parameter, get some simulation data, then we understand something, come up with a design, and then we repeat in multiple ways until we achieve the design that we want to achieve. Now, what if you change the paradigm and say you have a ton of data already, the inputs and the outputs that came from these simulators, can you understand and design in shorter steps and make this more streamlined? So what you see here is a prototype of a data exploratory tool that lets you down select, so to speak, all the existing simulations and look at data in a different way. So you can narrow down the existing tool set. So you see in a way an explorer, a database explorer of scientific results. And I think that is the next game changer in our apps, where we allow people to really explore data. So this will allow you for faster turnaround, and I've shown you examples of individual user behavior and collective user behavior. And I would like to, in my last segment here, show you how individual users can do behave. So imagine that you have an n-dimensional space, like a parameter space in a tool. And imagine you project that down into 2 dimensions, so into a plane. So the question now is, if you start from a particular starting point and start a simulation and change one parameter, say X. If you change 3 parameters, the dot in this pictogram becomes larger. And then you change something small again and keep walking onto a certain path until you get to your finish. So this is a way you can visualize, if you will, the exploration of a user in the design space. Now, here's one example from this PN Junction lab where a user took deliberate small steps to achieve a certain finished result. We call it a person, a wanderer, or a searcher. Now imagine here's another user. This is also, again, a true data set of a user where a person starts, takes a big step, small exploration, big and small, big and small, big and small, and then explores towards a final finish. Also, this user we call a searcher. Then we have another class of people that behaves like this. They take wild steps in design space where they modify 2 or 3 parameters at a time. And we call those folks wildcatters. They jump wildly. Now, if you sit on a bunch of data, it would be cool to know how many of the users in this tool, out of 1,800 users, how many of them are wildcatters and how many of them are searchers. So it turns out that most people are actually wildcatting. They're really jumping around quite a bit, and few people, really relatively speaking, are deliberate searchers. And we can compare that into different classrooms that have different instructional material. Here's a class that uses just this one tool in red, and here's the class in green that uses multiple tools. So there's overall different behaviors in these classes. So we can have that be linked to the scaffolding of the course, the syllabus, the tool set, student experience, and we can think about reporting that back to instructors in terms of the essence of their student behavior. So with that, I'd like to conclude that NanoHub, in a nutshell, is really translating traditional research to new paradigms in publishing, computing, research, and education. And I thank you for your attention.
Yes. Jenny. Yes, any questions? Yes, any questions to Dr. Gerhard? Thank you so much, sir, for participating in this event. On behalf of organizing committee members of Material Science and Nanotechnology 2121, we want thank you for insight presentation.
Thank you.
Yes. Thanks for taking your time off a busy schedule. Looking forward to meet again next time.
Thank you.
Yes, sir. So within a couple of days, you will be getting the soft copy of certificate as well as electronic booklet, sir, after the completion of the conference.
Thank you very much.
Yes, yes. Yes. So we came to know that Dr. Soshu Krihara from Osaka University from Japan asking to play his video again. So based upon his request, we are going to play the video presentation.
Okay, today I would like to talk about a new additive manufacturing process of the name is ultraviolet laser lithography. Okay. So in our investigation group, we try to fabricate various kind of metal and ceramic structures, compose 2 dimensions and 3 dimensional structures. Okay. So there are structures and compose periodic patterns and self-similar patterns. The periodic patterns has integer dimensions, 1 to 3 dimensions, and the self-similar structures is a non-integer dimension like this. Anyway, we can control the electromagnetic wave and the electric and magnetic field and the force and the sound dynamic field and the material diffusion flow, and by using 3 dimensions and 2 dimension and material patterns. So today I would like to talk about the photonic crystals, the functional materials of our, it's possible to control the electromagnetic wave by wave diffractions. Okay, here is our photonic crystals. Okay, this artificial crystal compose dielectric materials and the periodic structures. And this is electromagnetic waves whose wavelength is similar to this periodicity. In this case, the wave will be reflected by Bragg diffractions. In this case, then, the 2 different standing wave form in the crystal structures. For example, the one wave and the wave A vibrating in air region with higher frequency, and the wave B vibrating with lower frequency in the material regions. And the standing wave A and the standing wave B, between these frequency, the all electromagnetic wave will be reflected by Bragg diffractions. So in the limited frequency range, photonic bandgap form. This bandgap is possible to prohibit electromagnetic wave propagations in frequency areas. Okay. Anyway, the photonic crystals are artificial crystal composed of dielectric material periodic structures, and it's possible to open the photonic bandgap for the typical crystal directions. Okay, what is the ideal photonic crystal structures? The one type is like this, the diamond type. These are the 4 coordination number. Okay, if you introduce the electromagnetic wave for these 111, the 110, the 100, the crystal directions, the photonic bandgap will be opened for all crystal directions in the similar frequency range. This blue band shows the common regions for all crystal directions. So in this perfect photonic bandgap areas, all electromagnetic wave impossible to transmit to the opposite side for any directions in the artificial crystal patterns. Anyway, and the perfect photonic crystals, the diamond type photonic crystal, possible to open the perfect photonic bandgap. Okay, however, these has very difficult crystal structures, 3-dimensional patterns, so it is difficult to fabricate by using a conventional mechanical processing method. So in our investigation group, we try to fabricate the diamond type photonic crystals by using a stereolithography, one type of the additive manufacturing process. Okay, here is a photosensitive resins, and the UV laser scanned on the liquid surface to create the 2-dimensional patterns. And the layer by layer stacking, we can obtain the complicated shaped 3-dimensional structures. And the most important things in the liquid phase, ceramics particles disperse and to increase the dielectric constant of the 3-dimensional patterns. Anyway, we can obtain the composite materials, dielectric ceramics and the resin matrix, and by using a layer by layer stacking, stereolithography, additive manufacturing process. Okay, at first additive manufacturing material 3-dimensional printer ink was fabricated by using rotation revolution mixing machines. The aluminum particles, particle diameter is 117 nanometers, were dispersed into the photosensitive acrylic resin, the 40 volume %. Okay, and this liquid phase and the solid phase mixed materials enter into this small pot, and by using rotations and the liquid phase and the solid phase of the mix in here, and by using revolutions, so the gassing will be realized. So by using this mixing machines, we can obtain the paste materials. Okay, this figure shows a schematic illustration of the stereolithography. The paste materials are spread on the glass substrate by using mechanical knife edge. In this case, a layer thickness about 30 micron. Sorry. So the the liquid surface, paste surface, laser beam scanned on the like this, and to create the cross sections of the solid layers. And the spread and the laser scanning and the layer by layer stacking process, we can obtain the 3D solid structures in unsolidified paste materials. These 3D structures are picked up after fabrications, so the composite materials will be transferred to the full ceramic structures through the conventional dewaxing and sintering process. Anyway, in this case, the alumina particles and the particle diameter is 170 nanometers are dispersed into the acrylic resin and 40 bottom percent, and this paste materials were used. And the ultraviolet laser beam wavelength is 355 nanometers, and the diameter is 13 microns, and the laser power is 100 microwatt. Okay, this figure shows obtained the stereolithography the samples, and you can see the micrometer, the 3D lattice was obtained. Okay, of course, this is composite materials. This yellow color means resin matrix. So through the waxing process about 600 degrees C, you can see the resin matrix burner perfectly. So after the waxing and the sintering will be executed about 1000 degrees C. Okay. So this figure shows obtained the full ceramics micro lattice. You can see there are very fine lattice structures was obtained. In this case, a relative density reached as a 99.8%. High density micro lattice was obtained. Alumina structures was obtained, and you can see that translucent micro lattice was obtained by using stereolithography and dewaxing and sintering processes. So the terahertz wave transmission pattern was measured by using this optical system. So the micrometer order photonic crystals possible to control the micrometer order electromagnetic wave. That's name is a terahertz wave. Okay. Anyway, at first, femtosecond laser beam the instant into the like this micro antenna emitter, and generated and terahertz wave terahertz wave pulse transmit a sample and detected the same shape the micro antennas, and we can obtain the like this time and the intensity pulse data, and through the Fourier transformation we can obtain the spectrum. Terahertz wave transmission spectrum for the sample. The sample, of course, this is the photonic crystals. Okay, you can see there. This figure shows the attenuation properties of the terahertz wave, the frequency and the attenuation. Okay, and you can see the photonic band gap open for all three directions: 111, the 100, the 110 crystal directions. And this blue band shows a common region for all crystal directions. For example, the 0.4 terahertz wave impossible to transmit for any directions by formation of the photonic band gap. So this means a perfect photonic band gap formations. Okay, this figure shows natural semiconductor crystals composed of the periodic structures of the atoms. Okay, in this case, here is an electronic wave. The whose wavelength is similar to this periodicity, the wave will be reflected by Bragg diffractions. So in this case, the electronic band gap opens in the electronic band areas, and and if you introduce the donor and the acceptor, so that you can create the various kind of the localized mode in the electronic band gap, and you can control the electronic wave transmission and the reflections by semiconductor structures. Okay, the photonic crystals are the imitation, the artificial structures that are imitated to the natural semiconductors, and the composed of the periodic structure of the dielectric materials. And in this case, the photonic band gap opened by electromagnetic wave diffractions. So if you introduce a point defect and line defect and a plane defect, you can create the various kind of the localized mode in the photonic band gap. So this figure shows a point defect introduced into the perfect photonic structures, photonic crystal structures in the diamond lattice. Okay, so here is one unit and cubic shape, and cavity was introduced inside of the photonic crystal structures. Okay, this figure shows our calculation result. Okay, incident wave indicate localize and resonate here, and one wave and localize here, and increase the power, making us here is the perfect reflection areas, and the wave diffractions and the wave vibrations and multiple reflections occurs and increase the power and transmit to the opposite side like this. Okay, in this case, the incident wave and the localize resonate here, and one wave localize this directions, and here is a high intensity wave, and so the localize resonate, and the surrounding here is our perfect reflection areas, so the multiple reflection occurs and increase the power and transmit to the opposite side. Okay, the frequency, the 0.43 and the 0.46. Okay, so this figure shows the measurement result, and the perfect photonic crystals possible to open the photonic band gap in the limited frequency range. And the 0.42 and the 0.46 terahertz wave, and you can see the transmission mode is occurred like this. Okay, these are localized mode. And the perfect photonic band gap, photonic crystal open the photonic band gap, and they introduce the structural defect, the point defect possible to create the localized mode of the transmission peak like this. Of course, you can control this peak frequency by changing cavity size. If you introduce more large cavities, and this peak frequency shifted for low frequency. And if you introduce a more small point defect, you can control the peak frequency for the shift for the higher frequency anyway. So this is same figures, however, and in this investigation, in these trials, we have to use two different process. And at first, the stereolithography process, 3D fabrications, and the dewaxing process. So the next trial is a directional fabrications of the ceramic structures by using only one process, using a laser stereolithography process. In this case, the schematic illustrations is similar to the conventional stereolithography. However, the laser beam power increased into the 1 watt. This is not so high, looks like. However, this is 10 times higher than the conventional stereolithography process. Okay, laser beam scanned on the liquid surface. Of course, the liquid surface means a ceramic particle dispersing resin paste like this. And the high power UV laser will be possible to do the waxing, the resin decompositions, and the sintering through the electromagnetic wave resonance, localization, and absorption like this. So you can create the ceramic structures only the UV laser stereolithography, only one process. Okay, this figure shows a process photograph, and you can see the bright color obtained, and the laser beam scanned on the like this and the paste surface, so we can obtain the plate-shaped structures. Okay, here the solid structures, and this figure shows a microstructure of the plate-shaped structures samples, and you can see the large-scale ceramic sparks was obtained, and the bulks and grain were obtained. Okay, and grain size and the particle size, grain size is about 5 microns and 10 microns. So at first, dispersed the ceramic particle, the diameter is under 1 microns, and for example, 500 nanometers. So the particle, the resin was degassed, and the gas and the particle was sintered by UV laser irradiations. So in this case, the spread paste thickness is 15 microns, and however, after laser drawing and the layer thickness decreased to the 25 microns. Okay, this means the surrounding particle dispersion is just 50 volume percent equal to the volume percent. Okay, the shrinkage. So that the waxing and sintering shrinkage occurs only the z directions. So it's possible to realize a layer by layer processing. So this figure shows a calculated result. In our investigations in the ultraviolet laser beam were used.
Yes, yes. Thank you very much, sir, for participating in this event. And looking forward to meet again next time. So we have shared your video presentation in this online event. Officially, you'll be getting the participation certificates as well as electronic booklet after the completion of the conference. And if you go to the program, the conference, we have left Dr. Anupama B. Call from University of North Texas from USA, Dr. Huzidi Fatima from Aziba Benza Bola from Algeria, Dr. S.T. Mitchell from USC, as well as Dr. Aharon Gedankian from Bal Hayan University from Israel, as well as not the least of the speaker of the day of the conference, Dr. Vijay K. Srivastava, the Indian Institute of Technology from India. So we'll be waiting for, we'll be having a 10 minutes break, and we'll be joining this event by 6:35 according to ISD Indian Standard Timings.
just about every field that universities teach in, and one of the fields I research is in physics. And in this case, this talk is about the ether, which was thought not to exist by this paper.
Hello. All the participants, due to some delay of the program, we do have more 3 to 4 speakers from all over the world. So now I request ST Mitchell from USA will be playing the video presentation.
It was compiled from 12 smaller papers that I've written on the ether. They're all brought together under one paper under a journal by the name of NESSA, N-E-S-S-A, and the reference to that is at the end of this paper. So the Teflon is like a face-centered cube, and there's a slip plane in the face-centered cube, and we calculate the angles of that face-centered cube. So two important facts about the astrotheology theory, which is my theory on mathematical physics about the whole universe, not just the ether, but the whole universe, is that the universe exists where the force and the momentum are equal. So, of course, force equals ma, momentum equals mv, so that's saying that v equals a. Since acceleration is the derivative of velocity, and velocity is the derivative of distance, then s equals v equals a. It's a critical factor in astrotheology theory. So a number that popped up often when we use the golden mean parabola is that if we plug pi into the golden mean parabola, which is t squared minus t minus 1 equals the energy, or is usually 0. If we put pi into that equation, we get the energy equal to 57.29, which is 1 radian. So in this paper, we make use of these facts coupled with material engineering to see why these two values are important. And we begin with the slip plane with the face center. So there's a couple of free body diagrams of elements from mechanics. And we see that when the force of 8/3 is applied, that's determined to be the superforce. It's equal to 2.6666 repeating. And when the angle is 45 degrees, we wind up with the force pulling in each direction there in the right-hand diagram being equal to 8/3. So PTFE, polytetrafluoroethylene Teflon, is a linear polymer. It is 8 mers per molecule, and that happens to be 248 grams per mole, which works out to 1/403. 403 is approximately the Reynolds number for the universe. The Reynolds number is the inertial forces over the viscous forces, or ma over 1/2 rho v squared, where rho is the density. So we calculate when we plug in the values that we know for the density of the ether is 4/pi, which is 127.2. When we plug that into our equations I just mentioned, we get mass equal to 1/c squared. So that's saying the energy is equal to 1, because mc squared is equal to energy. So 1/c, if mass is equal to 1/c squared, the energy is 1. So there's a picture of the triclinic crystal. It's most basic of crystals, basic crystal shapes. And we've used the parameters there of the whole physical universe, which is 1 by 8 by 22, or 3 light years by 24 light years by 66 light years. And the volume of the crystal is 76.6%. And we get our periodic, the period equal to 252 from the volume divided by the speed of light. So the sum there on the right hand side, 201.5 equals y, is the dampened cosine energy. And there's what from astral theology, there's what's called the universal vector, which is 12.82. So we're dealing with the trackliner crystal. So there's the percent crystallization and percent amorphous. The crystallization is 76.6%. The so-called ether, as Teflon, is of course a fluorocarbon. We determined that ether is MERS of 8 parts long in a linear model. As per the picture there, the carbon backbone and the fluorines off the carbons. In this brief talk, we provide some more calculations to show that previously calculated crystallization percentage is related to base E, 2.7182A. We begin with molecular mass. We see these calculations indicate that the ether is Teflon. So there's on the right hand side is a famous diagram from astrotheology. It's the time versus the energy, and we have the mass is plotted as the ln of t, which crosses the x-axis or the t-axis at 1, and the line coming down there is the exponential to the power minus t, always decreasing. So mass begins in the universe when t equals 1, and it runs all the way until t equals pi, and then it cycles back again. So it's a cycle that keeps running through from 1 to pi for the mass. So some of the characteristics we see there of Teflon has the same density as concrete. The density of concrete divided by root 3. Root 3 is what's called the eigenvector of the time, is equal to 127 for the ether. And 1 atom of C2F4 is 88 grams per mole, which is 60 per atom. And if we plug that into our Reynolds number formula, we get the 23.61, which is the ln of pi. So that brings us to our energy time diagram there on the right. So we use basic physics. Very useful information in basic physics can be used at the highest levels. And here we have a block on a plane, which you encounter in first year university physics, or maybe even in high school now. And there's an important number, which is it's Young's modulus for the universe, which I call Q's, CUZ. But it's actually pi minus E, which is 0.4233. And we see there it's calculated in the equation. 1 over root 2 is the acceleration, is where sine and cosine are equal. It's the sine of 45 degrees is equal to the cosine of 45 degrees is equal to 1 over root 2 for your velocity and acceleration. So here we're using acceleration times the mass, where we just showed was 60.4242, which is pretty close to pi minus E, which is Q's, if you want to have a label for it. the superforce overcomes. So here we have the common diagram of the stress versus the strain, which we see in structural and civil engineering. And the slope of that linear portion is the Q's, 0.4233. We don't worry about the deformation or the rupture, just the linear portion. So the coefficient of friction is ranges between 0.05 and 0.1, which is noted as mu. The bulk resistance is 10 to the 18th. And density is 2,200 kilograms per cubic meter. That's lightweight concrete. Dielectric strength is 60 millivolts per meter, which is alpha. And the magnetism is 10.28 times 10 to the 6th. So now, using established formulas from the physics of electricity, we will show that the ellipsoid universe, 1 by 8 by 22, or in light years 3 by 24 by 66, can be modeled as a giant capacitor with the characteristics of Teflon. We calculate the mass, gap, forces, power, and capacitance. We see that the field electricity provides basic formulas that can be used to model the ellipsoid universe. So there's your circuit on the right hand side with a resistor of 0.4233, again Q's, with your capacitor with the capacitance of 1 over pi. The human mind has a frequency of 1 over pi, and so the human mind evolved to match the capacitance of the universe. And then we have an inductor, which has a value of 2 henries and a voltage of 105.2 volts. These are all characteristics from astrotheology that I'm not going to calculate here, just to show that what they are in the circuit. And we see on the left-hand side there, we see where the capacitance is 1 over pi, and 1 cycle, of course, is, as I said before, on the energy time diagram, the log of pi. And we calculate the mass, 117.36. There's actually 116 elements in the periodic table of the elements, and there's 2 that are unstable, 117 and 118. We see that number crop up all the time in astrotheology. So the permeability of free space is equal to 4 pi, which is equal to 1.2566. That's approximately equal to the minimum energy of the golden mean parabola. So if we take the golden mean parabola, t squared minus t minus 1 equals 0, or equals to E, and we take the derivative of it, it's 2t minus 1, and we find the minimum energy is minus 1.25, or minus 5 fourths, which occurs when t is equal to a half. A half squared minus a half minus 1. And we have the force of friction is mu n, so if we take the 125.66 newtons times the cosine of 60 degrees, 60 degrees occurs as often as 45 degrees does in astrotheology, and for reasons I won't go into here. And so we have 6.28, which is 2 pi newtons. 2 pi times Q's is equal to the superforce, 2.666, which is 8/3. So the superforce overcomes the force of friction. As I said, note that Teflon is the 3rd lowest coefficient of friction of all known materials. The ether shows a likeness to Teflon for some. 2 pi So there's the mass gap and the magnetic. So here we're about halfway through the talk, and we come up to from chemistry and material science, we have Maxwell's construction and van der Waals equation. known the critical temperature for the universal ether is T equals 300 Kelvin. So we consider some calculations from established equations taken from polymer physics to see where the PTFE ends up. We have found that some results are recognizable vis-a-vis AT math or astrotheology math. The equations used in the following calculations come from reference one. The references are listed at the end of the paper. And then 329, and we end up with L equal to 2.988, which is approximately equal to the speed of light, which is 2.9979. So we see that the constants from astrotheology math are evident when the ether is considered as a polymer. So the ether is the mass and ancient mathematical physics. The universe is made up of two masses that have the densities of steel and concrete. So our final topic here is the how light travels through a medium. It actually has a medium, which is the ether, which is contrary to what physics. So we have the force of friction, and we end up all the way down here at the bottom, and you can see it, that SE is the soul energy. It comes back, terminology I used at the beginning of astrotheology. And there is Planck's equation. We end up with the superforce, and we end up with the speed of light. And that's the top equation there is the cross product of energy and time, which is space. And we end up with 1. So the momentum is equal to mv, is the cosine wave. Force is equal to the sine wave. So we end up with G. And as we're coming to the end here, we see that we continue with the thesis, ether is Teflon. We examine how light reflects off a crystal plane formed by the fluorocarbon polytetrafluoroethylene. We see that the calculations provide parameters that are critical in the general theory of astrotheology. We also see that the ether is well modeled. So there's Bragg's law, and the light integer. We have force on a charged particle, 1.6528, and we end up with the mass of the periodic table, periodic table ultra heavy elements and the universal Reynolds number. There's the dampened cosine energy. Y is equal to e to the minus e cos theta, and we end up with the mass of Teflon is 60.
Yes, doctor. This was the last video from Dr. S.T. Mitchell from USA. The last speaker of the session will be Dr. Anupama K. Kaul from University of North Texas from USA.
Yes. Hello.
Yes, madam.
Okay, great. Yeah, okay. Thank you. Let me just
Yes, you can.
share the screen. Yeah.
Yes, ma'am.
Okay. Share screen. Okay. Okay, can you see that?
Yes, madam, it's fine.
Okay, perfect. Okay, thank you very much for this opportunity to allow me to share some of the activities in my research group. So my name is Anu Kaul. I'm a faculty at the University of North Texas. And most of our group's efforts these days are centered around van der Waals solids or two-dimensional layered materials. And we're particularly interested in looking at their light matter interactions for various applications. So which is what I'll share with you today. So here's the outline of my talk, just a brief introduction about van der Waals solids, and then we'll move on to some hybrid systems with 2D materials where zero-dimensional quantum dots can help enhance the optical absorption. And then the third item is looking at hybrid materials, not just inorganic 2D layered materials, but organohalides, the so-called perovskites, that can also be useful for optical absorbers, optoelectronics, and solar cells. And then a good chunk of my group's activity is centered around inkjet printing. So we'll just highlight some of our recent work given the time constraint in this schedule. So just starting off, for those of you who may not be familiar, but nanotechnology was really born out of a seminal work done on nanocarbons, and it's this nanocarbon field has earned 2 Nobel Prizes, with the first one on the so-called soccer ball structure, or the buckyballs. And so in 1996, Kroto, Smalley, and Curl earned the Nobel Prize in Chemistry for their seminal work on studying the structure and properties of these buckyballs, Buckminster-Fullerian spheres. And then that's the 0D form of nanocarbons. And then the two-dimensional form of nanocarbons, graphene, which many of you probably have heard about. This is like a honeycomb chicken wire lattice of carbon atoms. And so this is basically a plain sheet, a monolayer, graphene within the 3D structure graphite, or the bulk structure of graphite. And so this earned the 2004 Nobel Prize in Physics, granted to Novoslav and Gaim at Manchester University. So nanocarbons have been extremely important. And so we'll use the 2D graphene, and I guess I forgot to mention about the one-dimensional form of nanocarbons. These are the cylindrical structures, nanotubes. And so there's been a lot of activity on nanotubes as well, single-wall tubes, multi-wall tubes, and so forth. But our attention is focused mostly on the 2D form of nanocarbons, graphene, and how this has been a building block for a wider family of layered materials. So what is a layered material? It's essentially what's shown on the ball and stick diagram on the left here. Here we have a binary system, but essentially within this one molecular membrane and then the next molecular membrane, there's a weak interaction through the van der Waals glue layer. In-plane bonding is through the strong covalent interaction. So that's really the hallmark of these van der Waals solids due to the weak van der Waals interaction. So looking at the periodic table, where do these materials come from? So if we hunt around on the periodic table, we'll see that obviously starting with graphene, which is what kicked off this discussion, carbon, single element, graphene, when it's in that 2D planar structure, we have this monoelemental van der Waals solid. However, we can then look at mixing and matching beyond monoelemental systems, looking at transition metal dichalcogenides with the formula Mx2. M is a transition metal here. These are the common ones. that are highlighted, and X is a group 6 chalcogen atom, sulfur, selenium, tellurium. So depending on whether we have molybdenum selenide, niobium selenide, or molybdenum disulfide, we can get a wide range of properties. These properties can be semiconducting, superconducting, semi-metallic, metallic, and insulating. And so the ball and stick diagram on the left is for the case of MOS2, molybdenum disulfide, and we certainly synthesize these in our lab, but we can also find them naturally existing in the Earth's crust. So molybdenum disulfide exists as a mineral. It's earth abundant. It exists as molybdenite. Okay, so we can mine for it. And so that makes it very attractive, just like this electronics industry is based on silicon, but really silicon comes from sand, which is all over our planet. So nonetheless, these some of these TMDCs are naturally occurring as minerals in the Earth's crust. So what we're interested in looking at are these light matter interactions of these materials, which are very intriguing because when we take a bulk crystal, where bulk meaning that we have many of these layers stacked up, and when we take that bulk crystal and we look at the band structure that's derived from the crystalline structure of the system, we see that we can go from indirect optical transition, which means from the valence band maximum to the conduction band minimum. There is a translational K vector that we have to think about because the transition is not direct. So there's the help of the phonons needed in order for optical radiation to cause those electrons to jump up. So that's the bulk. But what happens if we take many of these layers and then go to the extreme limit where we just have one layer, one monolayer? We see there's a transition happening in the structure, in the crystalline structure or the band structure. And due to quantum confinement, suddenly when we get just one layer, we can go directly vertically up without the help of any phonons to get electrons to traverse this forbidden energy gap into the bottom of the conduction band. So there is a transition that took place when we went from bulk to monolayer in terms of the optical properties that go from indirect optical transition to direct optical transition. So what this really means for the everyday person is that we have really highly efficient optical transitions occurring, very high-speed optoelectronic devices because of this direct transition occurring. So my activity in my group at University of North Texas, we have several areas we're looking at. We have really an end-to-end capability where we synthesize our materials in-house. The synthesis approaches occur from vapor-based techniques. So we have high temperature ovens, really. They go up to thousands of degrees Celsius, where we then nucleate crystals that form on a substrate. So this is the so-called bottom-up synthesis or vapor-based route. We can go from the other direction where we take the bulk crystal, we can purchase the bulk crystal, for example, graphite, which is really our lead pencils. So we can take that bulk crystal and place it in a vial that has a mild solvent. And then with some gentle agitation, that solvent turns black. In this case, we have actually exfoliated or basically pulverized the bulk crystal into platelets that are suspended within this ink, the so-called ink. And then that ink is then used to print structures, print circuits, print single devices using additive manufacturing. So here we have our inkjet printer where we can print electronic circuits, electronic devices, optoelectronic devices on transparent substrates, biocompatible substrates that can be bendable, foldable, and so forth. So this is the other so-called top-down synthesis route that we have capability for in my group. And once we have all these materials synthesized, what do? We can look at their properties using cryogenic transport measurements. We can shine light on them and measure how the material behaves with electrodes placed on those structures. So we're not only interested in looking at the material properties, but really at the end of the day, we want to build useful things since we're engineers, and so we want to be able to add functionality to pre-existing devices. So prototypical device demonstrations are a part and parcel of my group's activities. So our lab is called the Nanoscale Materials and Devices Lab, NMDL, and we have 2 sub-labs within this umbrella, the Material Synthesis and Processing Lab, and the Electronic and Optoelectronic Properties and Device Characterization Lab. So here are the materials on the left column that we are looking at currently. Of course, we have nanocarbons, graphene, these TMDCs, selenides, sulfides, and so forth. Other monoelemental van der Waals solids, black phosphorus, which I won't have time to share with you today, but that's also very, very intriguing material. And then perovskites, which I will mention to you a little bit about our recent activity in the area of perovskites. And then integrating these lower quantum confined structures, quantum dots, GQDs, fullerenes, endohedrals onto our underlying 2D material. What does that do to the light matter interaction? In terms of synthesis, we have CVD, PVD, additive manufacturing, inkjet printing, 3D printing. We also have the ability to work with materials that are sensitive. They are hydrophilic, and so they like water, and so that's not very good for stability. So we need to work inside a controlled environment, a ppm level of moisture, a ppm level of oxygen, and so we do have capability to work in a glove box in my lab. In terms of characterization, we look at transport, IV measurements as a function of temperature, capacitance voltage, capacitance frequency. We can shine light radiation using tunable lasers with wavelengths ranging from visible to the infrared. We can look at the fingerprints of structure using Raman spectroscopy, PL spectroscopy as a function of temperature, how those vibrational modes are changing as a function of temperature. And then I also have an AFM hooked up to our system. And we can do strain-dependent measurements by poking the materials and looking at the light matter interactions. And then so we have UV vis, optical absorption capability as well. So the devices that drive our work are shown on the very last column: nanoelectronics, flexible sensors, solar cells, and so forth. So looking at the light matter interactions, when we shine light on a material, in this case, a semiconducting material, we can cause excitation to occur for electrons that are happily located in the valence band, but once they see that radiation, that extra energy, it gives them a kick to go into the conduction band. And so, so what we then form is an electron that has now left the valence band and is now located in the conduction band. So that's negatively charged. And what's left behind is a net positive charge. So plus and minus are interacting through the Coulombic interaction, and that gives a certain binding energy for this pair. This pair of plus and minus now are really denoted as excitons. And so excitons occur naturally in semiconductors due to the very nature of the energy absorption from optical or thermal and so forth. So that's nothing new. But what is intriguing is when we look at the exciton binding energy, how much energy does it take to pull apart that electron from its counterpart, the hole? So these are exciton binding energies, that's in the middle column. And when we look at the conventional three-dimensional semiconductors, silicon, germanium, gallium arsenide, these exciton binding energies are typically less than 10 millieV. So why are we interested in looking at exciton binding energies? That the TMDCs, the van der Waals solids, their excitonic binding energies are at least an order of magnitude higher, in some cases extremely high. For example, almost approaching 1 eV in the case of tungsten disulfide, 710 millieV. So these high exciton binding energies are suggest that we can have excitons survive even at room temperature being about 25 millieV. So how do we learn all these interesting facts about our crystals is by using non-destructive measurement techniques, non-contact techniques that can allow us to probe the electronic structure of the material. And so one way in which we do that is through Raman and photoluminescence spectroscopy. So here we have a two-step photon absorption and emission process. So we shine incoming light with energy h nu subscript 1. So this energy is something bigger than the band gap of the semiconductor. And so once that electron is excited into the conduction band, the emission spectra is what is then captured in our Raman system or PL system. And so basically the emitted radiation then tells us something about the structure, something about the band gap. And we'll see that not only can it tell us something about the band gap, but also other types of multi-body interactions can be gauged by looking at the temperature-dependent PL spectra from these materials. And so that's exactly what this work our group published in about a year ago, looking at the temperature-dependent photoluminescence spectra. We can see that there are multiple peaks that emerge at the lowest temperature. So our stage is able to go down to liquid nitrogen temperatures, about 77 Kelvin. And so we see certain features that are red-shifted, meaning to the left of this energy plot, beyond the main exciton peak, the pair of electron and hole. So besides this, this peak that is characteristic of the pair energy, the exciton binding energy, we also have other peaks that can be ascribed to other multi-body interactions. What we mean by multi-bodies is that we can have an extra electron that is then hovering next to this pair, and then we form this trion or three-body entity. Or we can have the pair, the exciton pair, get localized when it sees an imperfection in the crystal. So there's a localized exciton peak that emerges and tells us something about the defect, the nature of that defect, where this exciton is getting localized. So when we look at this behavior of the PL spectrum as a function of temperature, we see that some peaks get bigger. For example, when we go 77 Kelvin to 98 Kelvin, almost 100 Kelvin, this very left shoulder now is absent at the higher temperature. That means we've broken apart that particular structure, in this case, the localized exciton, and then we have just the trion and exciton. And so as we do this as a function of temperature, we see that the exciton peak increases, and then the trion peak decreases, and then all the way up to 448 Kelvin, we can put forth some kind of a model what might be happening at these quantum scale dimensions. And so why are we interested in looking at all these is because they have some useful characteristics that make them attractive for quantum emission. Quantum emission or quantum computing, that's catching a lot of attention these days, but some of these localized excitons can serve as single photon emission sources where just a single photon is emitted. And so these single photon emission sources are a key component of quantum information processing systems. So these are all very early stage, but certainly this work appeared in 2019 and in ACS Chemistry of Materials and was also selected for a supplementary cover image. And this was work done on tungsten diselenide. And then, let me see if I can move this here. Okay. So we also have, what I shared with you was our characterization studies on tungsten selenide, but some of our group's recent work has also been on looking at interaction of 0D systems with 2D materials. So here are a host of 0D systems, just like the name suggests. These are point-like charges with a zero-dimensional symmetry. And so what are these? These are quantum dots, for example, lead sulfide, cadmium selenide, scandium. So these are endohedrals, or the Buckminster fullerene spheres that I shared with you at the very beginning. So what happens when we dropcast a solution of these 0D systems onto an underlying 2D material? What happens? Does anything happen to the light matter interactions? Are there charges that are getting transferred? And so all of those questions is what our work tried to answer. And so this is showing the soccer ball structure, the fullerenes that are decorating the surface of graphene. Okay, you can see the graphene underlying sheet. And so as you can see, there's these blue arrows that have a label on them, H+, holes, and then the red ones are electrons. So with the arrows going different ways, it's with the C60 fullerenes, when they are on top of graphene, the C60 actually likes to collect the electrons. And so, because it has strong affinity. And so once it collects the electrons, it leaves behind an empty hole in the underlying graphene. So this is basically a dopant that has doped the underlying graphene more hole rich, or it's basically p-type. And so this work appeared in ACS Applied Materials and Interfaces in 2019 as well. So we looked at the Raman, the time-dependent response of shining lasers at this system. So this was with an empty cage molecule, 60 carbon atoms, but we can also have systems where something is within the cages. We have molecules within the cage. So these are called endohedrals. So that's what we looked at in this work here. Scandium nitride is encased within 80 atoms of carbon, C80. And so these are endohedral. And so do they behave differently than C60 on top of graphene? And so that's what this work was trying to address. And here we looked at the wavelength dependent response. We can see the photocurrent is very high up to a certain wavelength, and then takes a dive beyond about 850 nanometers in the optical radiation. So that dive, or this knee point, is really characteristic of the optical properties of the endohedral, not the underlying graphene, but essentially the band gap or between the HOMO and LUMO level, the scandium nitride C80 is not actually very efficient based on that energy gap. And so we looked at the figures of merit, responsivity, detectivity, EQE for bare endohedral, endohedral with the graphene for that system. Another system we looked at was instead of scandium nitride inside these numerous carbon atoms, we have lanthanum. Lanthanum as an endohedral with C82. So we need 82 carbon atoms to make that molecule stable. And so what is the optical response like in this case? And we see that there's really no taper, unlike in the scandium nitride endohedral. We saw a taper at about 850, the dive. But in the case of this particular lanthanum endohedral, it's relatively unchanging all the way up to the limit of our tunable laser source, 1100 nanometers. And so this means that this this particular ensemble system is optically active well into the infrared regime. And why that is because indeed the optical properties of this lanthanum endohedral are such that it is optically active into the infrared. And so what we've basically done is endowed the underlying graphene with the optical properties of the overlying 0D system. And there has been some doping occurring. In either case, not only are we affecting the optical properties, we're also changing the dynamics, the photocarrier dynamics through electron and hole transfer between the two. So one is actually donating electrons and the other is taking electrons from the underlying graphene. So we can form PN type of systems for the underlying graphene. And so this work came out in 2020 in the Journal of Materials Chemistry C, where we looked at the comparative properties of scandium nitride C80 and lanthanum C82. One is an electron donor and the other is an electron acceptor, so P-type and N-type. So that's obviously with a graphene underlying system. Our group is also looking at not just graphene as the base template, but other TMDCs. I mentioned MOS2. And so this work here is looking at the quantum confined equivalent of graphene, which are called graphene quantum dots, GQDs. When we decorate the surface of MOS2 with GQDs, what happens to the optical properties or the transport properties? So this work here that came out in ACS Applied Materials Interfaces earlier this year showed that we actually get optical activity at even lower wavelengths, and that's largely due to the optical character of the GQDs, which are active within the UV region as well. And so here we did various measurements of the hybrid GQD integrated with MOS2 as a function of temperature over here. And so we see that the GQD actually causes the currents to be higher compared to the bare MOS2 at various temperatures. Okay. So, and so that's showing this IDS-VDS response. Also at the photocurrent as a function of temperature with the GQD, without the GQD, and what happens to that photoresponsivity and the detectivity as well. What about the dynamics? So certainly we get electrons transferred and holes and so forth. How fast are these things happening? And so that's a question to be answered through the temporal measurements we did for our structures. And so here we have GQDs on MOS2, and these are measurements done at various temperatures. But nonetheless, when we take our light pulses that are turning on and off, we see that the structures are reacting. So when the light is on, which is represented by this square wave type of profile, we see. So essentially we get the device reacting to the incoming light. So when the light shines, is in the on state, the device photocurrent increases. When the light turns off, it decreases. And so, so basically, this is with the red plot is with GQD and MOS2. The black plot is just with MOS2. Certainly both seem to react to incoming light, but how fast those dynamics are happening is different in the hybrid system compared to the bare MOS2. And so when we look at a single pulse, let's say a single pulse here, and magnify it, we can extract out these time constants that are reflective of the overall speed of the detector. So on the rising edge, we see this tau of rise is about 56 millisecond. On the falling edge, we see this is, of course, 90% to 10% of the maximum intensity of the current. And so on the falling edge, the fall time is around 235 milliseconds. When we look at the same behavior in the hybrid, we see that the the rise time has decreased substantially, and so too has the fall time, 25 milliseconds versus 235 milliseconds. So this work was, as I noted, appeared earlier this year in ACS Applied Materials and Interfaces. And okay, now we'd like to switch gears a little bit. So that was our activity in largely nanocarbons and inorganic TMDCs. But recently our group has also included within our family of materials looking at hybrid systems, like for example, organohalides. And why we're looking at those is because they're actually also a layered family. When we look at the two-dimensional perovskites, these are the so-called perovskite structure, we see that they're actually part of the layered family of materials as well. Lead halide layered organics. Okay, so these are shown here. There's graphene, hexagonal boron nitride, and so forth. But obviously, all of these layered materials have a Lego-like building block structure. We can mix and match different layers together, one being, let's say, semiconductor, the other being a metal or a superconductor. And so we can get a system on a chip just by stacking different dissimilar materials to yield the properties that are of interest to us. But mostly our interest, one of the interests for our group is looking at the light matter interactions, or how do these things react to incoming radiation. So the 2D layered perovskites are right in there with the TMDCs in terms of their spectrum of absorption within the near IR to certainly active in the visible, just like the TMDCs, depending on the band structure or the type of material we're dealing with. And so the graphene family is obviously something we're looking at, 2D TMDCs circled here, but now into the perovskites. So speaking of perovskites, okay, I'm not sure who this is. Okay, so speaking of perovskites, we have we have the ability to inkjet print. Oops. Okay. So we have the ability to inkjet print these perovskites as shown by the structure here. And so this work appeared in ACS Applied Materials and Interfaces in 2020. And obviously we're looking at the light matter interactions in these systems. So we can synthesize these materials in our lab using various precursors to form the 2D perovskites, lead oxide and hydroiodic acid and so forth. And then we generate this powder at the end. And the powder then can be dispersed in different solvents to form an ink. And so we can study the properties of the film that we have solidified on a substrate. Here's the 2D perovskite thin film. Here's the 2D perovskite powder in terms of the band gap over here, the PL band gap. And so we see there's some kind of a red shift when we go into the thin film. We can compare the 3D perovskite with the 2D perovskite. Again, seeing that there is a bit of a red shift when we go to the 3D perovskite, more into the longer wavelengths. Optical absorption comparison between our 3D perovskite and 2D perovskite gives us this kind of a behavior where we see it in the 2D perovskite. There's some kind of excitonic interactions that are coming about at about 600 nanometers of wavelength. So looking at the crystal structure through XRD, we can assign or ascribe various crystal planes to these peaks. And when we do the measurement of the PL as a function of temperature, we can also see phase transitions that can occur in these materials. For example, at low temperatures at about from 200 to 275 Kelvin, there's a transition occurring from orthorhombic to tetragonal, and then tetragonal to cubic at the higher temperatures. And so the PL intensity as a function of wavelength was also measured. So we inkjet printed these structures, making different kinds of inks, and then forming devices on flexible substrates. So this work that came out in 2020, ACS Applied Materials and Interfaces, was really looking at inkjet printed 2D perovskite, looking at their light matter interaction, but with electrode materials that were not inkjet printed, but they were just deposited using a PVD system, physical vapor deposition. So here gold is deposited using physical vapor deposition on top of the underlying perovskite. We took that work one step further by having an all inkjet printed structure. In this case, not only is the perovskite inkjet printed, we also inkjet print the electrode contacts. So this makes it an all additively manufactured structure, a photoabsorber that is bendable. So toward bendable optoelectronics. So this work came out earlier this year in Nature NPJ 2D Materials and Applications journal. And so we looked at two different types of metal electrode layers that were inkjet printed, obviously graphene as one type of interconnect, but also silver that is inkjet printed as well. And so some of our activity in the solution processing of these layered materials has come out over the last few years. This is looking at excitonic effects of 2D materials, platelets within different solvent chemistries, other work towards inkjet printed black phosphorus, solution process black phosphorus on top of sol gel synthesized ITO towards solar cells. And these are some other 2D materials, hexagonal boron nitride, which is a dielectric. And so this white looking solution is inkjet printed between graphene underlying and overlying electrodes. And so we can measure the capacitance of this tri-layer structure as a function of temperature and find some interesting behavior there. And that appeared in 2020 in Applied Materials Today. And then again, looking at tri-layer structure, but instead of hexagonal boron nitride, here we place a tungsten disulfide and then measure the light matter interactions in that system. And over here, this is work that came out in 2017, a few years ago, but this was towards age-related macular degeneration. So making photodetectors on biocompatible substrates that can potentially serve as implants for retinal tissue. And so here we succeeded in forming a biocompatible ink. Not only was the structure that we inkjet printed with, in this case, MOS2, was photoactive, but it was also functional when we bent or strained the system, just like the retinal tissue in our eyes. It's a hemispherical type of geometry. And so certainly bending and strain are part of that application platform. And so we looked at strain-dependent properties of this biocompatible photodetector enabled by 2D Van der Waals solids. Other things that we look at are 3D printed structures for wearable electronics by mixing TMDCs with polymers and making these strain sensors, so to speak, for detecting bodily movement. And so that came out in 2019. So yeah, and then that's basically just a quick overview of activity in my group. Everything that I mentioned today was done by my research group, NMDL, the students and staff in my group. And then, of course, our sponsors, Office of Naval Research, NSF, Army Research Office, AFOSR, PACAR, and then UNT. They all helped support the activity in some form or another in my research group. So thank you very much. And I'm happy to answer any questions.
Yes, any questions? Yes. Any questions to Dr. Anupama B. Kaul? If you have any questions, you can text in chat box. We'll be asking behalf of you. Yes.
Yeah. Okay.
Yes. Thank you very much, madam, for participating in this event. On behalf of organizing community member of Material Science and Nanotechnology 2021, we want to thank you for instant presentation.
Thank you very much. Thank you.
Yes, looking forward to meet again next. Yes, looking forward to meet again next time.
Sure. Thank you so much.
Yes. We hope you enjoy it. If your questions haven't answered during this event, you can join through email. We'll be mailing you within couple of days.
Okay.
Yes. If you go to the vote of thanks. Thank you very much to all the participants, those who joined this webinar on second virtual conference on material science and nanotechnology, that is happened today, September 17th. Our most sincere thanks to all the keynote speakers, plenary speakers, students, delegates, general collaborators, media partners who have joined from different destinations around the globe to their support and cooperation. Let us thank speakers who have responded so well to our invitations to participate in this conference. We have received several papers which will inform the basis of our dimension in various sessions. Let us thank to all the associating with this conference by your presence. A special thanks to Program Manager, Mr. Williams, for his continuous effort in putting all us together under one platform in this online event. A special thanks to keynote speakers from lecturer from Sohu Kriya, Dr. S.M. Sapun, Dr. Vijay Kumar, Dr. Tanshri Chaudhary, Dr. Gokarnation, Dr. Santanu Mano, Dr. N.M. Fivirare, Dr. Anupama B. Kaul, Dr. Gunnar Shishankar, Dr. Gerhard Klimich, as well as session speakers like Suman Ghosh, Dr. Anil Ramdas, Dr. Manish Dev, as well as, yes. If everything goes well in 2022, hope we will join in physical event with the same topic, that will be Nanotechnology 2022. I would also like to thank participants. Hope we can collaborate in the future in physical event. Electronic certificate as well as handbook will be sent through email within 2 to 3 working days after the completion of the conference. Finally, we extend our appreciation to each of you for participating in this online event. Thanking you once again. This is signing off. Bhupati. Just if you have any questions, you can text in chat box, madam. We'll be sending you all the details officially after the completion of the conference. That's all. The conference is going to end.